Good morning. Welcome to Utah Chapter ICC training for October 2020. It's good to be back and doing some training. My name's Brent Ursenbeck. I think most of you know who I am. I'm retired HVAC contractor, retired building inspector, and currently I spend most of my time working doing this type of stuff, either teaching or being a resource for those that have questions on the Energy Code. Today we're going to be talking about building science meets the Energy Code. And the reason I wanted to teach a class like this is because we have lots of questions about vapor barriers and air barriers, and why does the code want us to do this, or why does the code want us to do that? You know, I know a lot of people are really focused on that vapor barrier and maybe not so much worried about blower door testing or air barriers or how tight the envelope is or mechanical ventilation. And I think if we talk about the building science, the physical principles that we're looking at in our buildings, maybe we'll understand a little bit better the things that are critical and maybe the things that maybe are not quite so critical. So my contact information is here. If you have questions, you are welcome to contact me with questions. Text message or email is typically better because I'm not always available on my phone. And if you can put your question in that message, maybe I can answer it without even calling you back. Maybe I can answer it in the evening or something. We could not do these at no charge without the support from Dominion Energy, Rocky Mountain Power, and most importantly, the Governor's Office of Energy Development. For those that are not familiar with it, the Governor's Office of Energy Development has contracted with Nexent and myself to produce these and present these trainings, and also to make myself available. And so even though I am retired, I do spend a certain number of hours every week answering questions and preparing for trainings and working with jurisdictions on particular questions they have. So I just want to thank them and Department of Energy for some of the resources they're providing. Brittany asked that I announce that if you're looking for CEUs for this class, you need to send her an email. You should have her email, just reply to it, and she'll arrange getting the CEUs taken care of for you. I have a sheet here, and we passed it out to the group here, and most of you out there that are watching hopefully have seen it. If not, you can send me an email and I'll send you a copy, or you can go to utahenergycode.com, all one word. This is a sheet that I prepared several years ago that goes through the key components of the Energy Code, the Residential Energy Code. And what I did include on this is everything in red is a state amendment. So we can understand a little bit better, what our amendments are. And it can also be a guide. I mean, if you're doing plan review, you can take this guide and just run right through. The first thing is what's your compliance option? And so please feel free to keep this in front of you. Probably 20–30% of the questions I get are answered on this guide. One page, both sides, and there's a lot of good information there. If you have any input that you'd like on this, please let me know. So the big question is what is the science behind the Energy Code, and why is it such a big deal? Many of you have heard me talking about Manual J and Manual D and Manual S, and some of the HVAC people say, oh, this is a bunch of BS, we don't need this. We put in a furnace to keep the house warm, and we put in an air conditioner to keep the house cool. We've been doing it for a long time. It doesn't matter if it's a little bit big. In fact, it's better if it's big. So let's not worry about it. Well, it's really not that simple. If we want a comfortable building, if we want an efficient building, and if we want the equipment to last a long time, and if we want our building to last a long time, then all these principles are important. The single greatest cause for construction litigation right now is moisture. It's not that someone thinks that they didn't build the structure right. It's not that they think that, the plumbing system is messed up or whatever. It is because there's water intrusion into the building one way or another. There is mold, there is OSB falling apart, the stone is falling off the building, we have leaks around the windows, it's water. And our first thought is, well, it must be leaking from outside. Well, we have lots of water issues that are related to the building science of the building, and we're going to talk about that stuff quite a bit today. So hopefully when you're finished with this, you'll understand the importance of the building science, and you'll also understand a little bit better why these sections are in the code and what we can do to build better buildings. Now, I know we have building code officials online, we have HVAC contractors online, maybe some general contractors. So I'll try to speak to all of you. So, introduction to building science. Building design, construction, and operation can affect occupant health. That's probably one of the big ones, isn't it? We don't want mold and such in the house that's going to be causing health problems with the people that are living in that house. Occupant comfort. I started in HVAC in 1972, and comfort was an important thing, but it wasn't as important as it is now. You bought a car in 1972, air conditioning was an option. A lot of cars were sold without air conditioning. Anybody want to buy a car today without air conditioning? Heavens no, we expect a higher level of comfort. In 1972, when a new home was built, air conditioning on the house was rarely installed right when the house was built. Homes in Pepperwood and high-end homes were even installed. We installed homes. They said, well, we'll wait till summer. Do we build a home today? Do you inspect a home today that doesn't get air conditioning installed as part of the initial construction? Almost never. So the public is demanding a higher level of comfort. And if we don't build that house applying the principles of building science, then we're going to have a house that has problems. Now the HVAC people know there's a big push to do load calculations and duct designs and select the right equipment and everything, and there's a little bit of disagreement sometimes about this. They don't think that the code official should be asking the questions, and they think that they know what's right, and many of you do know what's right. But building departments are constantly getting calls from people saying, my house isn't comfortable. And then there's a debate, well, they made me put in a smaller air conditioner, and it goes back and forth. Well, as we talk about these principles of building science, maybe we'll understand a little bit better how important it is to accurately apply the science and do the load and do the duct design, because rarely is the HVAC problem related to the system is too small. It's almost always there's a room or a section of the house that's too cold or too hot. It's almost always a distribution problem. I see 125,000 BTU, 95% efficient furnaces installed in relatively small houses that are 5 and 6 times larger than they need to be. And I'm kind of flabbergasted by this. But why would we need a furnace that big? And what does it create? It doesn't solve that cold room problem. It makes that cold room problem worse because the furnace turns on for a short cycle and shuts off. We don't get any distribution if that isn't running. So as I go through this, please feel free, if you're in the audience here and you have a question or a comment, I'm going to ask you to step up to the microphone so that people that are online can hear it. And don't be shy. If you would ask a question sitting in your seat, please feel free to jump up. And I'm going to be asking you questions, so be ready for that. Building energy consumption. If we do everything right, if we apply the principles that we're talking about to the design of the building, the insulation of the building, the air sealing of the building, the HVAC of the building, we're going to have a more efficient building energy-wise. Building durability. That's one of the big things that we really need to think about. There are homes that are 100 plus years old in this valley that are still pretty durable. They haven't rotted away. They haven't had a lot of moisture issues in it. And part of that is that they breathe so well. They're grossly energy inefficient, but they breathe so well that any moisture they get in it dries right out. And then they're not using plywoods and OSBs and materials like that that are water sensitive. And so they can last for a long time. Without a doubt, the materials we use and the tightening and the construction methods we use, the stuccos and everything, adds a risk of having some moisture issues. And so if we don't do things right and if we don't understand the building science, then we are going to have issues with that building. And it's not going to go 50, 80 years without something having to be repaired. How many buildings do you see that are 10 or 15 or 20 or 30 years old that the stucco is all pulled off and redone? The life, the durability of some of those products isn't really that long when you think about it. The house I'm in right now was built in 1992. I bought it in 2005. And in 2007, 2008, when I went to change the windows out on the house, I ended up tearing siding off the house to fix the OSB that was damaged by water. And it was because the code was a little bit behind and we weren't doing the flashing and we weren't doing the building papers and everything that we do today. That's not a very old house that you're tearing siding off to fix the structural sheathing. So what is this building envelope that I've been talking about? The building thermal envelope separates conditioned from unconditioned space. And with that comment, and I'm going to talk about this a little bit more as we go through, separates conditioned from unconditioned space. When we go out on a home, whether we're building it, whether we're a subcontractor, whether the inspector, and we do a weather barrier inspection, where do we see the weather barrier? Wrapped around the entire house, right? Do we see the weather barrier applied to the wall that separates the house from the garage? We don't, do we? What is the thermal envelope? Is the outside of the garage the thermal envelope, or is the wall between the garage and the house the thermal envelope? That garage wall is part of the thermal envelope. With the hurricane, I don't remember the name of it, 3 or 4 ago that hit Texas, Louisiana area, they had 90 some odd deaths from the hurricane, and almost half of them were from generators. People were starting generators because they had no power, putting them in their garages. They cracked a door or cracked the overhead door a little bit and run the generator. And then they'd wake up dead in the morning. Why? Because the wall separating the house from the garage is not near as airtight as we might think it is. And that's even today. People that do blower door testing tell me all the time that there's substantial amount of leakage between houses and garages, and in fact there's even test procedures. You go on YouTube and you'll see lots of procedures on there on how to tell how much leakage is just going between the garage and the house. People die from using charcoal in garages because it leaks into the house. So we need to remember what the thermal envelope is. And sure, we need to protect the outside walls of the garage from the weather, but when we're talking about an air barrier between the inside of the house and the unconditioned space, that's a whole nother thing. So we actually have two areas that we want to protect. So yeah, we want to protect the exterior here so the garage doesn't experience water damage, but we also want to protect the wall in between there. So the three areas that we're going to focus on the envelope, and remember this is the envelope. I'm not talking, when I say airflow, I'm not talking about HVAC airflow. I'm talking about airflow through the building envelope. All of these are talking about movement through the building envelope. Heat flow, and we're pretty familiar with that. It gets cold outside, the furnace turns on to replace the heat that's leaked out of our house. And moisture flow, the moisture that flows in and out of our house. Now, I've broken this up into three sections, but it's really pretty much impossible to talk about one without talking about the other, because they all impact the other. And what I'm saying is, we have airflow through that building envelope, right? We have some air leakage. And to make it 100% tight is pretty difficult. So we have this air moving in and out of our building envelope, and we can debate how much leakage is good and how tight is too tight and all those types of things, but we do have leakage or airflow through that envelope. And then we do have heat flow, and that's heat that's actually conducted through that envelope. And then we have moisture flow, and that's moisture either from outside in a humid climate or from inside moving through the envelope. The thermal envelope, we know what that is. It's everything that separates conditioned from unconditioned. So here's a diagram that kind of defines the building envelope. And it consists of the fenestration, the windows and the doors, the ceilings. So we have a ceiling here, we have a ceiling here, a ceiling here, a ceiling here. Walls here. This is a wall right here. Walls, walls, basement walls. And we could have a crawl space wall depending on how we do this. This could be a wall, and this could be a ceiling. In fact, that's the way I'm going to tell you is the best way to do it. Above grade walls, below grade walls, mass walls. We'll talk about those a little bit. Floors, here, here. That's it. This floor is over conditioned space, so we're not worried about it. Slabs, here. Crawl spaces. Consider the insulation, an air barrier on one, hopefully both sides of the insulation, and what happens to moisture in the envelope. So the insulation, we try to insulate this whole thing, and we have requirements in the code for it. And those requirements are based on what? They're based on building science. You know, there's reasons that we put more insulation in walls now than we did in the past, because we know it's going to save on how much heat is flowing through that wall. Air barriers, and you're probably going to be sick of me talking about air barriers before the day's out. This wall right here, an insulated wall, it separates conditioned from unconditioned space. What do we have to do on the air barrier here? The code tells us that we should enclose our insulation on all 6 sides if it's fiberglass insulation or some other type of insulation that relies on air. So we need to put an air barrier on the back side of this short pony wall or knee wall. What's that air barrier? It'll be OSB, it can be Tyvek, it can be, anything that's an air barrier material. And why is that so important? because I'll step to the board real quick. I have those are going to go in the trash. I don't know, what do we save markers that don't write? I have a wall. Inside, out. So just like this wall here. If it's cold here, and this is fiberglass insulation, what's going to happen on the back side of this wall? This wall, this is warm right here, right? This is warm because of the heat that we're producing in the house. And what does warm air do? It rises. So we're going to have air rising up along this surface. As air rises, what happens? It pulls in some air from the attic, and it comes up to the top, and then it comes out. Now, if they didn't block on top of the wall, then it's going to go up into the insulation above. But what we get is we get a convective flow within that wall that goes like that. And you can take thermal imaging cameras and you can see that happening in any time you have a knee wall or a wall like that that doesn't have an air barrier on the back side. What happens if you move air through insulation? It doesn't work very good, right? It doesn't work very good. I'm going to have a slide that we bring up in a little bit. You put on a sweatshirt, you put on a sweater, and you go outside and it keeps you warm until the wind blows. And then when the wind blows, what do you have to do? You put on some type of windbreaker, don't you? So the air doesn't go through it, because as soon as the air is moving through that sweater or that sweatshirt, the insulation effect is gone and you're cold. If you want this insulation to work, you need to have an air barrier on the back side of the insulation. Any vertical insulation is going to get that convective flow in it, and we need to do that. I'm going to give you an analogy that I think really kind of tells the story real well. We spent a little bit of time this summer, my wife and I, up in the Uinta Mountains. And we'd drive down up Provo Canyon, through Camas, and up into the Uintas. And every 2 days, if I stay there for a week, guess what I have to do every 2 days? Drive down to Camas and do what? Get some more ice for the coolers, right? And so every 2 days, you make a trip down and you get some ice.
Buy a good cooler.
The question is, why don't I buy a good cooler? Exactly. Why don't I buy a good cooler like this, right? Because how long does ice last in one of these? 10 days. And why does that work so well? Because it's it reduces the amount of heat transfer either in and out of the cooler, and it does it by higher R value on the insulation. And what's the other thing? It's air sealed. They have a good gasket system. They even have a little lip here that's sticking up that, interlocks in there. It's kind of a tongue and groove with a gasket in it. And so it seals it up so it's air sealed. Now you won't get 10 or 11 days, or you won't get 2 days with the cheap cooler if you open and close it and open and close it and open and close it a lot. But if you limit the amount of opening and closing, you can go 10 and 11 days with that cooler sitting outside, and it'll still have ice in it. Higher insulation, air sealed, so we have less airflow because of the gasket, and we have less heat flow because of the insulation. And the insulation has a really good air barrier around it, and in fact the insulation's foam, so it's airtight. There's no air going through it, it's closed cell. So it works really well. What's the problem with it? You can't live in that, in a great big Yeti or Pelican cooler, because why? Because you don't have any fresh air. So, if we want to compare this to a house, and there's people that say, yeah, let's build a house that's as tight as a Yeti cooler. Let's build it with ICF construction, foam, 2 layers of foam, solid concrete, really seal the windows well. We have a house that's real tight. And someone out there is going to be thinking, well, it's too tight. You just built the house too tight. I'm going to tell you, you can't build a house too tight as long as you ventilate it right. As long as you make sure we're getting some fresh air into the house, it's great. And in fact, if you build that Yeti house and you ventilate it right, you're going to have the healthiest house because you're completely controlling the introduction of pollutants from outside into your house. You can filter the air that you bring in. It's not moving through your building envelope. You're controlling it with a duct and a mechanical fan, and you can precisely control the air quality in the house. You can remove the contaminants from the source wherever you generate those contaminants. So this is a great comparison to what we're trying to do. So we have the 3 principles that we were talking about. The first one is the flow of heat through the building envelope. The second is the flow of air through the building envelope. And the third is the moisture flow through the building envelope. And that's the one that we're really going to be circling around a lot of the day today. And that's kind of the final item. This is the item that destroys buildings. This is the item that makes you have to tear all the stucco off, all the stone off. I mean, how many buildings have you seen that have what we call lick and stick stone? That the stone's failing in a matter of a few years, falling off the building. And it's because of this. Now, each one of these is broken up into 3 or 4 different areas. The heat flow is conduction, convection, and radiation. The air flow is leakage, wind, stack effect, and mechanical fans. And the moisture flow is bulk moisture, capillary moisture diffusion, and air transport. I'm just going to briefly talk about these right now, and then we'll go into more detail. Conduction. What is conduction of heat? If I have a wall, hot and cold flows from hot to cold. If I have a wall and it's a solid material, and let's say it's the Yeti cooler, something like that. If it's hot on one side and cold on the other side, we are going to have a certain amount of flow through it, depending on what? How well it's insulated. What's the R value of the insulation? And so we have heat flow because of conduction. There's no air movement through it. It's simply conducted. It's like heat moving up a hot tube. If you solder a copper pipe and you're soldering right here, it's going to get hot down the road, a foot away, and you still can burn yourself on it. That's conduction. Convection is when heat is moved by air. And so when I installed forced air systems, I was heating the houses using convection. I was heating air and then mechanically moving the air around the building. We have convection going on right now with air coming out of these registers being drawn back. That's all convection. We are moving heat in air. In our discussion on the building envelope, when we have air moving in and out of this envelope in the wintertime or in the summertime, we have that conduction, but we also have that convection that's based on how leaky the building is. Now, if we tighten it up, we reduce the convective flow through the wall. And then we have radiation. That's the sun's rays that come down and carry heat, within those rays. That's the stuff that when it's cold outside, but it's still and sunny, and you walk outside and you go, oh, this feels so great, the sun on me. That's the stuff that warms your house on the south glass in the wintertime. That's the stuff that makes your house brutally hot on the west side. If you have a big west window and the sun's beating on it, that's all radiation. So we can flow heat through our envelope through any of those three. The airflow, we've already touched on a little bit. If we have airflow through, that's leakage. We have wind that blows through our house, stack effect, mechanical fans. Stack effect is what? It's the chimney action. Everybody's familiar with B vents. What's a B vent? A B vent is not a positive pressure vent system. It is not a sealed vent system. A B vent works on stack effect. We introduce product combustion from a water heater or a furnace into the B vent, and it is not fan forced up the vent. It rises because what? Warm air rises. It's hot and it rises. And it actually creates a draft. We have the same thing occurring into a house or a building, and the taller the building, the more stack action we have. We have vestibule requirements in the commercial code because, in part, because those taller buildings have lots of stack action. That heat tends to rise. You take a home, my home has a basement and then 2 stories, so I'm 3 stories high. And I probably ought to do this and put it in this slide, but if I took a low pressure measuring device like you'd use on a blower door and sampled the pressure at the basement floor and sampled it at the basement ceiling, we would find that we have a different pressure, and that's simply by heat rising. And what does it do as it rises? It rises, pulls in air down low, and leaks out air up high. So sealing the building can stop that stack action a little bit. And then, of course, mechanical fans. If we have fans running in the building, if we have HVAC systems running in the building, we can end up moving air in and out of the building through those fans. And sometimes we don't want it to be moving in and out. For example, we have duct systems that are always installed in, not always, but lots of times installed in attics. What happens if the duct system is leaking in the attic? We're blowing air into the attic, right? Leaking supply. We're exhausting air out of the house with that leaky duct, which means that it has to be replaced by air coming back in, leaking in to replace it. So we're moving air through the thermal envelope simply because we have a duct system that we haven't required the blower door test, the duct blaster testing that they're supposed to have. Moisture, bulk real quick. Bulk moisture is the moisture that leaks in a building from outside. If we don't do the roof right, if we don't do our weather barriers right, if we don't do our flashings right, any of those things that we don't do right, we allow bulk moisture to leak inside. So that's large quantities of moisture potentially. When we get to talking in depth, I'll have you step up the mic and we'll talk about duct blaster test, okay? So that's bulk moisture. What's capillary? Capillary moisture is what you get when the stucco guy comes in, and what does he do when he prepares for the stucco? He comes in and he does his paper and he does his lath, and then he puts a little strip of metal down around the bottom, a wheat screed that has some drain holes in it, correct? So any moisture that gets in there can drain out. Any moisture that comes down on the backside can get out. But then they get lazy, and we don't pay attention to it, and they get over to the jambs around the garage doors, and they run the stucco just all the way down to the concrete. And they don't put their metal and give a little space down at the base there so that it can drain. And so if the concrete gets wet, what happens? the water wicks up in the stucco, and in a few seasons it's going to fall off down around the bottom of the jamb. You get water in a basement, and even if we only have this much water in the basement, how far up does the drywall get wet? Right? That's capillary action. It is drawn up through the materials. If you have a gap around a 1/4 inch, there's debate if it's 3/16, a quarter, 5/16. If you have a gap between materials, you break the capillary action. You know, we have drip edges bent so that water by capillary action doesn't track back. But we do have water moving that way. Then we have diffusion, and this is the one that we tend to spend lots of time worrying about. And diffusion is if I have a sheet of drywall with no holes in it, you know, sealed off around the edges, and I put moist air on one side and have a dry air on the other side, the moisture is going to slowly diffuse into the drywall and out to the other side. And we are going to get a movement of a certain amount of moisture through that drywall, and that's what we call diffusion. And it moves through everything except what? Vapor barriers, right? We put a vapor barrier on, so we stop the diffusion. And vapor barriers work if they are a vapor barrier, and truly a vapor barrier.
How come on underfloor ductwork?
If you got a question, I need you to step up to the mic.
Talk to the hand.
What is it?
If you have underfloor ductwork, I could never figure out when you use radiant, you put rigid insulation under it, but on ductwork, there's no insulation.
Let's talk about that when we get to insulation on ductwork, okay? Moisture flow by diffusion. Air transport. This is the last way we move moisture. And this is the one that I think we miss the boat on. We miss the boat a lot. This morning I jumped in the shower about 6 o'clock and added some moisture to the air in my bathroom, right? So we have this moisture in the bathroom, and what can I do with that? I can turn on a fan and exhaust the moisture out, right? If I just leave the moisture in the bathroom, it's going to get mixed in with the circulating air and stuff if the heat turns on, or it's going to move wherever air pushes it. So if my bathroom has a tight-fitting door, the furnace turns on or the air conditioner turns on, and it creates a positive pressure in my bathroom because it can't get back to the return, what's it going to do? It's going to leak wherever it can, and one of those places it's going to go is through the walls to outside. If there's leaks in the wall, it's going to move through the wall. So we are going to air transport that moisture into a wall cavity or up into a ceiling space or up into an attic space or up into the floor above. The moisture is part of the air. Just like we heat air, the heat is contained within the air, the moisture is contained within the air. So if we're moving air that has moisture in it, we're taking moisture with it. If I move it into a wall cavity and the conditions are right for it to condense, then it's going to condense. Now someone's going to be saying, well, that's why we put a vapor barrier so we don't move it through the wall. Well, the vapor barrier is stopping diffusion. Now if it's airtight, it's also going to stop airflow. But we're going to talk a little bit more in detail about that because we know that we are going to have some airflow through that wall because why? Because we have a electrical box or the drywall doesn't fit tight to the floor or the vapor barrier has a hole in it. So these are our three physical properties that we're going to spend our whole day talking about. And applying these principles in the system design, the selection of materials, the installation procedures, and the verification. And a code official is involved in all four of these. An HVAC guy is involved in some of those. A general contractor is involved in them. Architect, design professionals involved in those things. So we need to, in the design of our building, doing our load calculations, we need to be thinking of all these things. We need to select the right materials. Some materials aren't damaged by water. We need to make sure we install it right, and we need to make sure we verify that it's done right. So system design, real briefly, we'll talk about our climate zones. I think it's, I've heard a lot of complaining about the energy code, and you guys have heard it too, and as an HVAC guy, I complained a little bit about it sometimes. And there's the attitude, well, we're worried about life, safety, and health, and we're not worried about anything else. Well, the code says also the general welfare. But I'm here to tell you that that HVAC system and the energy code directly impact our health simply because of pollutants in our buildings, mold in our building, mildew in our building, radon in our building, all of those things, viruses in our building. How many times have you heard someone talk about, well, if the building has a poor ventilation system, we're going to spread the virus a lot more than we are if it has a good ventilation system?
It's really stupid. They got the plexiglass, and yet all that droplets get sucked up into the HVAC.
We'll talk a little bit about the flow of contaminants when we're talking a little deeper into airflow. But yeah, there's things to consider, And I'm not going to talk politics here. If someone wants to talk politics, you can leave and we'll talk about it later. But we can filter the air. My son manages the building engineer for a number of large office buildings. And as soon as this started, there was a big run, and it was really hard to get a hold of MERV 14, MERV 13, and MERV 14 filters, which are the filters that are tight enough that guess what they do? They start becoming effective in grasping and arresting virus-sized particles. And so the HVAC systems can be a big benefit in keeping our building air quality, high, keeping good air quality, because we can pull it back and remove it. And then we can consider our airflow pattern. What is the airflow pattern in this building? Well, you have to look at where the supply's coming in and where the the return grills are and the return panels. The returns back there. These things all impact the contaminants in our air. And it's not just viruses, it's everything else, including the moisture. But we have 8 climate zones, and actually we have 9 climate zones now because we have a climate zone tropical. And every climate zone is a little bit different. And because every climate zone is a little bit different, the building science principles have to be applied a little bit different. Now, I am generally going to be talking today about our high and dry climate. I'm not going to be talking about what it's like in Houston, Texas. I'm not going to be talking about what it's like in Hawaii or what it's like in climate zone 8. I'm going to talk more about the climate zones that we're in. And so what I talk about here today would not apply in other locations. We'd have to look at it slightly differently. So climate zones take into account, of course, mostly the temperatures and the humidity. We have to consider which way the building faces, what's the wind in that area, what's the use of the building. Generally, we're going to talk residential, but in commercial buildings, the use might be a little different, so it'll change things, but the principles still apply. The materials used, the energy source. Are you burning gas? Are you using all electricity? Are you taking advantage of the solar radiant heat? And then our HVAC systems, which we address through all of those things: comfort, humidity, surface temperatures, and airflow and noise. So the materials. We have a lot of materials that are being installed on this house. And I think it's pretty amazing that we can get so many people, so many subs, and so many bosses, and all coming together and creating a finished product. It's kind of amazing when you think about it. And I can see why some superintendents are pulling their hair out, because trying to get all those people coordinated and doing everything right is kind of a challenge. And that's our problem if you're a code official, and it's your problem if you're the HVAC contractor, because if the building doesn't get built right and the building isn't comfortable, the HVAC contractor gets blamed for the uncomfortable building. But if someone messed up on the insulation of the building, it's really not the fault of the HVAC guy. So understanding how these all fit together is important. So we have all these components that have to be used properly, and we see them used wrong all the time, and we miss it sometimes. Our installation procedures, we have all of these as resources: the codes, the standards, the engineering, manufacturers, installation instructions and listings, and ES reports. I don't want to get into a big discussion on this, but there are products, and I've had these challenges before. There are products that are manufactured that have specific installation requirements that are part of their listing. I don't care what the sales rep or the sales manager or the district territory manager or even the building engineer says. If the product was manufactured and the listing requires it to be installed a certain way, I think it needs to be installed according to the listing. I have heartburn with a letter that says, "I've reviewed this installation and it's good." Based on what? If it's not installed correctly, it isn't good. So any of those types of letters, they need to have something that addresses the reason that it was noted on an inspection. With all the complaining about energy code sometimes, it's really kind of interesting. Is there any other code that gives you 5 options to comply with the code? I don't think there is there? You build a home in Utah, you can build that home by complying with the prescriptive code. You can comply with ResCheck. You can do a performance model where someone with modeling software models the energy usage of a standard reference design home versus the home you're going to build. You can have that home rated by a HERS rater, or an energy rating index as it's called in the code. So we can give the home a score, an energy score. And in Utah, we have the 5th option that we can use the 2012 ResCheck and pass currently by 4%, next year 5%. And maybe we'll revisit that 5th option there on the bottom. But we have one of those 5 options. And all of these options have some building science to them. Any one of the upper 4, if you compare the prescriptive home to the ERI home, they are generally going to use similar amounts of energy if they both just comply. Now, they're not exactly going to be uniform, but what I'm saying is there's some uniformity. We have a prescriptive table that says do this and this and this, but then we go to what? We go to ResCheck and we say, yeah, but if your walls are a little weak and you go a little bit better on your windows, we're okay. Because why? Because it's going to average out to similar thermal performance. And the same thing with the simulated performance. So the goal is to give flexibility in the way we build a home, but also to allow to be energy efficient and to have the flexibility. I look for the day that the one on the far end, the energy rating index, is what we use, because that one's the very best one, because that one takes into account all the energy we're using in the house. It takes into account our appliances and everything else. So that's a really good path. Why is this one in there? So that they can still have the equipment trade-off. That's the reason it's there. They can put in a high-efficiency furnace and offset a weaker building component. But guess what? They can get the equipment trade-off using this method. All building science. So how do we verify that the building's built correctly? We do inspections, we do special inspections, other third-party inspections. We do blower door testing, we do duct pressure testing, and on our HVAC, we do some type of startup procedure ensuring the equipment's running correctly. So let's talk now about the heat flow basics. And I touched on these a little bit already, but we have the conduction, the heat flow from warmer to cooler. And it depends on the R value and the temperature difference. So if I have some material, let's say it's a piece of steel, and we put some heat to one end of it, what's going to happen? Heat flows. Real straightforward, isn't it? If you have hair this color and you went back in the days when we used to take a coat hanger and straighten it out and put a hot dog on it to cook over a campfire, didn't take very long before the heat came up the wire, did it? And your hand was hot. But if we use a willow branch to cook that same hot dog, does it ever get hot? No. Why? Because the wood is insulative. The wood gives us some insulation and the heat doesn't flow. So depending on the material, we are going to have that kinetic transfer of energy in the form of heat through that material. And sometimes we want to transfer heat that way. Our furnace, we use conduction in the heat exchanger. We have flame on one side, we have air blowing across the other side, and we want to move as much heat as we can from the flame through that conductive wall into the airstream. And if you look at a furnace nowadays and you look down in there, instead of just a clamshell type thing that the heat went up through, what do you see? Has a design where the products of combustion go back and forth. So there's large surface area to transfer the heat from the products of combustion through the conductive metal into the airstream. So that's conduction. And as we did in the cooler, if we insulate or use an insulative material, we stop the conduction. Convection, transmitted through air or water, or any liquid or any gas. And if we open a window, what do we have? We have some conduction, some convection. We have some air that's moving through that opening. Now, how big of a hole does a typical house built today in the valley, 2,000 square foot house, how big of a hole might we have in that thermal envelope if we added up all the little holes? There's people that go through all these calculations and formulas based on blower door testing, and they'll say, we blower door tested your house and it leaks at an air change rate of 5 air changes per hour at 50 pascals, which is equivalent to a 4-foot square hole in your wall. So a 2x2 hole in your wall. A hole maybe just a little bit smaller than that piece of paper. But if we make that envelope tighter, if we do some what? If we make sure we do a little bit of gasketing, if we make sure we lap the OSB over the rim so that we don't have a seam right at this where the plate lies on the floor. If we do some of these things, then we can get the house tighter, and it might only leak at 3 air changes per hour, which would mean we have an equivalent hole that's a little bit smaller. And if we keep going, we're going to get smaller and smaller. And that's kind of our goal if we want to have a fairly tight house. So someone might have the question out there, okay, we're making our houses tighter and tighter. We're reducing the convective flow. We're reducing the amount of fresh air that comes in. We're reducing the amount of pollutants that leaks out. Wouldn't we be better to just let it leak? Then we'd have better air quality. Would we really have better air quality? How much? If we have air leaking in and out of our house by simple wind pressure on it, opening and closing doors, and changing pressure in the house a little bit, we crack the windows a little bit. Let's say we crack every window in the house 3/8 of an inch, so we have enough leakage to, quote, give us some fresh air. How good a job is that going to do at clearing out the stink that you get when you cook fresh cauliflower or something in the kitchen? It doesn't do a good job, does it? We're not at the source. We're leaking in and out. Does opening the windows in the kitchen and family room do anything to freshen the air in the bathroom at the other end of the house? No, it doesn't do anything. If we can control it, we control the air that we're taking in and out of our house, exhausting at the sources, or gently always changing the air in our house, then our air is a lot fresher. So anytime we leak air in and out, we're leaking heat either in or out, and we're leaking moisture in and out. And if that leak is through a wall, through an outside wall, we are taking the moisture with it. And the last one is radiant heat. That's the sun's rays. Why do we call in-floor heating radiant heat? Because actually it does radiate a little bit up off the floor, and it makes you feel good. If you have a brick house or something with some mass on the exterior surface and the sun beats on it all day, and then the sun goes down and it cools down, and you walk by that wall, what do you feel? You feel heat coming off that wall that's radiating back off at you. You stand in front of a fire when it's cold, we feel nice and warm. Part of it is the heat that's conducting through the air, but the majority of it is the radiant heat from the flame. How many have paid attention when you're on an airplane? Some of them have the little screen on the back of every seat, and you can hit the flight information, and it will tell you at what altitude you're cruising and the outside temperature. Anybody paid attention to what the outside temperature is at 30,000 feet? It's cold, isn't it? I mean, sometimes it's summertime and it's 0 degrees at 30,000 feet. Why is it 0 degrees at 30,000 feet? Aren't we closer to the sun? Yeah, we are. The radiant heat, we don't feel the benefit of the radiant heat until it strikes something. So the radiant heat strikes the atmosphere as the atmosphere gets thicker and warms that atmosphere. It strikes the earth and warms the earth. It strikes us. It strikes the roads. It strikes everything and absorbs that radiant heat and gives off the heat as thermal energy. So radiant heat is a big piece of what we have to deal with, the building science. My son that works in large commercial buildings, the previous buildings he worked with, they built a large building, and I think it was a 40 or 50,000, maybe a 60,000 square foot building while he was with that group, and they put dynamic glass on it. Has anybody heard of dynamic glass? That's the glass that has a film on it, and if you apply an electrical charge to it, it turns turns obscure. It darkens. And actually, the glass in that building, they had 4 steps in the glass. And it was hooked to the BMS, the building management system. And so as the sun would come up on the east side of the building, it would darken the glass, change the reflectivity, decrease, the solar heat gain coefficient, so it allowed less radiant heat into the building. And then as the sun moved, that building automation system automatically changed which glass it darkened. Really a cool system. And you might think, well, that's a fancy system. Why would you do that? Because it took, I can't remember the number, but I think it was 35 tons off the chiller size. They reduced the chiller by that size, which means they reduced the amount of energy they had to remove by using the chiller, which is expensive. You remove 35 tons of of heat through the cooling process, you're paying a lot of money to suck that heat out of the building. If you can stop the heat using building science, it's a bonus. It's a big deal. And you can literally go in with your phone and you can change any section of glass in the building. You know, if you're going to have a PowerPoint presentation in a conference room, you can darken the glass. I mean, pretty cool stuff.
The amount of mass you got inside the building, concrete stuff affects it too.
Well, the mass in the building affects it, but if you can stop the radiant heat from hitting the mass, that's a plus. But if you want the mass to absorb the heat, then that's a plus, that's a bonus. Passive radiant homes do what? They have south-facing glass that has a higher solar heat gain coefficient, so you let the heat in, and then you have mass. You put in CMU walls, you put in concrete floors, you put in hard surface floors, so they can absorb the heat, and then you can use it through, you know, to heat your building. So yeah, radiant heat can be a bonus, or it can be a challenge. My previous home, on the front of the house, I had 2 big windows, you know, 2 separate little dormer kind of things, and I had 2 big windows on the front of the house, and they were facing south. And I put in low E glass and everything, but in the wintertime, when we had a bright sunny day, my office would get so hot that I had to open the windows. It'd be 10 degrees outside, but it was still so hot because of the radiant heat. Only 30% of it was getting through, but it was enough to make it uncomfortable. So it can be a plus or a minus, but we have to understand it. So, third form of heat flow. We measure, just like we measure gallons of water. I'm going to have a slide later on that we talk about how many gallons of water will go through a piece of sheetrock by diffusion and how much goes through a 1-inch square hole through that sheetrock. And so we measure water in gallons. We measure heat energy in BTUs per hour. And 1 BTU per hour is the amount of heat that will raise 1 pound of water 1 degree Fahrenheit. And it's just a matter of reference on how we measure heat. But if we know how to measure heat, we can measure how much heat we're going to lose through a wall, or how much heat we're going to gain through a wall, and how much heat we either have to add or remove with our HVAC system. Okay, here's a thermal image that I took in my house. How many are familiar with these? Some of you a little bit. This camera only sees heat. It doesn't see anything but heat. If everything in that view was exactly the same temperature, it'd just be all the same color. And there's a little scale on the side. 68 is the warmest temperature and 58 is the coldest. So there's 10-degree temperature difference inside my living room, my front room, at the time I took this picture. And the temperature right there at that spot is 64.2 degrees. So obviously, what's this? It's a stud, right? This is a corner. Now the window here, it reflects and it kind of confuses the camera, so we won't worry about that. But paying attention to this wall, we can see that in the corner, it's the very coldest. Why is it colder there than anywhere else? Because we're losing more heat there.
Plus, it doesn't circulate as good there.
No, it's because we're losing heat through the wall. It's the surface temperature. Yeah, maybe it would, maybe 1/10 of a degree is circulation of air, but it's really the conduction of heat through the wall components. What's this right here? It's actually the corner. My wife has one of those antique pump organs. And it's not touching the walls, so what temperature is it? It's room temperature. There's nothing that's removing heat from it, right? The heat's being sucked out at all these places. So cold isn't coming in, heat is being removed. The air in the room can't keep the surface warm because the heat's being removed, right? Quicker than the air just sitting in the room can warm it up. We can even see, if you look closely, you can even see the nails in the sheetrock. That's because the nails or the screws go deeper into the wood, and so they have less R value beyond the tip of the screw. So every place that it's darker is where we're losing heat at a greater rate. And this is conduction flow for the most part. But going back to the corner, well, let's go to the cavity first. So I have insulation in here, probably R13, and then I have a stud that has R1 per inch, which is, so it's like R3.5 right here. And I have 3.5 on this stud and 3.5 on that stud, but I have a corner that's worse. And why is that? Because I don't have any insulation in the corner, right? There's no insulation in the corner. And so it's worse there. And what's the other thing? And we'll go to this. There's one other thing on this that we need to think about. How tight is the seam on the corner of the OSB? It's not, is it? Yeah. The sheetrock is tighter than the OSB on the outside. And so we have an uninsulated cavity because of the way they framed the corner, and we have air leaking into it. And it's for that reason we have more heat flow through that corner. My house didn't have a weather barrier when it was built. So materials that resist the flow of heat are assigned an R value, which is a measure of the resistance to heat flow, which is the reciprocal or of the U factor that we see on windows, which is the ability for heat to flow through it. So if we have a high R, we're going to have a low U. And we'll talk about that a little bit more in another slide or two. So this thermal camera really tells us a lot of information on how this is flowing, how the heat's flowing. So here's some of the things that we can do. And I'm going to bring this up because for everybody that's an inspector out there, they should be thinking about this. Everybody that's a design professional should be thinking about this. This is probably how my house is framed, right? Something like this. And it might even have, this over a little further and another stud or whatever, but it's going to have a bunch of wood in the corner, no insulation in the corner, and this joint is not that pretty. Pretty safe assumption. We can frame it this way and we can get some insulation behind it, or we can frame it this way using only 2 studs and some type of clip. And they make little drywall clips so you have some backing, and that'll get you some insulation there. Now, I kind of like a hybrid of this. When I've been doing remodeling in my house, I take a little piece of OSB, a couple of inches, 3 or 4 inches wide, and I screw it to the back side of this so it comes over here. Then I can get good insulation behind it, and I have full height backing behind my drywall there. It's a little too springy to put nails into, but you can screw into it and it works really nicely. SIPs, structurally insulated panel, they work well, but you do have to foam some corners.
They overlap though.
Whatever the design, I'm really not saying one is the one that we should all go to. The thing we want to always be thinking about is, do we have conductive flow through it? Do we have air flow through it? And if we have flow through it, do we have moisture flow through it? Those are the three things that we've got to be thinking about. So what's the U factor? It's how quickly or easily heat flows through a material. It's the inverse of the R, and we're very familiar with these stickers. If you're an HVAC guy, or if you're a general contractor or you're a design professional, you should be concerned about the window you're putting in. Number one, you need to put in a window that complies with the code. We don't want to put in a window that's obsolete and it has a U factor of 0.5. You know, I mean, that's a crappy window. In fact, that window doesn't comply with the prescriptive table anymore. It's lower than that. The smaller the number, the better the window. Because why? Because it means it's more resistant to heat flow. Small is good. So remember I said R equals 1 over U? Well, U equals 1 over R. And if you remember the math, you know, you do multiply both sides by R or divide by U, and you end up with the inverse. So what this really means is this number is the time rate of heat flow per unit area and unit temperature difference. Let me say this another way. If I have 1 square foot of window that has a 0.35 U factor, and I have 1 degree temperature difference between inside and outside, 1 BTU will flow through that 1 square foot every hour. So if I have 1 square foot of window and I have 10 degrees difference between inside and outside, if I said 1 BTU, I should have said 0.35 BTUs will flow through it, because that's the U factor. So 1 BTU difference, 0.35 BTUs will flow through the square foot. If it was 10 degrees difference, it'll be 10 times that much, or 3.5. And if it's 100 degrees difference in temperature, then we'd have 35 BTUs flow through it.
Does the frame affect any of those numbers or anything?
The frame of the window is averaged into that number. So if you have a 5-foot square window, you're actually going to have a lower U for the glass and a higher U for the frame. And the manufacturer, when they generate this label, take into account all the frame. So if this was an aluminum window, that number would be higher. If it was aluminum without any thermal break in it, that number would be really high. It'd be close to 1. If it has thermal breaks in the aluminum frame windows, then it'll get down there, but it won't get down much below 0.35. So be careful when if you're designing with aluminum frame windows, if you're the HVAC guy and you're seeing aluminum frame windows going in, or if you're the inspector and aluminum frame windows in there, because that number sometimes is really hard to comply with on the residential energy code. So what this really says is I can take any square foot of the thermal envelope, whether it's wall, ceiling, window, door, whatever it is. If I know the U factor of that square foot, and if I know the temperature difference that we're designing for, the difference between inside and outside, I take the U factor, I multiply it by the area, whether it's 1 square foot or 10 square feet, and multiply it by the temperature difference, and I know how many BTUs are going to go through every square foot of the building. That's what a load calculation is. It's an analysis that looks at every square foot of the building and identifies how many BTUs will go through every square foot based on the temperature difference. So U factor, or R, and temperature difference are the two factors that control the heat flow. Solar heat gain coefficient, we already talked a little bit about that. That number, 0.32, says that 32% of the heat, of radiant heat available in the sun's rays, will pass through this window, which means 68% of the heat that's available in the sun's infrared rays is going to be reflected back out. So if you have a low solar heat gain coefficient, we get less heat in its form of radiant heat. Insulated glass units, IGUs, that's what we see in these windows. They're 2 panes of glass. They're manufactured with the spacer and sealer, and they put them in the aluminum frames. The IGUs will have really good U factors because they don't have a lot of frame that has a lot of conduction. And we'll get a number for them that might be like 0.26 or something like that for a good quality IGU. But other things, let's consider glass all by itself. 1/4 inch glass, 1 pane of 1/4 inch glass all by itself has an R value of 0.046, which isn't very good. In fact, the U factor for that would be the U factor for 1 single pane of 1/4 inch glass is 21. So instead of 0.35 BTUs going through that window for every degree of Fahrenheit temperature difference, we have 21 BTUs. So if you have a big temperature difference and just a single pane of glass, we have a lot of heat flowing through that single pane of glass. We put air spaces in there and we drastically improve it. We put films on the glass and we drastically improve it. That's why on old houses that have single pane glass, if you sit anywhere near the window, you swear that there's holes all over in it, right? You felt the drafts, haven't you? And it's that air that's against the glass is cooling, it's dropping down and it's doing this, and we're just circulating like this all the time. And it's a huge, drafty, uncomfortable feeling, and it's because the windows suck. 1/2 inch glass is twice as good. Inch glass, twice as good again. The air spaces is almost R1. The films add some more. So glass is a weak link. We need to make sure our glass we know what glass we're putting in, and we calculate our loads. We design our buildings based on the glass. Now, if we have cheap, crappy glass, what also is it going to add to our problems with our building? Water, right? Because it just pours down the window, correct? And we've seen that. We've seen it a lot. In fact, good windows, because they're only R3 or R4, have a lot of condensation issues if you have high humidity in your house. I want to back up and just talk one more thing about this. So if U equals 1 over R and R equals 1 over U, if I have a 0.33 window, So I take 1 divided by 0.33. What do I get? No? 3, isn't it? 1 divided by 0.33 is 3. So a good if that window is 0.33, that's 3.5, so it's a little bit less than 3. It's like a 2.89 or 2.9 window. So a good window has an R value around 3. A really good window, triple glazed, everything, has an R value around 5. Are those great R values? No, they suck, don't they? They're kind of crappy. But it's a whole lot better than the R value we had right here. Is R3 a whole lot better than that? A whole lot better than any of these? But even at R3, if it's really cold outside, we're going to get moisture condensing on our windows. We have, some of my windows have I can't remember what my wife calls them, but they're a cloth blind. There's no slats or anything. And when you drop, and they fit pretty good in there, she made them, and you drop them down at night, and they fit fairly well in that window opening, so they act as insulation. So they're closed at night, it gets cold outside at night, and what do we have? We have an airspace in there that actually allows the window to get colder because we have that buffer that's stopping the heat from the house getting to the glass. It's slowing down the heat getting to the glass. And so this temperature inside that space is even a little bit cooler. The glass gets colder, and I pull the blinds up in the morning, and what do I have on the glass? I have condensate on the glass. Now they're good Milgard windows, they're 0.30 windows, but it's still, with an R of only 3.2 or 3, I get condensation on it. If I have a lot of it and it's running down, what do I have? I have damage. I have water damage.
They make those with a blind right inside the window.
Yeah, they do put blinds inside the IGUs.
I put 5-inch plantation shutters on mine. So you close them at night before you go to bed in the winter. The room stays warm. You open up in the morning, you just feel the
cold.
blast through.
Yeah, he has 5-inch plantation shutters, and he closes them at night, and it's closing a shutter. It's adding, what you're doing is you're improving the overall R value at that opening from whatever the window is, adding another airspace, adding some thickness of wood, and yeah, you have some air leakage and stuff, but you're still improving the R value. Old houses years ago had shutters. One of the reasons is to keep the house warmer. So, we want great big windows, we want all these things, and natural light, I love natural light. I could never live in Alaska in the wintertime where it's dark all the time. It's kind of nice in the summertime when it's light all the time. But if we understand this, then maybe we're going to be a little bit more careful in the products we select for our buildings. So how do we calculate the R value of a wall? And we're just going to spend a minute on this, but this helps us understand heat flow. Here's an R11 insulated wall. And the first thing I'm going to talk about are air films. We have an air film that gives us a little bit of R value that kind of clings to the surface of a wall. And people say, what do you mean? What are you talking about? And let me describe it to this. If I have some woodworking tools in my garage, and if I open my garage and take my compressor and blow the dust out and it settles on my wife's car, and I take the air compressor and blow off the car, it doesn't all come off. It'll leave a little film on the car. There's an air film that clings to it. I can go out and drive at 100 miles an hour, and it stays there. You can write your name in it, in the dust on the wing of an airplane, and go up and travel at 200 miles an hour, and it stays there. There's an air film that clings to every surface. And that air film gives us some benefit. It gives us a little bit of R value. And we actually account for it when we calculate the heat flow through a wall. And so we have an outside air film that we have about a 0.17 R value, and we have an inside air film that we have an overall average 0.68 R value. And the reason that the outside is less is because we have more air movement on the outside than we do the inside. So it tends to thin the film down a little bit.
That would be dependent on what you were using for finished material on the outside.
It really doesn't change much depending on what the finish is. Now, some of the finished materials might have some air spaces in there that could maybe make an impact.
You got the 1 inch on the masonry.
Well, that's a different, the 1 inch on the between the masonry and the wall is a different thing. And yeah, you could account for that in this calculation. And we do account for it in tables. But I'm just talking about the outside surface and the inside surface. And this is the simplest wall assembly. And so let's finish that calculation. So we have these two air films. When you take that air film and add it to to glass, it actually helps improve the performance of the glass a little bit, quite a bit. In fact, you get more from the air films than you do the glass itself. Siding material. Let's say it's a 0.105 R value. The insulation is 11. The drywall on the other side is a 0.68. The inside air film is a 0.68. Total R value of that wall is 13.58. So if I have this wall was a 2x4 wood wall with no windows in it, would I have an overall R value of 13.58? I'm going to say no. And the reason I'm going to say no is because I have studs in the wall. And the studs in the wall have an R value of what? 3.5. So part of the wall is R 13.58, and part of the wall is where the stud is. So that if we had a stud right here, it would be R 3.5 here, and then the rest of the numbers. And so when we average in the studs, we average in top plates, we average in sills, we average in all those things, then we're going to end up with an R value that's somewhere less than that. But that's okay if we understand the science and we do that. So what happens if we do metal studs? Then the R value goes down. And it goes down so much that in the wintertime, if we don't do something on the outside, and air spaces help, and foam helps, and lots of things. If we don't do something on the outside, and we're in a really cold climate, or we have a real low temperature, what are we going to have on the inside surface where the stud is? We're going to have condensate on our walls. You don't need a thermal camera to see that. You'll see the moisture streaks on the wall. And over time, they'll be visible, and they'll be showing up all the time. The comment was his closet got so cold, it didn't. And you get ice and moisture, and clothes got wet, and it caused a lot of damage. It's building science.
I just have brick, an air gap, and drywall, and that's it.
Yep.
My house is a whole.
Brick, drywall, and an air gap.
Church
Yep.
built tons of those Atlas brick buildings. Those were the goat.
Yeah, all the Atlas built brick buildings, houses.
Or the zone light down there, it's got all those webs and grout, you know what I
Yeah.
mean?
Yeah, that's a good point. We have CMU block or Atlas block or whatever, and we pour a little bit of zone light, or we even spray foam in them and stuff. And some of the block people will say, you're going to have a really good wall if you insulate it. Well, how much of the wall is insulated? And how much thermal bridging do you have all the way around with every web in the block that has no insulation? And so concrete has like 0.09 R value per inch or something like that. Yeah, you pour bond beams. And what do we do to our CMU masonry products now? We grout them heavily. And if you go to any table, go to your ASHRAE tables, and they talk about how much grouting, how much reinforcing do you have in your wall. And by the time you put openings and everything in those, you're way beyond 50% grouted on most of your buildings now when you build them with CMU and stuff. So what are we seeing now on buildings? We're finally seeing lots of exterior foam on our commercial buildings, aren't we? Because the materials they use, remember we talked about materials right at first? The materials they're using on the buildings have poor R values. And so they don't work. They're just too cold. You have too much water issue. You have all these different issues. And so we're seeing the big thing, and it's going to become bigger and bigger and bigger, and that's what we call CI, continuous insulation, because it solves so many problems, and you're going to see this as we go a little bit deeper. And it all ties back to the building science of moving heat, the heat flow, the airflow, and the moisture flow. Heat loss calculations. As I said, the heat loss, we take the area times the temperature difference and divide it by the R, or simply area times delta T times the U factor. So if you have bought all new windows in your house and you had the stickers on every window and you went and measured how big each window was, we could tell you exactly how much heat you're losing through those windows. So if, for an example, you have a 1,500 square foot house that has 300 square foot of glass, and that's not an unreasonable number. Maybe some will have a little less, some will have a little bit more. You have 300 square foot of glass, and it has a U factor of 0.3, and your temperature difference you're designing for is 10 degrees outside, 70 degrees inside, so 60 degrees. 300 times 60 times 0.3 is 5,400 BTUs. What if you had single pane aluminum frame windows that had a U factor of 1.2? That number would be 4 times that number, which is 21,600. So 21,600 BTUs going through your windows versus 5,400 BTUs going through your windows. When you close your shutters or something like that, you're dropping this number to smaller. You're increasing the R value, reducing the U for that period of time that it's closed, and it's good. Back when I was growing up, windows were crappy, and so what did everybody have? Heavy blinds. You know, it's not until we started improving our windows that people wanted levelers and shutters and all that stuff, because it was so cold that you wanted to basically hang a blanket over your window so that you didn't lose so much heat through it.
Log cabins didn't have any windows.
Most log cabins and stuff didn't have any windows, because, well, what do you put in them? A piece of oiled paper or something like that?
Wasn't that what you was raised in?
Pretty close. Yeah, we got electricity when I was 3 years old. I'm not that old. I'm just experienced. Any question on that? Pretty straightforward when you really think about it. But the windows make a big difference. A house with a lot of glass is going to have a higher heat loss. A house with less glass is going to have less heat loss. So our load calculation, we just look at every component of the thermal envelope. We look at how much we lose through the walls, through the roof, through the windows, through the doors, through the ground or the slab edge. Let's talk a little bit about poor insulation procedures. I remember real well the first time I failed an insulation inspection because the builder freaked out How could you fail an insulation inspection? No one fails an insulation inspection. Do we fail insulation inspections? I hope so, because insulation is probably one of those things that is done wrong so often, and it has a large impact on the building. You take that thermal camera, and I probably ought to just put a whole slew of pictures in there. I've gone out and looked at houses for friends before they bought them, and they have a cathedral ceiling that's just rafters in an older house, and you shine the camera around, and there's a strip of insulation that's missing. Been missing for 30 or 40 years. 2 foot wide by the whole length of the ceiling there, and there's a piece of insulation missing. You know, I went and up to one of the well-known architecture firms that's focusing on energy efficiency, and they had done a remodel on an existing building, done some wonderful things to it, and we went through and we found a couple of defects simply because we could see where the heat loss was great. And so all these little things that get ignored make a difference. What?
I've been doing lately, putting an inch of urethane.
Okay, an inch of urethane is something they do. A lot of houses doing net and blow now. A lot of houses are doing some things that are really good. I'll admit it, I'm going to kind of bash batt insulation right now. Batt insulation, to install it correctly, is very labor intensive, and in fact, if we required it to be installed the way it's supposed to be installed, everybody would probably give up and say, you know what, we're just going to net and blow the thing because it's same cost. Does the code say anything about manufacturer's installation instructions? All the time. In fact, I think I did a search on it. I have digital codes and put in manufacturer's installation instructions, and it was more than 100 references to it. Maybe it was 200 something through all the codes. So the code relies heavily on manufacturer's installation instructions. In fact, it has to, because the code can't address everything that the manufacturer might want. And so if you pull up insulation manufacturer, CertainTeed, whatever company you want to, and look at their batt installation instructions, it will tell you to split the insulation for wires and for pipes, to cut around the boxes, to fit a little piece of insulation behind the boxes, and they don't want any airspace. They want it flush, tight against the back of the sheathing. They want it fluffed up and in full contact with the drywall. And when you do that and you take the air spaces out, the open air spaces, the insulation works at its full rated value. If they aren't doing that, the insulation is not working at its full rated value.
How much can you smash?
You can't smash it any. They tell you don't smash it any. No more than a ½ inch at the most. But what do we have here? If you can see this piece and this piece, that one not as much, but these two were probably 6 or 7 inches longer than they were supposed to be. And so what they do, they kind of tucked it under and packed it up in there, which creates a bunch of airspace in here, a bunch of airspace in here, airspace in there. That's a crappy insulation job. It really is. It should be nice and pretty and flush right with the face of the framing. Here it is, tucked in behind the wires. Is that manufacturer's installation instructions? Does it fit the requirements of table 402.4.1.1 or whatever it is in the code that you're supposed to follow? No, it doesn't, because it says you're supposed to cut and fit it around everything. How about this one? That was my house when I pulled the drywall off. They just tucked it behind the box. So it's crushed behind the box, reducing the R value, and then this area here is just open air, which actually allows what? It allows air to move through it. When air is moving around, it moves through the insulation. It reduces the R value. And the little strip here was missing.
We did a bunch of houses up at the mouth of the canyon, they squirted this crazy tacky blue stuff between every stud and around every corner, everywhere. That would even adhere to the drywall and close the
Okay.
envelope up.
He mentioned that he did a house that they sprayed this little tacky blue. They formed a gasket.
Yeah, you remember that stuff? Garbett ones. Yeah.
Yep, and they sprayed that a lot. And what that is, it's not so much an insulation, is that it seals the drywall through the framing. And we'll talk.
Between the studs and everything.
Yeah, and we'll talk about that a little bit more here in a little bit. You know, these are little things, but they're kind of big things. What does a new home cost today in your jurisdiction? Minimum 500 grand. Isn't that almost the case? I live in South Jordan, and there's a little older house. My buddy Daryl, he moved into a care center. His wife died, and so they put the house up for sale. It's a 3-bedroom brick rambler built in, I think, the late 60s, early 70s. And they've gone through and they've made it nice. It's maybe 1,400 square feet. It doesn't have a beautiful yard. $470,000 they're trying to sell that house for.
California people are jacking
Yeah.
the price up.
Oh, California, that house, my son is in a house in California that's smaller and older, and he rents it for $3,600 a month. So people buy a new house today and they're spending $400,000 to $500,000. Maybe they get one in the threes if they go out further, and it's not. But if it's in this valley, it's really tough to get one, a new house for under $350,000. At $350,000, do they maybe at least deserve a house that's somewhat energy efficient? I kind of think they do. You know, my grandkids buying houses I could have grandkids buying houses in 10, 15 years. What kind of money are they going to have to pay for a house? And if they buy a house that was built in 2020 that's a POS, because we weren't vigilant in how we built the house, that's kind of sad.
Materials went up about doubled the last 3 or 4
Yeah,
months.
everything's up.
How do you eat the cost?
Materials, labor, everything's up. You know what I mean? And really, I installed HVAC systems for 33 years, and yeah, we spent a little bit extra effort in doing it right, but the extra effort meant what? I didn't have problems. I didn't have problems with my systems. They worked. If you put a little bit extra effort and you just make sure the subs do it right. In fact, I've had many builders tell me, I'm not paying any extra for them to do it right. I expect them to do it right. So it really doesn't cost any more, and in fact, it's cheaper in the long run if we do it right, because the little things all add up, and then we have a house that is more energy efficient and doesn't have the water problems and doesn't have the other issues. So it's really important that we understand the science, we understand what happens when we do some of these things. Now, my house all had this yellow insulation, and I've literally torn all the sheetrock off the main floor and a lot of the upper floor, and a lot of the insulation was black. And that's because it was an air filter, right? All the air that leaked in and out of the house would catch the dirt as the air flowed in and out of the house.
Is that black one there yours?
This one's mine. And this one isn't too bad. I mean, there's a little discoloration there, but there's other spots that it was just black.
Not that upper one, is it?
No, this is a new construction. So we have all these issues with the insulation installation, and compression reduces R value. if it's misaligned, we have air spaces that allow those convective flows. Remember we talked about this? If we have air gaps in there and it's not fit tight, we have much exaggerated airflows in those spaces. And it's failing to cut and fit it right. Pressure imbalances, because we get these flows, we get pressure imbalances, and we have air moving in and out of our walls. And when we suck air into our walls, we are creating a potential for a problem. Let's take a 10-minute break. Oh, did they go to get some break stuff?
Yeah, keep going for a few more minutes.
Okay, we'll wait.
Okay, thank you.
Thanks, Britt. Net and blow insulation. I don't own one of these companies. I don't have stock in one of these companies. I don't care one way or another, other than it's a great product. It costs a little bit more, but it probably doesn't cost that much more than if you required the bat insulation to be installed correctly.
I used to like that cellulose, but I haven't seen it around much.
Well, cellulose has some problems. The fiberglass gives you more R value. This packed in, tightly packed in, it gives you an R24 in a 2x6 wall.
Cellulose was like quiet.
Yeah.
Like,
Yeah. Well, this is quiet too. You know, spray foam, an inch of foam is quiet. If you put continuous insulation on the outside, it's quiet. You put in good windows, it's quiet. But what's the beauty of doing this versus bats? What do we have right here? Can you see? No, this is ladder blocking. So we have ladder blocking. Here's an outside wall, here's an interior wall, and rather than put all these studs in there that make it hard to insulate, they just put, you know, this one's at 4 foot, this one's at 2 foot, so that you have something for the sheetrocker to nail to. If this was a bat insulation job, they would shove the bat behind it, and that'd be done. So what's happened here, we have the 1.5 inch of thickness that's reduced, but we have full insulation around it, and it's completely naturally filled around it.
You ever seen use the recycled jeans and they run through a shredder?
Using what?
Recycled Levi's.
Oh, the recycled Levi's? Yeah,
They run them through a shredder, so it's tiny.
Yeah.
pieces, and that blow them just like that.
yeah, yeah. Yeah, there's other materials, and they all rely on, what do they rely on? They rely on the air, the stagnant air that's sitting in there, that works well if the air isn't moving. Remember the jacket? If we have the windbreaker on and the air is sitting motionless within that lining of whatever it is, we're much warmer. It's even year, 2020, and I missed my Alaska trip because I go every other year, and I missed it this year because of the virus. But you get up in the morning and it's 40 or 45 degrees, and you're heading out in the fishing boats across the water, and guess what? It's cold. And so what do? You put on 3 or 4 layers, and what's your last layer? That windbreak. Without the windbreak, you'd freeze to death, but with the windbreak, you're warm because the air is not moving through the layers, and every layer you put on creates another little layer of air in between the layers. So much warmer than just the one big coat. This is a great insulation job, but if we don't do the air sealing to stop the air from moving through it, then we have a problem. So any material that we can create some air, little tiny air spaces that sit there and act as part of our insulation. We know that airspace works because we do what? We put it in our glass. We put it between 2 layers of glass, and it works really well. So, great way to insulate wall cavities. You know, it's fully insulated behind that intersecting wall. We don't have any voids. It fits around wires, pipes, boxes. You're not trying to cut and split and fit it around it. It fills around all of them. There's no air spaces for that convective flow. If we have the air barrier here and everything's all enclosed on all 6 sides by the time we drywall, then we have that static air sitting inside that space. typically higher R value than bats. With bats, I don't think you can get any higher than R21 with a bat in a tube of 6, and this you get about an R24. So the effects of the heat flow on our building. I'm going to say the number one is the health and safety. Even though people say that energy code doesn't have anything to do with health and safety, it has a lot to do with health and safety. Mold and mildew, where we have mold and mildew where we have moisture carried into the heat flow, in heat flow contacting surfaces. So if we move moisture into a wall cavity and we have a cold surface, we're going to have condensing. Comfort. Cold walls, windows create a circulating draft.
That mold you had in that one in 50th Market,
I got pictures in here.
you got pictures of it?
I have pictures in here. Absolutely.
You inspected it, man.
Huh? I know who inspected it. Yeah, I know this guy had it. There's an issue with, and I'm not going to name any names, but there was an issue. I got called out to consult on it that had mold in a crawl space, and the comment made something like, "I'm too old to crawl in crawl spaces." I can't believe he said it, but you know, someone might have said that. You know this is being recorded, don't you? Building durability. That's a big one. I mean, I had scaffolding up the outside of my house for a long time. 2 stories, my basement's half out of the ground, and so I had a lot of scaffold up to tear all the siding off all the way up and to address the rot in every corner of the windows. Energy efficiency, heat loss and heat gain, total area not insulated or improperly insulated. So we talked about the air, how big of a hole do we want in our house to leak air? How much do you want, how much area do you want that's not insulated? I don't want any that's not insulated, do you? Zero. You know, I don't know how many times someone complained to me because they do a remodel and they open up part of the kitchen wall for the plumbing and electrical, and I says, great, insulate it. Well, it's just a little bit. The rest of the house isn't insulated, so insulate it. Anything we can do to reduce the heat flow through the wall cavity is a bonus. You reduce the energy bill on a house built today by $10 a month. What happens as energy gets more expensive and everything? What happens over the life of the home? How many thousands and thousands of dollars is saved by doing those things right? I would love to not have an energy bill. And I'll be honest with you, I use a lot of energy, you know. I have a garage that's poorly insulated that I heat in the winter so I can work out there. I have power tools and a big compressor with a 5-horse motor and all this stuff. And so I use some energy. So anything I can do to reduce my energy consumption is a bonus for me because I don't want to pay a lot of money for it. I want to reduce it as much as I can. And if we're just saving money and we're burning less fuel, we're consuming less energy, there's no real negative about it. Insulation issues. This is, if I look out my front house, my front door, there's a little new lane circle that's across the street from me. This kind of curves over into a little circle. But this is the house that I see out my front door. And what's this 2 melted spots? It's 2 supply air boots where the heat cooling blows there in the master bedroom. Now, while it's snowing, there's enough heat coming through that the snow never sticks and it just melts off immediately. Because you can see it's collecting some snow. The furnace is in the attic over in this area, which is obvious because why? Because we're melting snow. Now, when when Morgan pays his gas bill, do you think he knows that part of his gas bill is going to melt snow on his roof? And the rest of the time, when it's not snowy, he's trying to warm the outside through those spots, isn't he?
Where they install those furnaces, they don't get enough insulation.
There's not enough insulation. There's not. You know, it's a horrible location, and we'll talk some more about it. It's a horrible location to put it in the attic. Just terrible. I mean, just horrible. I have some ductwork in my attic, and as I've remodeled upstairs, I've been taking it out, and I've been creating soffits and stuff like that so that I can get my ductwork out of the attic. And I still have a little bit in there because I haven't done my master bedroom yet, but I'm getting it out of the attic because I don't want to throw money away. So, yeah, but you know what? That would have gone away if when they hooked the flex to the boot, if they'd put a little piece of R8 insulation over the boot, over the top of the boot, right? Now, I'll admit that I didn't require that for a lot of years, but my last 5 or 6 years, one of my inspection write-ups was ensure all exposed metal in the attic is insulated, including boots, return boxes, Ys, everything else. And I required them to be insulated for that very reason, that kind of stuff right there. Did they have to pay more for that? No, the builder isn't going to pay the contractor anymore because he's supposed to do it per code anyway, isn't he? So it doesn't really add to the cost of the house, and it means that next time they'll just do it while they're there. Here's a house. That's a nice one, isn't it? There's a whole section of roof there that's not insulated completely. I don't know what's inside. I was just driving by and had to take a picture. This strip you can't see as well, but there's a whole strip that goes all the way up, and then there's a partial strip right there. The insulation's missing. It takes a lot of heat to melt snow. There's a lot of heat going through there. You have to add a lot of BTUs to melt ice. Doesn't matter though, does it? Yeah, I think it does. Yeah, and that's not a cheap house. If you bought that house today, it would be that $600,000, $700,000 house. It's about 8 years old, I think it is. Okay, I talked to one of the builders to take some pictures for a class I did a little while ago, last May or June, and said, can I go walk through a few of your houses and take some pictures? And he says, sure. He says, let me know what you find. So I walk in the very first house, the drywaller had just barely finished. I mean, here's his corner bead stuff sitting in a box on the floor. It's all swept up, cleaned up. And I have a full width strip of insulation, and then I have a little cut piece, a little thin piece that would fit a small space sitting on the garage floor. Do you think it's extra? Everybody's saying no. It's some insulation that fell out, isn't it? Some insulation fell out, and everybody ignored it, done their job. They even swept up after they hung all the drywall and left the insulation that was left out sitting there on the floor. Here's one, different, this was taken before, but here's a piece of bat sitting on the floor, and there's a space up here that's missing the bat. Did anybody put it up before they drywalled? Did the inspector say, whoa, put all the insulation back? Yeah, I did. I said, make sure the insulation's all in place. If we leave that one piece out, what are we doing? We're creating a spot where the heat that's in the cavity flows into the garage. Because we have heat flow, we're going to have air movement, and we're going to have air moving around inside the furred down cavity. This really is kind of a crappy way to insulate ductwork. You know that's metal ductwork in there that hasn't been insulated. and they've insulated underneath it, and we go on, well, yeah, the ductwork is inside. We're kind of making it inside the envelope because we put the insulation underneath, right? What's the chances that there's a piece of insulation laying up against the face of that fur down? Is that about right? Probably 0.
What about on the opposite side, on the exterior wall?
I mean, back here? Yeah. And that's an exterior wall, or maybe it's the house wall. I don't know, but it's still an airspace. You're pointing out an important thing. Insulation is most effective without air spaces. We don't have these open air spaces. Why have they been saying for years and years and years, shove the insulation all the way up against the floor? Because we don't want that air space between the insulation and the conditioned space. We want that tight. We don't want those air spaces. Air spaces means we have air movement. And air movement means we have moisture movement. They don't look like anything, but they do amount to something. What if because of one of these issues, we end up with some damage, some rot, some water issues because we have a cold spot? Air barriers. And so that's really what it's all about, is air barriers. We have no air barrier on all sides of these insulation products. We just have them sitting in there. We don't have any insulation where the studs are, so we have strips where the metal duct's straight above it with no insulation. So we do need our air barriers behind this, non-flammable air barriers behind our tubs and showers. Any place we have the insulation, we got to have an air barrier. The code is very specific. The installation, the manufacturer's instructions are becoming more and more specific on this. Insulation, with the exception, well, it would make a difference, but it's just not practical. But all vertical insulation has to be enclosed on all 6 sides for it to be effective. If it's in a stud cavity, it has to be enclosed on both sides. We already talked about the knee walls, the bottom plate, the top plate, so you can't just throw studs up into going up above trusses without putting blocks in. The insulation needs to be completely enclosed with the windbreaker. And that's the key thing that we really got to keep in our mind. Do we have the windbreaker?
I think that fireplace is supposed to have a piece of cement going across the top.
The fireplace might have some other requirements, but that's what... As inspectors, is it a bad thing to ask for the installation instructions? No. It's a good thing. That's what we should be doing. We should be checking that stuff out. Ensure all the insulation is secure at installation inspection. Here's a piece that's fallen out. This is a concrete stem wall, and then they have a frame wall on top. And they actually did a good thing here. Here's the blanket below, and then they went up top and they put another piece of blanket up above so that it was uniform thickness, and we didn't create an airspace behind there because this is not as thick as the concrete. Yeah, that one needs comment? So a garage, ducts in garages, and here's a view of what we were looking at before and talking about with a little bit better view. So if they bat this, are they going to put insulation in here? Are they going to be able to get it on the other side? Are they going to really fill this cavity up so that it's full of insulation? They never fill them up, do they?
No, they'll throw some batting in there because it's in the garage. You got floor drains from bathrooms inside there and stuff like that. And they'll put some insulation in it, but gonna always go to the end either.
No.
They'll stop the beam across the garage door and leave the rest of it hanging.
Yeah, they just missed so many spots. Here's some panning, and you know the code without amendment wouldn't allow panning anymore, but it's panned, but they have upset it enough that you can get a little bit of insulation underneath it. So, is there a way to do this right? Should we be making them wrap those ducts first before we insulate them? What should we be doing? Are we ready, Brittany?
Yes.
Let's take a break. 10, 12. Let's try to get going at 10:30. All right, welcome back. Actually, Brittany, I'll announce when everybody's back in their seat. But we took a break where we were talking about ductwork in garages. And ductwork in garages we see a lot because we put so many bonus rooms above garages nowadays, or the upper floor goes over the garage, and so it's pretty common, and that's great. But how do we treat it? Now, if you'll notice this fur down, I have a 2x4 on the wall. These 2x4s are flat, and so we got 4 to 5, maybe even 6 inches underneath this duct. And just insulating what we can see really doesn't do a good job. We have possibly plumbing up above in here. We have pipes that are running out through. You see this 6 or 8 inch pipe running out, that one. How did they insulate around them? They don't insulate them around them very well. And here's what I believe is the best way to do it. And if they do this, if they have this situation and they do this, I consider that duct is really well insulated and generally inside the thermal envelope. They're not going to require any more insulation. And so they've done the same thing that I was touting before. They've netted it up and they've blown the cavities full of insulation. Now, how's this? That's going to fill around the sides. We're going to have insulation in here. We're going to have insulation in there. We're going to have it on the back side. Every place that we have a void, we're going to have insulation. And that's going to do a much more effective job. Completely encapsulates the ducts with a minimum R8 insulation, eliminates all the air spaces, maintains the required level of floor insulation above. The blown will generally work, the bats will not. We can't demand that someone do this, but it's certainly something that we can require that this duct to be fully insulated. And maybe that's going to be the best choice if they do that. Okay, let's talk a little bit more about the knee walls that we talked about in the past and earlier today. So this really isn't a knee wall, but it's a shift or a change in ceiling height. And so we have a house that has scissor trusses that go up and over, and they have chosen to fur down the ceilings out in these other areas behind and so that we have flat ceilings out here and then we have the cathedral ceiling here. And so they have put bats in here all the way around. It is missing something. It isn't solid blocked on top. You see that? So that really is not enclosed on 6 sides, but they have gone in and wrapped around the back side with an air barrier. The thing that's lacking is the air barrier on top. And so air can rise up and move up through the insulation and into the attic. If we're a builder and we're having our windows installed, we need to leave the stickers on that include the NFRC labels until they've been inspected. Now, a lot of these were missing, but maybe they were seen before they were removed. Still talking, we're focusing on heat flow, but we're going to tie it over a little bit into the airflow. And that's what we've done here. We're really talking about the heat flow through the insulation, but we have the airflow issue as we go up. Here we have a bay window that pokes out, and look at these little spaces. Too often those get ignored. They really need to be sprayed with foam when they're doing their foam package around the rest of it. Now there's something else with this slide that concerns me a little bit. And I actually talked to the builder about it, and he says, well, I'm going to talk to the framer about it because he doesn't want to be paying for all that lumber. But we see a whole pile of studs here, and I think there's 6 of them here and 5 of them up here. And I looked upstairs to see if there was a point load that was coming down, and there wasn't. And the plans didn't have anything on it that showed that we had some drag strut or something that had to hook in, or I couldn't find any reason why they had to have that many studs. So what's the R value there? It's R1 per inch, and we have lots of studs. Now this is one of the things that across the country we're finding that if they eliminate unnecessary lumber, that the savings is substantial, and that you have obviously a better thermal envelope. You can put full depth insulation in there. The code doesn't go so far as to say you can't have extra studs. You know, but what does it say? It says you need to frame your corners so you can insulate them. It needs to, if you have space in your headers, you need to insulate your headers. And maybe someday it will say something about that, but I would think the builder would want to do something about that. What does a 9 or 10 foot 2x6 cost? Like 10 bucks, 12 bucks. And if you have 3 extras in there, and if you do that in multiple places around the house, what are we going to have? We're going to have some issues there. So the little spaces on the corners. Here we have a 45-degree corner. And we know that there's that little air gap back in there, isn't there? And what's happening with the OSB on the outside? It's just kind of sitting there flopping, isn't it? So we have a good source of air leakage there. And if we're not tight down on the floor and those stud cavities aren't sealed up like this gentleman was talking about, Garbett putting the gasket stuff on it, and we have some air movement from this kitchen area up around the base and leaking out there, and we have moisture in the air, we have the potential for what? We have the potential for water to condense in there, and we have the potential for damage due to the water in there. Small spaces, they all make a difference. You can see the daylight in that little space there. This one's a 90-degree, but it's a tight space. Do we really need as much lumber as we're filling into those spaces? The structural engineer tells us what we need. Some of these are so tight that they need to drill a few holes so they can get their nozzle in and spray some foam in there. Remember we had the page where we talked about the compliance method, where we do the res check, or we do the prescriptive table, or we do the energy model, or we do the ERI path, or we do the Utah res check. Whatever the case, I'm going to suggest that for those of you doing an inspection, you maybe glance at the res check and see what they figured they were putting on the basement walls, see what they were figuring on the windows, and verify that that's accurate. I'm going to further say that the HVAC guy ought to occasionally check to see that they're insulating the building the way he calculated the load. And then I'm going to go to a real stretch, and I've actually had this conversation with one of the major architecture firms in Salt Lake here, and had a really interesting discussion on it, is that we need to have, and they admit they need to do a better job of identifying the thermal performance on the plans. Now, those of you that do plan review know that sometimes we have to search and search and search to find what window is supposed to be in there, or what the R value is supposed to be. And most of the time it's not on the plans. It's on the res check. But the number on the res check is different on the load calculations. And so my point being is we need to make sure the plans include accurate information that matches the res check, that matches the load calculation. We're asking an HVAC guy to design an HVAC system that's going to work. But if he has the wrong U factor for the windows, or if he has the wrong insulation value for the walls, how can he design the system properly? He can't, can he? Is that the blanket insulation that is spec'd on the plans? Now, perhaps it would be good to talk for just a second about why we are insulating the walls of our basements. Why don't we just insulate the floor and have the thermal envelope go across the basement ceiling? Anybody venture a comment on that? What happened on this is, and I remember quite a few of them when we were still installing HVAC systems, that the decision was, we'll insulate the walls and everything upstairs, and then we'll insulate the floor. And so our thermal envelope is the main floor, or the basement ceiling, which means the basement is what? Entirely outside the thermal envelope, correct? So if we're creating a thermal envelope that runs across the basement ceiling, what things do we have to worry about? Insulate the ducts. We have to insulate all the ducts. We have water lines that are in an unconditioned space. Now it's probably not going to get that cold down there. Do we have stairs going down in the basement? And do we insulate underneath the stringers? Do we put an exterior door at the bottom with a threshold and a weather seal, a gasket and everything on it? Here's our furnace and water heater and everything sitting down there. Now, if there's a positive to it, is the combustion air duct isn't inside the thermal envelope anymore. It's sitting in the basement with the rest of the furnace. But it's really, there's a lot of problems with that. And then anytime someone comes in after the insulation to pull phone wires or whatever the case, the insulation is pulled down and it's uncomfortable, it's messy. The kids play down there after someone moves in the house and they got all this fiber and crap that's loose in the basement. So it's really kind of it's really a bad design. I hated it. I mean, I really did. And I always liked it when they started blanketing the walls. Well, probably about 10 years ago, Department of Energy had a study that they wanted to verify or try to figure out how to measure energy code compliance. And so we had 6 or 7 jurisdictions in the Salt Lake area volunteer to have an expert come in and look at plans and look at homes that were being built. And Shauna Mazinga, who is from Colorado, she worked with Steve Thomas, she came out and she was inspecting homes. And we had, at that point, we had started blanketing the walls, and she said, if the walls are blanketed, we've created a conditioned space down below, but we need to condition it, which meant, she says, I think we should put supplies and returns. And I said, well, I don't think so, Shauna. And so we debated it back and forth. And I went to ASHRAE, and ASHRAE has, in 90.1, ASHRAE has a section that talks about conditioned spaces, and then it talks about indirectly conditioned spaces. And so I'm assuming these are closets on either side of this room. And inside that closet, there's no supply and return, right? but it's inside the thermal envelope because we're insulated back on that back wall. Should we add a supply and return? No, we shouldn't, because that space is actually being indirectly conditioned because it has what? It has a heated space on this side, it has a heated space on the other side, and it's being conditioned indirectly. And our discussion, and we agreed that when we blanket a basement, we don't insulate the floor above, we've created a thermal envelope that goes down to the basement floor, and it's being indirectly conditioned from above, and we don't need to add supplies and returns. So what did we do? We changed the definition in the code for conditioned space to include indirectly conditioned spaces. And so if you go to your code and you look up conditioned space, you'll see that it changed, I think, in either 2012, where we said indirectly. So I bring it up because I get the calls every so often that, well, they have a space, a storage room that's inside the thermal envelope, it's insulated against the wall. Should I make them put a supply in it? No, we don't need to make them put a supply in it. If it's not habitable space, they don't need a supply in it. It's indirectly conditioned. The key and the important thing is if we want a building to function properly, we want to create the most complete and simplest thermal envelope and not have a bunch of jogs or crazy difficult areas to insulate. Cantilevers. This one I really, really have a lot of problems with, and we do have a lot of challenges with these. That same house I'm in right now that I bought in 2005, I bought it in August, and right about this time of year, got up one morning, walked downstairs, walked across the hardwood floor between the kitchen and going into the family room, barefoot, and the floor was really cold for about 8-10 feet right across the family room there. And that cold spot was directly in line with the bay window. Now that night it had turned cold and the wind was blowing from the south. And so we had this cold wind blowing up in through the soffit of my cantilever for my bay window and across my floor. Across my basement to a storage room on the other side. Went downstairs and you could actually feel the cold air coming out of the joists and spilling down onto me where I was standing down there below. The issue was I had a bay cantilever like this, and what do you think was installed on the bottom of the cantilever? Aluminum soffit. How airtight is aluminum soffit in J-metal? Almost none, right? I mean, it doesn't fit real tight. They cut it a ½ inch short so it fits in the J-metal and it's not hard to get in there. The whole thing was something that I didn't recognize. I was an inspector then. I'd been an inspector for 6-8 months. I'd been a mechanical guy. I'd never really paid attention to it. I'd stuck a lot of supply airs out in those bays and never really given it a lot of thought. So this is the house, or this is a group of houses, and in this group of houses, they're doing all that net and blow insulation. But this cantilever, they've chosen to shove bats in it. And I think that's, a decision the insulation contractor decided, and he's done it on this one, and this one's a fireplace cantilever. He's done the same thing there. And they have, it looks like, created a space that they can nail a piece of OSB on it after. So just first glance looking at it, we have a lot of gaps in the insulation. There is a duct above this one. We have a rim joist out here See this insulation here? Do you think we have full insulation for this rim joist? Probably not. They didn't even put any in. Yeah. Yeah. So we have the potential for a lot of places that aren't insulated, don't we? And we have a potential for a lot of air gaps. So we got a view of that. Let's go inside. So here's that cantilever, and then there is that supply air going out, and there is a piece of insulation underneath it. And I don't know how thick that insulation was, but I'm pretty sure that there was probably a couple inches of airspace above it. We have that uninsulated rim, so we have potential for quite a bit of air movement in there because it's not a fully insulated space. Then we have the gaps between the blocks. Of course, that block's gone, but we have the gaps. And then we have what's here. We have all those places where they notched that block for the foundation bolt. Now, they do this all over the house, but it's usually covered with OSB, isn't it? When they cover the rim, they put the OSB over those, they lap over that joint and down on the rim joist. So we have all those gaps. You can't really see them here, but they are up in there. So hopefully we can seal it up pretty good here, but even if we do seal it up good, we don't have a good insulation job in there. And we have this wide open space above, and we probably have wide open spaces where you can see insulation here, and then it looks like we don't have any insulation up higher. So this is really a poor insulation job and a potential for some issues there. Is there a minimum of R8 under this duct? I don't think so, because the duct is compressed. The insulation is compressed. So we have some issues there. I can almost guarantee you that that rim isn't insulated properly. Is there a true R30 there, or they traded off the value of that cavity insulation against something else? I'm pretty sure it probably was put in the res check at R30, but I don't think we have R30 in there. And I'm of the opinion that probably net and blow would probably be the only way that really would work there. Now, why didn't they do a net and blow? It's because it's going to take quite a bit more effort for that little space, because what would they have to do? They have to come in and seal all of these places, so when they blow it from outside underneath, it's not blowing into the basement and just spraying that extra insulation inside. You'd have to net around this, and you'd have to seal up all those little spaces to net and blow it. But it would be a good job. But yeah, I'm sure there's hundreds of thousands of little cantilevers that have nothing in them. Are you in the same house you were 10 or 15 years ago?
The front bedroom is either 1,000 degrees or 0.
Yeah.
And it faces west, and so we could figure it out. We tried everything so that I popped the stuff up.
Yeah. And the bedroom was hot or cold because you had a cantilever and no insulation in it. And was it a big overhang, or was it a bay?
8 feet by 4 feet, so it's pretty good size.
It was a big overhang. Yeah. Yeah, I remember when I had a house, and it was a beautiful house, and I thought we had done a beautiful job on it. And really nice people. It was up kind of by Pepperwood on the road that goes up the back side there. And they had this one room that was cold. And she called and says, I hate to bug you, but we have this one room that's cold. And I went out and looked it over, and I couldn't see anything wrong with it, but I could tell that the room was colder, and it was her little office room. And so I went out, I sent a guy out, and I said, I don't know what's going on with that thing. And I said, let's go out, and it was a nice hardwood floor and everything. I said, I don't want to add another run to it. Let's just had one 4x10 in it, and I said, let's change it from below to a 4x14 and run an 8-inch pipe instead of a 6-inch pipe. So I sent a guy out, and we did that. And she says, well, it's a little bit better, but it's really not like the rest of the house. And I said, so there's something else wrong. I said, that just can't be. I said, can I come out and look around a little bit more? So I went looking around, and it was a room that stuck out on the front of the house a little bit, so it just jogged out a little bit. The foundation jogged out, and it was about 8 or 10 feet. And then it had a little gable that came out, over that room. Beautiful home. And I crawl up in the attic, and guess what I found? That when they had overbuilt the roof coming out, they hadn't cut out the plywood that was on the trusses to get out into that little space. Am I making sense? It was just a roof overbuild that they hadn't cut out the plywood so that when the insulator come over, he would make sure he got some blown insulation in there over the ceiling of about 3/4 of the room. Now, I'd never even thought about that until that point. And so later on in my inspection career, I tried to notice those things. And when I was doing my rough inspection, if we had an overbuild, I'd alert them, you know what, we need to cut something out so when the insulator comes, we can insulate that overbuild. And that's what it was. They got the insulator out there, they cut it out, they insulated it, and
Other thing you gotta watch on those overbuilds is ventilation.
yeah, and the ventilation on the overbuild too. Are they being ventilated? So the whole thing is just something we need to be observing the details. And sometimes the details are a little bit bigger like that, but sometimes the details are they're little things that we just didn't catch, and the people aren't going to complain too much. They just figure, well, the room's a degree or two off. But if we just watch the details, if we paid attention to the science, it'd make a difference. So knowing what we do, if we have that, Carl, I'm sorry, I'm going to move, so you have to move that. I'll take you up on them. I probably ought to just throw all those away, huh? So I have this room that's sticking out on the front of this house, goes back into the house, and it has an overbuild coming out on it. And so we had this portion that was blocked off, and we had maybe, let's say, 12 feet by 12 feet of attic with no insulation. Now, if we put, you remember my formula for heat flow? No one's going to pull it off the top of their head, but our heat flow, Q, is going to be equal to our area times our delta T, our temperature difference, times our U factor. And so my area is 144. My delta T, let's call it 60. 10 degrees outside, 70 degrees inside. What do you think my U is for an uninsulated piece of sheetrock? Well, the R of sheetrock equals about 0.5. So what's the U equal? What's 1 divided by 0.5? Is that right? So we had a U of 2. So $144 times 60 times 2 Did I do that math right? That almost seems bigger than I expected, but it's probably right. 144 times 60 times 2. Yep, 17,280 BTUs. Now, it wasn't that cold, and maybe the attic wasn't that cold, but that's potentially what it is. So what's the heat loss if this is insulated to R38? What changes? Just this number right here, right? I take 1 divided by 38, and I get 0.026. So my U went from 2 to like 1/100th of what it was before. So those people that have an attic that has hardly any insulation or no insulation have an horrendous amount of heat loss through it. And yeah, some of those old homes that they didn't have any insulation, then they add it, all of a sudden you take all those BTUs away, they're melting snow, and you have some issues.
Oh, so I think caving in the roof.
Yeah, that's exactly right. So the roof caves in. 144 times 60 times 0.026. $227 BTUs versus 17,280 BTUs. We're 17,000 more BTUs of heat loss with an uninsulated attic than we are with the insulated attic. Is there a reason that I kind of say, you know what, we really need to make sure our insulation is done right. We need to make sure that we maximize the performance of the insulation because we make some big differences. When that HVAC guy says, I know I need a 120,000 BTU furnace because I put one in the same size house that was old and crappy insulated, well, of course, because we'll have a house nowadays that uses 1/5 or 1/10 of the heat because the insulation is better. So big numbers, incredibly big numbers. So important. Now, anything I've talked about today is nothing that big, but there are lots of little things that add up. And if it's 10% or 15% or 20%, that's a big thing. Would you like to save 20% on your utility bills every single month simply because your house was built a little bit better and they took a little bit more care? That's really what we're talking about for those people that are buying those houses. On this cantilever, I'm going to back up, the most critical piece is that we have an air barrier on that. We wrap the Tyvek down and we stop it right here. Do we make sure that this thing is sealed, whether it's caulked or gasketed or they sprayed this stuff, make sure it's sealed so we at least stop the airflow through there and give the insulation some ability to give some R value. Framing allowing insulation in the corners. Now, these are a little hard to see, but here's a corner and it just has the one stud back in there, and you can see that we have it so that you can insulate the corners. That's code. And the code is a minimum. So when it's blown, they just poke their hole and fill that thing full of insulation. I thought I'd throw this in just so you could see. You don't see a sticker like this very often. What's the U factor on this window? 0.21. How do they get a 0.21 window? 3 panes of glass. So there's a pane of glass here. There's actually another pane of glass there, and then another pane of glass there. So they've got 3 panes of glass, which gives you an R5 window.
They have much problem with those condensing inside those panes of glass.
The question is, do they have problems condensing inside the panes of glass? Whether it's double or triple, if they don't do a good job of sealing between the panes, they're going to get some condensation in there. I don't have any scientific studies on this, but my experience lately is generally it appears that the windows are sealed better now than they were in the past. I mean, 20 years ago, it was common to see the fogging and stuff inside the.
I had some double pane Pellas, and they had little vent holes down in the bottom.
Yeah, there's window technology's improved a lot, and I don't know how much they've improved on everything, but I can tell you that, in 2007 is when we first started really talking about enforcing an energy code, and that at that time required 0.35 windows, and 0.35 windows were a little bit challenging because the standard vinyl window with 2 panes of glass with low E coating ran around 0.35, 36, 37, maybe some 3/4s. But they were always right there around 0.35. And now when you go out and look at windows, we see all the time 0.28, 29, 30, 32, 33, and rarely have I seen a 3.5 window anymore. Remember, smaller numbers better, and so window technology is constantly improving. In fact, I was really surprised when I started seeing AMSCO make some double coat windows that, depending on the configuration of the window, they get down to the 0.26, 0.27 range. That's a pretty darn good window with 2 panes of glass. That's approaching R4 on the window, and so it makes a pretty good difference on it.
Brent, does a wood frame give you a better U value typically than a vinyl frame?
The question is, does wood frame give a better U than vinyl? Typically, no.
So I got a res check the other day and all the windows were 0.23. And so I asked him to verify it because that's lower than you typically see on your res check. And they came back and said that they're double pane wood frames and they're all 0.23 or better.
Okay, their comment was, she had a res check that they said the windows were 0.23, and they were wood framed double pane, correct?
Yep.
I highly doubt it.
Okay, that's what I
I highly doubt it.
Usually those that put metal cladding on the outside too.
Yeah, and metal cladding makes it worse, not better.
Yeah, right.
The reason I doubt that, Britt, is just the IGU, the 2 panes of glass that they seal together. If you go to PPG and the glass manufacturers that make them for the storefront windows, it's really, really tough to get the window, the insulated glass unit itself to get that low, let alone add a frame to it. So I would ask for specifications. And if you get specifications that show a double pane window that's 0.23 overall assembly U factor, please share it with me because I'd really like to see it. They might have the glass itself that has a COG center of glass that low, but
About the argon.
maybe I just.
So that's what I asked him. I said, please verify this is for the assembly, not the center of glass. And they came back and said, yeah, it's for the assembly. And then that's when they said that they were wood frame double pane, not vinyl. And I'm like, I still don't think you can get a 0.23.
Yeah, I mean maybe, but I try to stay away from it's impossible. I might say it's virtually close to impossible or something like that, because every so often someone shares something with me Well, I special ordered these windows from Sweden, and I ordered them, or Norway, and I paid $98,000 for my windows, and they're crazy performance windows. But they're usually 3 panes, and they have frames that are fiberglass that have closed cell polyurethane foam inside the cavities, and they've done all kinds of crazy things, and they do get them down there to where they're really, really great windows for $100,000 or more. So that's a great question, because I kind of don't think so. And it is something that we need to really think about. I mean, we have buildings, and I'm not trying to point fingers at anybody, but, and I'm glad you brought it up, Brittany, because this is building science right at the basis. We have what we call COG, the center of glass. And you take, they put in these frames, and then they send the measurements out, and they make the IGUs for all the openings. And they rate it right dead center in the middle of the glass. They rate the U factor at that point. And so they call it center of glass. And that's the very best performance in the whole IGU, because it's away from the frames and everything. And there are a lot of buildings, when we first started becoming concerned about energy code, that the architects didn't know, and they would call the glass people and say, what's the U factor on the glass? And they would give him 0.26, which is the IGU for the center of the glass of that unit. And then they go and put it in an aluminum frame that might have a thermal break, but might not have a thermal break. And if it doesn't have a thermal break, when you put that glass in that aluminum frame, the overall average U factor is like 0.78. So you put 0.26 in your calculations, your modeling calculations, and your windows actually perform 3 times worse because you have an aluminum frame and you have a giant building that's 27 stories high. Why do they allow 2 different types of numbers? That's a good question, and let me get to it. So we have buildings built in every major city that they thought their utilities were going to cost them X when they cost them Y, and it's because the glass was modeled wrong. And it's because, and I think that one has to be almost for sure a center of glass. Now the question here is, well, why do they even have this? How does this happen? Why don't we not allow them to give us the center of glass? And that's a great question, but it's one we got to think about here. And the code recognizes it, and I have been beating this one to, how long have I been beating this one up, Brittany? 10 years? At least 10 years, 12 years. And in fact, I did a lunch and learn, a short class on this, and it's on the Utah Energy Code website, where that's what I did. I talked about site-built windows, and it's an hour and a half long or something like that. And Carl recorded it for us. But how do, the issue is, these windows are what we call site-built windows. They put up the structure, they do the CMU or whatever, the masonry, they do the brick, they buy the frame from Kinnear or someone like that, and Kinnear buys the gasketing from someone, and then they go to PPG or someone and they order the IGUs that fit in the openings. And because they're site-built windows, there's not a factory that rated them. And they're all different sizes, and we have all these different things. And so what NFRC has done now is they have created a process where there's actually software and a database that you can take Kinnear's frames or someone else's frames and someone else's glass, and you can get a number out. And they make tables, Kinnear has a table, and I use them in that class. They have a table that says if you put .26 glass in their 451 frame that has no thermal break, it's going to be 0.7 whatever. But if you put it in 451T, which has a thermal break, then it's going to be 0.4 something. And if you put it in 451UT, which has double thermal breaks, then it's going to be even a better number. And that gives you an assembly rating. But you don't get the assembly rating until you combine all the components that come from different manufacturers. So it's a challenging thing, but I don't know how to.
Does that become standard?
Well, that's referenced in the code.
You know what I mean? That it has a piece that has built and then bring up a number, is that going to become standard?
Well, the standard or the requirement is, and this is something that those of you that do plans examination, is when you get that commercial plan in that has site-built windows, you need to ask for a bid report or some type of document up front where they tell you what type of frame, what type of glass, and everything is going to go into the project. And if they say, well, I don't know, I haven't decided yet, it's time to say, guess what? We have to make these decisions before we issue permit. And really, that's not being unreasonable. Or at least the specifications that the U factor for the whole assembly has to have some type of supporting documents. Now, Brittany did a great job on this plan review asking the question because she did what? She saw a number that doesn't make sense. And I'd like to take credit that maybe I taught you that number doesn't make sense, Brittany. And that's really one of the things, if we understand the building science and you think, wait a minute, Brent said that it's really hard to get anything better than 2.6 or 2.7 out of 2 panes of glass in a vinyl frame, and he said the aluminum frames are worse, then maybe it should raise some red flags as you're going along and you're looking at things. If nothing else, it should alert you to, I need to be looking for the labels, and if I'm reviewing a plan, I need to be making sure this decision's made up front. It's all of us that have worked as code officials, all of us that worked as contractors and subcontractors know that we get to a rough inspection or a final inspection and something's not just right, and what do? We make the best decision we can for the situation. I don't think any of us would get away with saying you have to tear $750,000 worth of glass out and change it because you're off by 5/100ths on your U factor. But if we catch it up front and we catch stuff as we're going through the process, we're better off. If we're inspecting slab-on-grade plumbing, or if we're doing slab-on-grade building and we're a builder, or if we're an architect and we're designing a house with slab-on-grade, there should be a flag that comes up immediately. I'm slab-on-grade. I need to have slab edge insulation. And if someone doesn't catch it and we get all done and the floor's poured and someone's out there for final inspection or rough inspection, and they're going, wait a minute, the plan didn't say, but the code requires slab edge insulation. Or the plan says prescriptive code, we're going to follow prescriptive table. Well, the prescriptive table says R10 slab edge insulation. And it's missing big weak link, cold basement floors or cold walkout basement floors. So it's, yeah, site-built windows are one of my, yeah, yeah, but it's an important thing, you know, it's really important. And it makes a huge difference. It makes differences not quite as much as no insulation, but it can be triple the heat loss or heat gain because we don't have the right number.
That stuff goes on all the time with fire doors.
It goes on all the time with all types of components in the building envelope. And I'm kind of excited because this architecture group, I'm going to be doing 2 classes for them next month. We're very open to talking about how that they could produce a plan that's not only easier to get through plan review, but ensures that their building gets built right. there's lots of litigation that goes on because buildings aren't built right. And you can do a lot of finger pointing, and there can be a lot of people that are guilty of, pieces of it. But ultimately, if the plan's right, we get a good building. If the plan's not right, we don't get a great building. I'm a little off subject, but I think it's important for me to share this, and I think it's because I learned the hard way. I can think of 3 or 4 jobs that I did as an HVAC contractor, and I'll admit I took the jobs, and they were big jobs, really big jobs, commercial jobs, and I took the jobs to keep my employees busy and to keep my overhead up. And the plans sucked. The plans were horrible. And guess what happens when the plans are horrible? The project is a can of worms all the way through the project. And those 4 jobs, I lost so much money because it was just a mess. It was stop, we'll go to the architect, we'll do RFPs, we'll do all this stuff, and then what does the standard architecture contract say? It's up to the subcontractor and the contractor to identify any weaknesses in the plans, and if you don't catch it, it's your fault. And so you end up eating them.
Did Ray inspect those?
The problem was I was sending crews, pulling crews off, sending crews, pulling crews off, making changes and everything else. And I would have been better off at the start of the project to get out my wallet or get out my checkbook and write them a check for $5,000 or $10,000 and say, go get someone else to do your job, your plans suck. Now, I wouldn't do that, but what I did learn is if I looked at the plans and it was a bad plan and I didn't have good information and I didn't know how they were going to insulate that building or how they were going to do things, I said, I'm not interested. And I left the plan with them, and I didn't do it. And so, yeah, I'm kind of, when I do plan reviews, I kind of beat them up on some stuff. Because why? Because I want them to get a good building, and I want everybody that works on the building to make some money, and I want the client to have a good building. So, good discussion. Let's talk a little bit more. We've talked about insulation. We're still talking about insulation and heat flow. This is my prediction that we are going to see more and more continuous foam installed on buildings. I think it's going to improve and increase over the next years. And at some point in time, we'll see it on almost all of our buildings in our cold climates. There's a lot of, not experimenting, but they're starting to do a little bit. They did some studies, and they're starting up in Alaska and northern Canada in wood frame structures, putting 4 and 6 inches of foam on the outside and not even insulating the cavity. Now, why would they want to do something like that? Because when you do multiple layers of foam on the outside, not only do you have real good insulation, but you have an incredible air barrier, right? Because you don't lay the layers right on top of each other. You stagger the seams so that we have continuous insulation, as we look through it. We have a good 3 or 4 thickness layer of insulation. Moisture can't move through it, air can't move through it, and we stop the heat flow. So we don't have heat flow, we don't have air flow, we don't have moisture flow through that. And we're using a product that isn't susceptible to moisture. No value in even insulating the cavity. Please.
Well, with that being said, as per manufacturer's installation instructions on insulation, they still have the air gap in the stud wall cavity on the inside between the drywall and the exterior.
Step up and say that so everybody can hear it out there. I'm not going to be able to repeat it all. Thanks, appreciate it.
Okay, so in regards to, you have your interior wall, But as per manufacturer's installation instructions on insulation, it requires not to have an air gap between your drywall and your insulation. But you have your insulation on the exterior and your stud cavity on the interior with no insulation in it. How does that work?
Okay, you're absolutely right. If we insulate in a cavity, we can't have an air gap, right? Well, that's what you're saying. If I insulate in a cavity, I can't have an air gap. So they can't put 6 inches of foam on the outside and then put 2 inches of foam in a 2x4 cavity. If they're going to put insulation in it, they need to put full 3.5 inch or 5.5 inch bat, depending on what the stud cavity is. However, the code doesn't require you to insulate the cavity. What the code requires you to have is a wall with a certain level of insulation. So the code doesn't say you have to put it in the cavity. It just says you need to have a certain amount of insulation. And when they put, let's just say, for example, 6 inches of foam, 6 inches of foam is a minimum of R30 up to R42, or even a little higher if they're using polyisocyanurate. So we're having someplace between an R30 and an R45 wall, and we don't even have to insulate the cavity to get it. And so, because there's no fiberglass in the cavity, it's just a cavity for wires and pipes and stuff like that, and it doesn't even have to serve a purpose for insulation. Now, it's easy to do it and it's cheap to do it, but they don't even insulate them. They just put it all on the outside. It's kind of like insulated concrete forms. You're familiar with those? The Lego blocks that you stack them up and you form full of concrete.
I did 2 houses like that.
Yeah.
Crazy.
Do they have a cavity? Can you build a wall with insulated concrete forms, and it's going to end up like 12 inches thick or 14 inches thick, depending on what you have, foam, concrete, and foam, and can I go inside and do a stud wall simply to run my wires and stuff through if I want to? Absolutely.
Some of those are just the forms and some of them are block.
Some are formed, some are block, yep. But I can create a cavity or a chase. Let's just call it a chase for my wires, and that's okay. So on this wood frame up in the northern parts of Canada and stuff, the wood frame is the structure, but it's no different than a steel structure that we put some type of wall outside the steel structure that is encloses the building, but the structure is held up by the steel inside. Does that answer the question? Yeah, yeah. If we have enough insulation on the outside, I mean, we can literally, in this case, it's 1 inch of, can't remember the brand. What's the pink one? Is that Certainteed? Maybe. Anyway, it's an R5, and that's a bonus. That's a good thing. But,
Styrofoam stuff.
yeah, it's extruded polystyrene.
But it's a little bit less than closed cell.
It is a closed cell, but it's different than polyiso. And it's different than spray closed cell.
It's an R7.
Yeah, for spray closed cell is R7. It's a little bit different product. That's not extruded. But that the road I'm trying to head down is trying to show you the advantages of foam on the exterior of a building. Now, those of you that are familiar with the prescriptive table and this little sheet I passed out, my little energy guide, we have just a little copy, a little piece of the prescriptive table. In climate zone 6 and up, moving forward, you'll notice on this one that it says, even for our climate zone 5, and maybe some of you are working climate zone 6, but in climate zones 3, 5, and 6, we have, and let's look at this real close. Climate zones 3 and 5, it says we can put R20 in a cavity or R13 in the cavity and R5 on the outside. When they say 13 plus 5, that means 13 in the cavity, 5 on the exterior, correct? So you can do either one. But when you get to climate zone 6, what does it say? It says 20 plus 5 or 13 plus 10. Both, if you go prescriptive table in climate zone 6, you have to have some continuous insulation. Same thing for climate zone 7, 8, and 8. So climate zone 6, 7, and 8, prescriptively, you absolutely have to have exterior insulation.
Yeah, we required that on all of them up in Jackson, that's.
Yeah.
Cited 7, climate zone
Yeah,
7.
up by Jackson where you work, yeah. Climate zone 6 or 7,
This 7.
they absolutely have to put it on. Now, if they don't do prescriptive and you do res check, you can, it's stupid, but you can get out of doing it. You really shouldn't do it, but you can get out of doing it. Why does the code mandate in those cold, cold climates that you absolutely have to have some continuous insulation on the exterior like that? Because it's so cold, we have our wall assembly, inside is warm, outside is cold. What's the surface temperature of the back side of our exterior OSB when it's 10 below 0 outside? 0, right? It's really cold. If you have a wall surface, a sheet of OSB, the back side of the exterior sheathing is 0 degrees or 10 degrees or whatever. What's going to happen if we get moisture in the air, moist air hitting that wall? It's going to condense, isn't it? Absolutely guaranteed it is going to get wet. And if it's cold all winter, it's going to be wet all winter. What happens if we start putting foam continuous on the outside? We raise the temperature of that surface where the moisture coming through the wall hits that backside of the OSB. And so the more foam we put on the outside, the warmer our temperature on that backside of that OSB, and so fewer chances for problems of condensate and stuff like that. So, yeah, EFIS. Great way to go. You put an EFIS system on it, and you put a couple inches of foam on there. Now the foam they use doesn't have quite, they use expanded polystyrene because it's easier to sand and stuff like that. And it has a little bit lower R value. I think it's like 3.5 or 4 per inch. But still, they put several inches on sometimes. And you can't even pay them to use what's called, they call it Atlas board. And it's a polyiso material that Atlas Roofing makes that gives you like R7 per inch or R7.5 per inch. And so those EFIS systems, where you put foam on the outside, they give you the same benefit and they decrease the risk of moisture condensation on the backside. This is building science, and the code isn't perfectly caught up with it, and the code doesn't address it all. Because in climate zone 7 and 8, it should be like R15, not R10 on that outside to minimize the risk of moisture condensation. So, and here's kind of one of the things that I'm really trying to bring together as we discuss the physical properties or the physics of building a building and applying the energy code, is we are looking to reduce the risk of condensating someplace. Now, one of the ways we can reduce it is we can put some foam on the outside. What's one of the big ways we can reduce it? Trying to prevent so much moisture from getting there. Trying to keep the moisture level down in the building. Trying to make sure that we aren't pushing it into the wall cavities either through, you remember we talked about right at the first that moisture moves by bulk water, it moves by diffusion, it moves by transport in air. If we can reduce the ability of the moisture to transfer into the wall cavity, we have a better building that doesn't fall apart. It doesn't rot. It doesn't have moisture damage. The stucco doesn't fall off it. We have all those things. We have all those things that we're protected against. And so I'm here to tell you we're not going to come up with one perfect solution to making sure our buildings are better. And some of the things that I'm going to talk about are beyond the minimum of the code, but there are things that we can do and we can be vigilant on, and we can make sure that we do our best to make sure, whether we're building the building or we're part of the verification on the building, that we get a building that's going to be durable. So this guy this is the guy that had triple windows too. He put R5 insulation on the whole exterior of the house. And I actually went down and took these pictures, and the insulation manufacturer was down there doing a demonstration. And you notice it is Owens Corning. They have a tape that's made for this. It's called Home Sealer. And it's a tape for their insulation. This is important. When I added polyiso to the outside of my house, it took me a little time, and so I had some set exposed for a little bit. I taped the seams with Tyvek tape because I had some Tyvek tape handy. And I did it in the fall, and as the temperatures, we have warm days and cold days, guess what happened to my Tyvek tape? It cracked. It cracked on my seams. I used the wrong tape for the product. So if you're going to be sealing a seam, you need to use the right product for what you're sealing. And so they do make tapes specifically for various foams, so as the foams expand and contract, the tape will expand and contract with it. And Tyvek tape doesn't really expand and contract. It's not meant to bridge a seam. It's just meant to seal the lap. That's all it's there for. But I had a roll of it because I'd put Tyvek on first, and that's what I'd used. And it was the wrong thing to use.
On Tyvek systems, they let them use that tape for window flash.
Yeah. Yeah, some of the Tyvek products, they allow them to use it for window flashing and stuff like that. But they got to be approved for that. When we misapply the products, it's kind of like the walkable roof surfaces. I remember when I was at the county, we had this conversation at least every couple of months with someone that wanted to have a deck that was walkable, that was over living space. And so they would want to use a membrane roof and put sleepers on it and put some type of walking surface. And we would say, well, go to your roofing membrane manufacturer and see if it's approved for that application. The membrane guy would say, no, you can't do that with our product. And we kind of went round and round on it, and there were some products that were roofing products that weren't approved for regular walking. And then there's a couple of products, and I was accused of promoting Duradeck. And I don't know if you guys are familiar with Duradeck, but it's a product that's specifically made for a walking surface for a deck that's over living space. And they have in fact, they have a procedure. They won't let anybody but their trained installers install their material. They won't sell it to you. But their product works. And they have a lot of business going back on projects, apartment projects that have decks that have failed and water's getting in, concrete slabs and everything else, so they're going back and fixed them because they put the wrong product on.
I had one on a 16,000 square foot house on the side of the hill, same thing, the deck was over the garage. They put something on like the Duradeck, but they didn't do it right, and it just leaked before the first year was up, all the way in the garage and destroyed a ton of stuff.
Yeah. There's so many instances of putting a walking surface on over a living space or over a garage, and they leak. And they leak almost immediately. I was involved in, as an expert witness on a litigation up by the canyons. I can't remember the name of the project. Anyway, every house in there is millions and millions and millions of dollars. And they had all these huge concrete decks all over the place that all failed before they even, they put stone all over them, that all failed before they'd even finished the project. And they didn't put the right membrane underneath it. So really what I'm trying to point out, as we are building buildings a lot more complicated than we used to. And because we build them with a lot more complicated systems, we have to make sure the systems are right so we can protect the components of the building, we can protect the investment of the homeowner or the building owner, and we get a building that functions and is durable. But we have to be vigilant and paying attention to the instructions. And there's nothing wrong with saying, whoa, wait a minute, provide the instructions. And ask them to find in the instructions. You don't have time to read them all sometimes. Ask them to show that that is the correct way to install it. And again, so much litigation due to water. What's the other advantage other than stopping condensation? What's the other advantage of putting rigid foam on the outside? Do you remember my picture of my living room where you can see the studs? If you put R5 on the outside, and I have some slides in another presentation, I didn't put them in here, where that wall didn't have foam on the outside, where other portions of my house, when I had siding off, I put foam on it, and the studs just about disappear because we have that continuous insulation on the outside. So where the continuous insulation is, we don't have to, that we can just add R5 or add R10 or whatever it is, and there's no thermal bridging. There's no bridging due to the wood studs or anything like that. So it really performs well. It eliminates that thermal bridging. And so the one I was talking about where they put multiple layers, we have no thermal bridging. We don't even worry about the cavity for inside. We don't put any insulation in it. All the insulation is a package on the outside. And see, this tape here is also approved for their windows. As you can see, they've put it here on their windows. So what defines continuous insulation? Continuous insulation, if you're going to list it on a res check or list it on a com check or use it in a calculation, continuous insulation can only be penetrated by a screw or a nail or some type of fastener. It cannot have a piece of Z metal or some type of channel or something like that that penetrates that insulation. If it has something like that, then it's cavity insulation, correct? Now we see a lot of commercial buildings now that they are putting like a Z metal, and they're putting what? They're putting mineral wool bats on the outside of the buildings. You've seen that? And they try to call it try to call it continuous. It's not continuous because it has those channels, those Z metal channels that penetrate through it. And so it's okay to call it cavity insulation. It's better than a lot of things, but it isn't continuous insulation. Continuous insulation really gives us a lot of protection. Tyvek tape is not improved for insulation. This also serves as the air barrier and the weather barrier. This foam, extruded foam with the tape on the seams, we don't need to add Tyvek to it, right? We got an air barrier. If water gets through, what's it do? It runs down on the surface of it. If we have an air space, it'll drain well. So you can put whatever you want over it, and we're accomplishing a couple of things. Carl, is it important that we break at noon, or we can break whenever? Okay. Let's just finish a couple of slides. Our lunch just got here. Those of you that are watching out there on the web, we'll be breaking in within the next 5 minutes. Rim joists. And let's have a discussion on rim joists, and then we'll take our break. What does what did I say about vertical insulation? Insulation in a knee wall, vertical insulation in a wall that separates a higher ceiling from a lower ceiling. What did I say we had to do on that insulation? Enclose it on all 6 sides, exactly. Is rim joist insulation wall insulation or floor insulation? It's wall insulation. Is it enclosed on all 6 sides? So how do we enclose the rim joist insulation on all 6 sides? Do we take pieces of OSB and cut them to fit the profile and then fit them in and then caulk them?
The only way to do it would be to put an insulated floor joist and then put it with drywall.
Well, insulate the whole floor joist and then drywall it? Yeah, we could do that. Insulate the whole floor joist 100%. We could do that. We could urethane it. What is urethane foam? Closed cell foam. If we spray foam on the rim joists, we have our insulation and we have our air barrier. Because we don't have to put an additional air barrier on closed cell foam, because why? Because it's closed cell, it's sealed. Whether we spray a 1/2 inch or 10 inches, it's sealed. It doesn't have air movement through it. It's an air barrier, it's a vapor barrier, it's everything. It's completely sealed. It has a perm rating of like 0.1 or even lower. It's really, really tight material. And it's crazy good material for building construction. It really solves a lot of problems. So this is a house that's really done well, except they kind of got the cantilever screwed up and they got the rim joist screwed up. Now, rim joists are kind of nasty things anyway, because they are prone for leakage. And they're prone for leakage because we have a block sitting on top of our sill plate, right? That we have a piece of that blue foam underneath it that we hope that it's not so irregular that that doesn't seal. And then depending on how the framer frames and puts the OSB on the outside, we probably have a gap down at the bottom. They might have done the rim separate, so we have a seam right on top of the floor. Hopefully not. Hopefully they took a sheet of OSB excuse me, all the way down to the foundation. Leaving it up just a little bit so it doesn't wick up. But we have lots of potential for leaks there because we have all these transitions at that point. So not only does the spray foam in the rim joist give us protection from mold and all these other issues, it also does a great job of air sealing. And we drastically reduce that amount of airflow that goes through there because it isn't sealed. And if on that house with the bay windows and all that stuff, if they had sprayed foam in there and then just insulated that thing out there, we would really be sealed up well. So, one last comment on this, and we'll talk a little bit more about this later. If we go to this sheet, if we go to the code as written says every home from climate zone 3 and up is supposed to be blower door tested. Every home from climate zone 3 and up is supposed to follow that insulation checklist, 402.4.1.1, whatever it is. Every home is supposed to do that. And that checklist says that you have to have that air barrier on your rim joist. Now, we have an amendment in Utah, and it's outlined here, And the amendment says we can either blower door test, or we go through that checklist and we meet every single item on the checklist. Now, too often, neither happens, but if the way the code is amended in Utah, if they do not blower door test the home, it should be mandatory that they spray the foam on the rim joists. That's the way the code's amended. Or some other way of getting the air barrier. You have to have the air barrier if you do not blower door test. Now, is that smart? Well, the smart thing would be we blower door test everything and we follow the checklist the way the code's written. That would be the better thing. Table 402.4.1.1. Turn the page over. Bottom right-hand corner. It's amazing what happens if you actually get the resource that I prepared just for you, Gil. So, that's the first introduction to what we're going to talk a little bit more about. In Utah, we should either be doing the blower door test or we should be doing the inspection checklist, but really the building science tells us, and that's the reason the code tells us, we should really do the whole checklist, and if we do the whole checklist, we're easily going to pass our blower door test. And then we'll pick it up from there after lunch. We'll be about a half hour for lunch, so those that are out listening, join us again around 12:20 or so. All right, welcome back after lunch. Let's pick up where we were at before we took a break for lunch. We were talking about our rim joists and the blower door test. The requirement, if we do not blower door test, we need to be doing not only the spray foam in the rim joist, but we have a list of a bunch of other things, and we'll get to that here in a minute. But again, that list is on this sheet, and it's the bottom right-hand corner of the first page. You turn it over, the list continues. So the rim joists and the cantilevers are a weakness on this project. No air barrier on the facing of the insulation. I might have had this one in earlier, but again, this one's reminding us that the small gaps, we can get the insulation behind, but one thing that we do encounter once in a while, that the small gaps between two studs do not get insulated. And that's the area that we need to do some spray foam. Attic access doors. This has been code for at least 3 code cycles, and it should have been there for a long time, that our access panel has to have a piece of weather stripping of some type, and the insulation needs to be secured to the door. Now, I think everybody's is going to agree with me pretty much. If that insulation is not secured to the door, where is that piece of insulation sitting right now in most of the houses in the valley? It's sitting at the side, isn't it? Because no one wants to get that and put it back on top of their panel and get the insulation all dripping down on them, the fibers dropping on them. And so really what needs to happen, they either need to take multiple layers of foam, or they need to somehow glue and secure that piece of insulation to that panel. And you have to have the weather strip. You remember me talking about stack action? That access panel is typically at the highest point in your home. So we have all that heat rising, and it's coming up, and and it creates a pressure, and it comes up and it hits the ceiling, and it's just looking for any place that it can get through. So it goes through at light fixtures, and it goes through at the attic access. And there's a huge amount of heat loss that occurs there.
On an unvented attic, do they need to seal around all the lights?
On an unvented attic, if the attic's not vented, if the attic is conditioned, you don't need to seal anything in the ceiling, because our air barrier is...
Well, it's not conditioned, it's just unvented. Yeah, I guess it would be.
It's indirectly conditioned.
Yeah.
If the insulation, the question is, do you have to seal around lights and stuff on an unvented attic? On an unvented attic, we have their insulation up on the underside or even on top of the roof deck. So the insulation is creating an enclosed, encapsulated attic that's part of the thermal envelope. If we are not penetrating the thermal envelope, we don't need to seal it. If we penetrate the thermal envelope, we need to seal it. And our thermal envelope, in this case that you're talking about, is up at the roof line. So no. But if it's a rafter system, a roof rafter, TJIs or whatever, and we have can lights in there, then they need to be sealed, because our air barrier, our envelope, is right there. Just a reminder again on the labels, the NFRC labels, none of these windows had them on there. Now here's a condition that occurs quite often, and I've received a number of calls on this one, and we just need to think about the science of it. Here is a doorway that comes in from the basement finished area, and it comes into a little storage room, and it comes down a little hall and opens up into a bigger area. And they have not insulated this wall here. And this is an issue, because what they're really, it looks like they're trying to do, is they're putting and creating a thermal envelope that does not include the storage room. And so lots of times people say, well, I'm not going to heat and cool the storage room, so I'm going to insulate around it and leave it outside the thermal envelope. Well, as soon as you leave it outside the thermal envelope, this ductwork needs to be insulated. You need to seal up above. You actually need to create a thermal envelope all the way around, and you would have to insulate the floor above because we're conditioned above and not conditioned below. So much, much better to make sure we just insulate this wall. We don't have to add supplies and returns to that storage room, but just include it inside the thermal envelope because it's going to be so messy trying to make that division between conditioned and unconditioned space. Vaulted ceilings. Now this one really can be, this one can create a big problem. Ceilings without attic spaces. They can do them with bats. They can net and blow and fill the whole cavity. Probably when you were at Jackson and people that work up in Summit County and Wasatch County, almost every home up there is built with rafters rather than trusses. Very few trusses, lots of these rafter roofs. And they do whatever system here to insulate those. And those will have the same condensation issues that we have with our walls, but worse. They're going to be more challenging. They're going to have more condensation than we're going to have with our walls.
In Jackson, they want as little outside air coming in as possible.
Yeah, tight as possible. Yeah. So, first, before we take the condensation issue on, R30 is allowed, you know, the code for everybody we're talking to right now is R38 or R49. And if you have a smaller rafter, the code is saying that you can reduce down to R30 for 500 square feet or 20% of the total ceiling area, whichever's less, where you have a higher requirement if you don't have room. So it's basically saying if we have a little unique dormer or something that's sticking out that's framed with tubetans and you can't get R38 or R49 in it, you can put R30 in it. But if it's a 1,000 square foot house, as we have up there, 500 square feet or 20%, the 1,000 square foot house would only be allowed 20% or 200 square feet. It couldn't use the 500. The 500 would be used for bigger houses.
What's an R30 bat, about six
An R30 bat is going to be around, well, you can get 21 in 5-inch, so it's going to be like an 8-inch bat. But, and the big thing I want to talk about is the IRC has a requirement for unvetted attics. And this requirement is actually not in the energy code, it's in Chapter 8. And I think we miss this one a lot all across the state and in other cold climates. Unvetted attics, unvetted enclosed rafter assemblies have to have some type of air impermeable insulation for ceilings without that attic or ventilation. So I have two examples here. Starting on the right-hand side with the fiberglass bat, we have spray foam that has been sprayed up against the underside of the roof deck, and then they have added fiberglass bat.
So what would that give you, 11 7/8? They got 3 inches of urethane.
Well, let me tell you what they're going to have on the urethane. The code requirement is climate zone 5, minimum R20. So that would be 3 inches. Climate zone 6 or higher is minimum R25. So you're going to have closer to 4 inches. The thing is, we have two requirements, 20 or 25, depending on how cold your climate is. But what's the whole purpose here? The purpose is the same thing we were talking about on a wall, but when we consider a ceiling, let's think about this a little bit. If I have a wall and I'm worried about the moisture getting into the wall, my big concern is, do I have something in the building that's pushing the moisture either through air or whatever, or heat, into the wall cavities? It's not a normal, natural drafting situation that's pushing moisture into our walls. It's when we create a positive pressure or something that we push the moisture into the wall. What's happening on our ceilings? If we have a heated space, we always have what? We always have heat rising. If we have that heated warm air rising, what's moving with it? Moisture. So virtually all the time in a heated building, when it's cold outside, we have that stack action occurring, and we always have some pressure on our roof system coming from the warm air. So this one, you know, the walls, they're going to condense some of the time. This one's going to condense virtually all the time. Now, what happens even today with older roofs that have attic ventilation and everything? The roofer goes out, gives a new price to put a new roof on a house, and he walks around and finds the spongy spots. And there's going to be some around the edges where there's been some ice damming. But there's also going to be some at locations where maybe the attic ventilation isn't very good and the moisture has been condensing on the underside of the sheathing. Well, if you don't have any ventilation and that moisture gets up through there, it's going to strike the underside of the roof sheathing and it's going to condense. And they're going to end up stripping the roof down and replacing all the sheathing on the roof.
I've seen some of those that were unvented that rotted out in less than a year.
They rot out real fast. I did a lot of work up in Summit County, and I actually had them calling me and saying, you got any ideas? We have water running out on the glue lamb beams, you know, that are running through there. They have water dripping out. And that was when we were first discovering this. We're tightening up our homes, we're doing all these things, but we're not paying attention to where the moisture's going. And that's a big issue. And so the code, I think it goes back to even 2009, has had some requirements in there about that. And so there's a couple of ways you can treat it. This one is probably the most common, but I am seeing more of this, and people in our class yesterday, a couple of them had seen it, where they're putting rigid foam on the roof deck on top. And in this case, they put down 6, 7, 8 inches. Well, actually this one they had 1, 2, 3, they had 4.5 inches of foam.
They do that a lot when they put a metal roof on.
And that's what this one is. This is a metal roof. They've used long screws to screw another layer of sheathing on it, OSB, and then they put the metal roof on. And then they put the balance of the insulation underneath. If you have that R20 or R25 up here, as that moisture comes up from below and moves through the rafters and hits the underside of the roof deck, it's going to be warm enough that it doesn't condense. So the whole purpose is provide enough insulation that that surface stays warm so that it doesn't condense. Some of them, and a lot of them I'm seeing now when they do this, and this isn't done that much, but they put on the rigid foam, and then before they put the next layer of sheathing on, they lay sleepers on it, you know, 2 by 4, 2 by 6, flat, going up through the roof, screwing those down through, and then they have that 1.5 inch air space on top of the foam, ridge vent on top, venting down at the bottom, and then you have airflow, cold airflow through there in the wintertime, and you virtually eliminate the ice damming. That we don't have any heat coming through melting snow. And so what do the roofs do? They hold the snow. And that's okay if your roof's designed to hold the snow. We designed the roof to hold the snow, and it actually is better than, you know, the bare roof, you know. But eye stabbing is such a big deal. I mean, any of you that spend any time up in the Summit County, Park City area, we see heat tape on every single building that's built up there. You know, that's standard procedures, is to put heat tape on it. Well, if you could get the building to hold.
Sorry, you have a question from the internet.
You have a question?
Yes. It says, will you explain if there is a difference if you used 4-inch of closed cell and then open cell after instead of back?
Okay. The question is from out there. So if we put 4 inches of closed cell and then put the remainder of the required insulation in open cell, is that different than the bats? Well, really, no, it's the same thing. The key thing to remember is we have an insulation requirement, and let's just say it's R49, because that's what most of us are now. If you put 25 on top, then you need to put the balance, the R24, in fiberglass or open cell. It really doesn't matter. You can put it in whatever you want to. The key thing is that we have enough closed cell to to meet the principles of psychrometrics, to where we don't condense on that surface. So open cell foams, their R value is close to per inch what fiberglass is, but either product's fine. And I kind of like the idea of doing it in closed cell, then the rest in open cell.
Those R38 fiberglass bats are usually 12 inches or a little bit under.
Yeah, the bat, well, and bat density, you know, you can buy a 3.5 inch bat that's R15. You can buy a 3.5 bat that's R13. You can buy a 3.5 inch bat that's R11. You can buy a 2x6 bat, you know, 5.5 inches.
What's that mineral?
That's 19. And some of those are the higher value. They'll be like R21 on a 2x6 or R15 on a 2x4. So you really got to check your products. You net and blow, and it's going to be a little bit higher than those numbers. So either one's fine, Brittany. Just make sure that the total insulation at least meets and exceeds the requirement. Now, while we're on that, it's important to bring this up. I've received lots of calls from people that say, I'm trying to get my res check to pass, and it doesn't matter how much roof insulation I put in, it doesn't make any difference. Once you get up to R38, R49, adding more insulation almost changes nothing. It's virtually does nothing. What did I show here? R38 insulation for 144 square feet is has 227 BTUs flowing through that 144 square feet. If I doubled the insulation from R38 to R76, what would it do to that number? Put it in half. That's all it would do. It would just take it in half. So once we get down to a small number, taking 227 down to basically 113 or 114 just isn't that much difference when we look at the whole envelope. So R49 is great insulation. If you're building a net zero house or you're building a super insulated house, you really, once you get to R60, buying more insulation just really isn't worth the investment. Put the money someplace else.
They used to allow that, you remember that smart barrier
For this?
for unvented attic, that
Yeah.
they allowed that smart membrane, then they just blew the whole thing full. But they had that smart membrane like
I know what you're talking about.
you know, that breathes or whatever. And then if you put sheetrock over that and paint it, you wouldn't get that air infiltration in there, would you?
Okay. Okay, I'm going to repeat that. The question is, there's some smart membranes. There's some vapor barrier membranes, and one of them is called membrane, you know, 2 words or something, but they're smart membranes, and what they do is they'll block the moisture coming in, but if there's excessive moisture in the cavity, it opens up and lets it dry, lets it breathe. And so it changes depending on the humidity conditions. And a lot of jurisdictions have allowed it in the past. And my problem with smart membranes is the same problem I have with any vapor barrier. They only work if they are complete, sealed, taped, caulked, so that you have a complete air impermeable membrane.
Painted.
Well, the paint gives you a class 3 vapor barrier. But what happens, and this is, we allowed them some at the county, and then we quit allowing them. And that's because what happens with the drywall on the wall or the drywall on the ceiling when the sheetrocker comes in? How do they cut out sheetrock holes? With a router. So we take a whole house and we spread Visqueen all over all the walls on the house, and to do a vapor barrier right, that would mean you'd seal the boxes, you know, you'd tape to the boxes, you would caulk the holes or spray foam the holes in the back of the box. You'd create a complete vapor barrier, because if you don't complete the vapor barrier, what good does it do? It's like having a bathtub that has holes in it. It really doesn't. We're trying to stop water movement, or a swimming pool with holes in it. So the water's going to go through it anyway. Well, the smart membrane, and they're very effective and they're great products, but what if you have can lights in there? You do all this, and the smart membranes mandate that you caulk it, you know, you run it down the ceiling line, and then you caulk it to the top plates, you tape all the seams, you do all that stuff. You tape it and seal it to your can lights and your electrical boxes, and then the drywaller comes in and does what? Gets his router out and goes on all those penetrations. And how much integrity do we still have in our vapor barrier? It's full of holes, isn't it?
But if you did all that, would you still meet code today?
You'd meet code if you could maintain the, well, it's an interpretation thing. The code doesn't say you can use a smart membrane.
Doesn't it have a air infiltration rate or something on that in there?
Well, yeah, but that's not what the code isn't looking for that. What the code says, and I see where you're going. The issue is not exactly what the code says. I'm talking about some of the things that we should be aware of, and it doesn't matter what the code says. It's building science, and we should be aware of it. Now, if the code says, yeah, you can use a smart membrane, which it doesn't specifically, and they don't do it right, then it's not going to do any good. If they come to me and say, I want to use a smart membrane, and I, under the alternate materials and methods, say, sure, you can use a smart membrane because it meets the requirements of 806.5, and you can make that interpretation, then that's great, but you have to install it so that it's compliant. And if it's cut full of holes, it's not compliant.
But say you get a remodel and it's stick frame, you know, with 2x10s, how do you meet the requirement for the insulation and unvented? So it's unvented, plus you gotta meet the R value.
Well, the question
2x10.
The question is, you have a stick-framed house and it's 2x10, and you're doing a remodel, and you strip the drywall off. Is that what you're saying? You strip the drywall.
Totally rebuilt.
It's totally opened. How do you meet the requirements of the code for insulation when the cavity's too small, and And how do you meet this requirement? Well, the code doesn't require you on a remodel to do any more than insulate the available space.
So
Now,
it doesn't have an R value.
well, I mean, if you go to the existing building section of the energy code, it tells you that if you expose a cavity, you have to fill it. It doesn't say specifically that you have to meet the R value. Now, you could, as the code official, you could make the judgment, well, wait a minute, you got a 10-inch cavity. If you fill it full of,
9.5.
you got 9.5 inches and you sprayed 9.5 inches of urethane foam, you can meet the code requirement.
Right.
And that might be considered a little bit heavy-handed, that you shouldn't make them spend that much money. But if they expose that, you definitely should have them address this. And the R20 that they add will take however many inches, and then the balance they can meet. So I've never got hung up on if they expose a cavity, even though it says we should be putting in R20, the only a 3.5-inch cavity, put in what you can fit. If they exposed one and all it had was first strips, I had them put the foam, rigid foam, to the maximum they could fit, even if it was only 3/4 of an inch, because you're complying with the existing building portions of the code. Yeah, but you'd really want to do this, and it's really something, if you're doing plan reviews, you need to try to catch. We had a lot of them in the county that they had like a flat roof or a really low pitch, and they put a new membrane roof on it, and you get out there, and they didn't put any foam under the membrane before they set the membrane. The most inexpensive way to insulate a roof is to put the rigid foam on top, and when it's a low slope, like a 112 or less, it's the perfect way to insulate that roof, is to put some foam on it before you do your membrane. And it's not very hard to get the R20 on top, or the R25. If you use polyiso, you get it in a few inches, 3 inches. We kind of miss this in the code a lot, but it's a real critical building science thing that we need to be thinking about, and that's why I spent so much time on it, because I want you to walk out of here going, well, you know what, maybe I'm not going to, and I'm not telling you this is what you have to do, but you can think about this. Maybe I'm not going to be so hung up on the vapor barrier on the wall as I am on this type of thing. Or maybe I'm going to worry more about the rim joists, and I'm going to worry about more of these other things, because as I get further in here, you're going to see that our vapor barrier is probably not the most critical piece. In fact, I can guarantee it's not the most critical piece of what we're looking at here.
Didn't you say they were gonna eventually omit that?
I think it'll probably be generally gone from a large portion of the code. But let me make sure you understand, for our climate zones, for our cold climate zones, now we're not going to see them disappear on the warm climate zones where they go on the other side. I think they're going to stay there for a long time. Grab something to eat, Jim. Closed cell foam or some other method to prevent the condensation. Airflow, the good, the bad, and the ugly of airflow. Airflow can be the best thing we have in a building. If we have proper airflow, if we maintain proper pressures in our building, we have far fewer problems. But if we have bad airflow, or airflow where we don't want it, then we have huge problems. I mean, I used airflow to deliver heating and cooling, and to filter, and to humidify, to exhaust, to do all kinds of things in buildings for more than 3 decades. But then I have old buildings that didn't work very good because they leaked a lot of air. They had airflow out of the building. Our real focus right now is on the airflow in our building and through our building envelope. So on the plus side is airflow for our forced air heating and cooling. On the bad side, or the ugly side, is airflow leaking in and out of our buildings. It's good that we can exhaust contaminants and moisture and stuff out of our buildings. It's good that we can have a ventilation system that provides us the fresh air we need in the locations we need it, but it's really ugly when we have airflow pushing moisture to the wrong places. And so if we have those wall assemblies, and for whatever reason, and there's a bunch of them we'll go over, we force air into all of our wall cavities, the possibility of condensation in our wall cavities goes way, way up. If the airflow is slightly into the house through the wall cavities, then we lessen the chance for condensation in our wall cavities and increase the durability of the building. Important thing that we have to understand is air in means air out. If you have an exhaust fan running in a building, you have 100 CFM leaving the building, 100 CFM has to come in and replace it. If you have a supply fan of some type, it's hooked to your furnace. Let's say you have a duct hooked to your return air on your furnace, you have your fan running continuous, and it's sucking in 100 CFM from outside, blowing it into your house. What's going to happen? We're going to leak 100 CFM out of the house. We cannot add air to a building without air leaving the building. We cannot remove air without air coming in to replace it. So the question is, well, what if I have a big fan, a 1,000 CFM fan on my range hood? Can it remove more air than leaks in? No, it can't, because it'll reach a point that if you can't leak enough in to replace it, that it quits moving air out. What happens when you have a dirty filter on your furnace? I've been on furnaces that there's almost no air coming out of the supplies. The furnace constantly runs into limit, and the fan's just running and running and running. There's hardly no air. Why? Because the filter's restricting airflow. So the furnace doesn't move any air if it's completely blocked off. You have to have it air in equals air out. Now, go ahead.
If you have a hood over 400 CFM, can you wire that in to where that comes on and opens a damper in your return air?
Say the question up in the mic. Your yes and no's, I'm okay, but
Yeah. If it's over 400 CFM on a hood, can you wire that so when you turn that on, it brings in outside air into the return air of the furnace?
can you do that?
Yeah.
Yeah. Yeah, absolutely.
You can do those
So-
controls so they work like that?
Yeah, so, and that's a perfect example of what I'm talking about. Air in equals air out. So the code, and this number's come about just by general experience. And I don't know exactly how they came upon the 400 CFM. But the assumption is the typical house constructed today, if you exhaust more than 400 CFM out of that house, it won't leak enough to replace it. You with me? So we've made the assumption, whether it's wrong or right, that we put an exhaust hood in a house that moves 410 CFM. It can't leak enough in to replace it, so it's not going to be very effective if it's an 800 CFM exhaust fan, because it can only leak in somewhere around 400. And so the exhaust fan doesn't work very well. And so the question is, well, so how do we resolve this? And one of the ways that it's being done is when the exhaust fan turns on, we also open a damper that allows air to come into the through the return system of the forced air furnace and supply outside air, makeup to replace what we're exhausting. And there's simple controls that you can do that so that it only opens when you're exhausting air. And in fact, that's what the code requirement requires, is that it only operates when you're exhausting air. It's not the best code, the best written code. It doesn't say anything about tempering. It doesn't go down that path. It just gives you the direction.
Yeah, that's a bad thing about it, the cold air.
Yeah, it can bring in a lot of cold air. But what it is the code's trying to address the building science principle that if you exhaust a certain amount of air out of your space, you got to have a way to get it back in. But if you build that house out of insulated concrete forms, or if you spray foam everywhere, guess what? 400 is probably too high of a number. It should probably be 100 or 150. It could even be smaller than that, because if your home's super tight, you put in that 800 CFM fan, and guess what it's going to move? It's going to move like 100, whatever it can leak. Maybe it's 100, maybe it's 50.
A lot of those hood manufacturers, I think they're kind of pricey that will supply that unit with the hood.
You can buy
Conditions and everything.
You can buy makeup air units for residential hoods that have electric strip heats and everything else in them, and they do work. So airflow can be good, it can be bad, it can be ugly. So we've been talking about airflow. Let's talk about air as a transport mechanism. So I used air to transport heat. I also used air to transport moisture. And I did that by putting a humidifier on my HVAC systems. And so we would take moisture, generate moisture through steam or through a pad or some method at the furnace, and then we'd transport it through the rest of the building. And that's great. That's one of the good ways that we transport something with our air. We beat up air barriers for a half a day because I'm trying to get you to be thinking about this and to understand that the air movement that we have within our buildings, whether it's because of positive pressures or because of wind or because of stack action, will also transport moisture. And whichever way we're moving air, we're going to be moving moisture the same way. We just talked about our ceiling, and we talked about how we are going to transport moisture straight up to stack action up against the roof or the attic assembly. We also have air transporting pollutants into our house. If we have a radon issue with our house and we don't have a sealed floor slab, we're going to have little air leakage and radon leaking up into our house. As we mentioned early today, if you have your car running out in the garage with only the garage door open this far, and you haven't air sealed the wall between your house and the garage, we are going to have air transport bringing exhaust fumes into our house if the pressure conditions are correct. If the garage is positive with respect to the house, or the house negative with respect to the garage, we're going to transport carbon monoxide and everything else into our house. So vapor travels in air, and that's the big one that we want to focus on. We move air and we move moisture. If we have moisture in our air and the air moves, there's going to be moisture in it. And kind of summarizing, if we have a hole, depending on how big the hole is, we are going to move air through that hole. And if we're moving air through it, we're going to be moving moisture through it. Pressure differentials drive the flow. Some of you have heard me preach about return airs in every bedroom, right? Or a return path out of every room, out of every bedroom, any room that you can close up. And if you've been to my load calculation classes, we talk about this a lot. If we have a house and we don't have a return air in the bedrooms, and we have carpet that fits fairly close to the bottom of the door, and our furnace is running or our air conditioner is running, what's going to occur? We're going to blow supply air into the bedrooms, and if it's a master bedroom, we'll blow it into the master bedroom, the master closet, the master bathroom. We might have 3 or 4 supply airs, and then we just have this little space under the door that we're trying to return 400 CFM back to our return airs that are located in the hallway. Well, that's not going to work. We know that. So what it creates in all the bedrooms with the doors closed is a positive pressure in the bedrooms. And then it creates a negative pressure out where the return airs are. Correct? Does this make sense? So we have all the returns and just some of the supplies out in the living space. And then we have 40% of the supplies in the bedrooms and no return. And with the doors closed, we're trying to draw too much air back to the furnace from the living space, and we're positive pressurizing the bedrooms. So what happens? We positive pressure the bedrooms, and the air finds a place to go, and it leaks to outside. So if we take a long shower, our master bathroom's full of humidity, and we're shoving the moisture into the walls, we are drastically increasing the possibility of condensation occurring within those wall cavities. We are drawing from outside through the rest of the house, and so we might have the pollutants and stuff from outside that we're bringing into our house. I kind of laugh at, the news tells you, well, we have bad air days, so make sure you stay in the house. Well, if your house is leaking all that stuff in anyway, it's not going to do much good. And if we're not filtering it or not trying to take care of it, how much good are we doing? So simply by not having a return path in our bedrooms, we can create the positive pressure, and we can be moving that moisture where we don't want it. So let's define that air barrier. It's one or more materials joined together in a continuous manner to restrict or prevent passage of air through the building thermal envelope and its assemblies. And that is our focus today, is the building thermal envelope, its assemblies, and how are we restricting air. Now, I'm not going to go into how to flash windows and everything. That's the subject for another course. But we need to be looking at the materials that are being used to seal an envelope, and if they're using Tyvek as an air barrier, Tyvek will tell you you have to take the seams. If you're using it just as a weather barrier, it doesn't tell you you have to take the seams as long as you install it in a shingle fashion so it drives the water out. So if it is your air barrier, it doesn't need to have the seams taped.
How good is that painted on OSB, or what's it called?
Well, there's a number of other air barriers, and we'll talk about some of them. In fact, I got slides in here for 2 or 3 different ones. But the whole thing is, what's the definition of an air barrier? And if it meets the definition, it's an air barrier, correct? Does it, number one, is it continuous? And does it restrict or prevent the passage of air through the building thermal envelope and its assemblies? So looking back at the cantilevers, are they continuous? Have we continuously provided an air barrier to all those places? This one we've already talked about. We can put on that fleece jacket, we can put on the flannel shirt, we can put on the sweater, we can put on all these things, and if the wind blows, we're cold. We have to complete the air barrier and put that windbreaker on if we want the insulation to work. So that's why our air barrier, one of the reasons our air barriers are important. So airflow basics. Airflow requires a hole or a passageway or an opening. A force to push or pull the air through the opening. Can a building be too tight? Any opinions? Can we make a building too tight? No? Yes? Anybody else want to weigh in? The comment is they already have in some places because they're installing ERVs. HRV or ERV, they both work similarly. So what does the code say about a building being too tight?
Gotta provide mechanical ventilation.
Provide mechanical ventilation. The code without amendments, and I've already touched on this, without amendments to the code developed by people, a number of them that are pretty smart, that know building science, Joe Stiebrick and all these other people that really know building science, says we're building houses tight enough now that we need to make sure we provide some mechanical ventilation. Remember me talking about the cooler? We need a certain amount of fresh air. And so the code has defined, based on ASHRAE 62.2, how much fresh air we should have for every person and a little bit more for how many square feet of building we have. So we have specific numbers that are easily found in the IRC, and it basically is a number someplace for a home between 30 and 100 CFM is generally where we're going to be. It's not a huge amount of air. It's square footage and number of people, those two factors. And so the code development bodies have said, okay, the magic number where we need to make sure we mechanically ventilate versus naturally ventilate. And what's mechanical ventilation? That's a fan. What's natural ventilation? That's cracking a door or a window. The code says if we hit 5 air changes per hour when tested with a blower door at 50 pascals, we're tight enough that we should have mechanical ventilation. So rather than just using it, looking for a guess, the code says, let's test the house and see how tight it is, and if it hits a certain threshold, let's make sure we put a fan in there that exhausts pollutants out, or a fan that brings fresh air in, or a fan that does both, brings fresh air in and exhausts pollutants out. And it gives you all three options. And so what did we do in Utah and other parts of the country? We said, no, we don't think that number's a good number. We don't want to worry about mechanical ventilation until we get down to 3 air changes per hour, or a tighter envelope. And we don't want to blower door test everything, so we want to leave an option. We either blower door test or we follow the list, that table 402.4.1.1. So without amendments in Utah, starting back in 2012, every single house would have a blower door test. And the requirement is 3 air changes per hour. The trigger for mechanical ventilation is 5 air changes per hour. We've exceeded, we've gone tighter than that. And so every single house, every single family dwelling, every duplex, every townhouse would also have mechanical ventilation. By amendment, it says, well, we don't want to blower door test them all. We have this checklist. We can do the checklist, and if we do the checklist, we don't have to blower door test. Well, if we don't blower door test, how do we ever trigger mechanical ventilation? We don't have anything in the code that says we can make them do mechanical ventilation unless they do a blower door test.
If they left it at 5, every house would require.
That's exactly it. The code without amendment says you have to tighten the house up to where it's clear down to 3, and the trigger for mechanical ventilation is 5. And so the 3 is much tighter, and that's where we're triggering now at 3.5 by amendment. We basically have a state amendment that ignores building science, and I understand that it adds cost and doesn't require the blower door test. And so in turn, if they don't blower door test, there's no one's going to tell them, well, you have to put mechanical ventilation. Well, a lot of my good friends that are builders And I truly, I'm being 100% honest, a lot of the builders that have pushed for these amendments I consider my dear friends. I mean, they really are. They're good friends of mine. They've been very candid with me and told me, well, you know what, Brent, I found out that my houses are tight and I'm having moisture issues, so I am just automatically putting a fan in my house, all my houses, wiring it continuous, a Panasonic or Brown's really high efficiency fan, and letting it run all the time because I want to control my moisture. I want to make sure I don't have the issues that we've been talking about for 4 hours now, 5 hours. So it's the science that I'm trying to get you to understand. And I'm not here to preach to tell you, if you're a code official, do a better job. If you're a builder, do a better job. Or if you're an architect, do a better job. What I'm here to tell you is I want you to understand the science and why we have these various requirements in the code, and to maybe make better decisions and do our job a little bit better and build better buildings. That's the key thing. We want to build a building. So can a home be too tight? Not if you ventilate it. It's never too tight if you ventilate it. You can build it just as tight as that cooler as long as you bring in some fresh air and exhaust some air, you're great. Now you can get so tight that you can't just put in an exhaust fan and rely on leakage to replace the air you exhaust. You're going to have to mechanically supply your fresh air just like you mechanically exhaust your bad air.
How do you know if you've reached that threshold?
Blower door test
The test they don't want to do.
that they don't want to do. I mean, have we said, well, we're going to quit testing drainage, DWV. We're going to quit testing gas lines. We're going to quit testing, we're going to quit testing concrete. No, there's nothing wrong with testing a house. In fact, it's a good thing to spend a little bit of money to test your house. And these guys that do the testing, the HERS raters, they provide a lot of service and they give you a lot of information, and it prevents you from having one case that ends up going to court. Then it's a great thing. If it makes happier customers and you get referrals, it's a great thing.
So, what's the threshold if you have to use the fan, if you have enough infiltration? Is that the 3 air change?
The question is, at what point do we know that we're going to have to do balanced ventilation versus just an exhaust fan? It's probably as you're getting closer to 1. It's pretty tight. I mean, let's look at it this way. The trigger for makeup air for your range hood is 400 CFM. And I'm really making some assumptions here, but that's kind of assuming that the house is someplace between 3 and 5 air changes per hour when it's tested. They're saying the typical house will leak about 400 CFM. So you're going to have to build a pretty tight house before it won't leak the 30, 40, 50, 60, up to 100 CFM, depending on the size of the house, that you need for ventilation. But let's just say if it's insulated concrete forms, if you spray foam everything, it's too tight. And you mentioned we're seeing houses that they just put in HRV, ERV. Even the Icynene people, when they started pushing, they'll spray the walls, they'll spray the ceiling, they'll spray the underside of the rafters and everything. One of the things they had in their specifications was ventilation. They wanted a heat recovery or energy recovery ventilator. They backed off on it a little bit and said that you need mechanical ventilation because it was scaring people off. But you do need some mechanical ventilation. And if we know we're building tight, we need to make sure we meet it with the appropriate mechanical ventilation.
I don't think I've ever seen one come under like about 2.8 or something.
Yeah, they're generally running between 3.5 and the high 2s. But I'm seeing on the super insulated houses, the houses that are spraying foam, theirs coming in down close to 1. I'd have to ask Mitch what's the lowest one he's ever tested, but I know some of them gone under 1.
All sprayed and, they still about the same.
The thing that's going to leak is your doors and windows and your ceiling assemblies. Now, I think I touched on this earlier. Notice we have a garage door. I think that's garage, or maybe it's a window. Someplace on this house we have a garage, and we wrap the Tyvek around the outside of the garage, but we do the Tyvek inside, separating the house from the garage. Isn't that a place that's part of the thermal envelope, not the outside of the garage? Yeah, and the garage, but the garage needs a Tyvek for the weather barrier, for the drainage. So I'm not saying it shouldn't be there. So a building is not too tight. We've minimized uncontrolled infiltration or air leakage, and we've provided ventilation. It's not really hard. Airflow through the thermal envelope. I have a list of, I think there's like 19 items here that identifies all these different places that air leaks through our thermal envelope. And so that's why it's really hard to get a house completely tight. And notice how many of them are up at the ceiling. Quite a few of them are at the ceiling. Those are all places that we can leak. And there's a couple of ones that I want to note, and that's because they create an extra hazard. And we've already talked about it. And the one is number 15 between the garage and the house. And we know why that one's a critical one. And then the other ones are the ones that do have to do with the fireplace and the furnaces and water heater, and they're venting to outside. Anytime we have a combustion process inside the house, we have some reasons to be concerned, because they are using air out of the house, which means we're infiltrating air into the house. And
When they do a blower door, do they block those furnaces and stuff off?
they're not supposed to. When they do a blower door test, they typically draw the house negative, and so it pulls the backdraft dampers closed, because they exhaust the air out of the house and take it negative 50 pascals. And so any backdraft damper should close, and it'll measure the leakage through those. If you have ductwork in an attic, it's going to measure the leakage that comes in through the ductwork. And so all those things will be accounted for in there. But the dangerous things, again, are that wall between the garage and the house, and we have the potential with gas-fired and wood, fuel-burning appliances and fireplaces in the house. So those are ones we want to kind of be concerned about. Airflow, again, the controlled airflow is the mechanical fans and ventilation systems, and they might be a positive, negative, or balanced pressure, and we'll go in a little more detail on that. Uncontrolled, not part of the building design, leaks and holes in the building, leaks in the HVAC ducts, and wind and other pressures. We had someone in the class yesterday that when they have wind blowing against their house, they can't keep their house warm because their house leaks so much. Now, the solution isn't a great big furnace for when you have strong winds once a year or once every 3 years or whatever. The solution is to make the house quit leaking, because it multiplies. When the wind's blowing, it multiplies the amount of air leakage. Infiltration, by definition, is the uncontrolled leakage. I can control my ventilation air, I can control my exhaust, but I can't control how much leaks through the holes in the building. Airflow through the thermal envelope, we have, again, it's how many holes or what pathways do we have in that envelope. And here are some of those spots that we kind of forget about. This diagram, one of the reasons I included it in here is anytime we have this kind of condition, and it might be the inverse of this. This is outside. This is an overhang, but we might have a condition where it turns and goes the other way, like that attic space that we had early on in one of our first slides. Anytime we have floor insulation that's running through a joist and we don't need it to continue any further, we need to have a block. We need to have that air barrier to stop the airflow.
Brandon, you have another question from online.
Okay?
Does a radon mitigation system pull more air into the home?
Does a radon mitigation system pull more air into the home? It could pull a slight amount of air from outside into the home. What a radon mitigation system is doing, and the way they work, is they're trying to exhaust under the slab, correct? So they have the perforated pipe under the slab in the gravel. They're needed because we have cracks and we have places that air can leak up, or radon gas can leak up into our space. So if we have the radon system running and exhausting air from under the slab, the air has to be replaced, right? And so it's going to leak some air into the building and drive it down and suck it into under the floor slab, basically. And so what we're creating with the radon system, and that's a great question, is we're creating a negative pressure under the slab. By doing that, the radon doesn't flow up into the house. In fact, we have the opposite. We have air, outside air or inside air, flowing down in under the slab. So we're completely, if it's functioning correctly, we're completely stopping the flow up into it. We're reversing the flow. And in some cases, that's what we want to do with the moisture and the other pollutants. We want to control which direction we're moving them. So that's a good question. We're controlling the airflow. And that's a great use of airflow to protect our thermal envelope. How large a hole do we want in our home? We've already had that question. Pressure differences, wind, stack effect, fans, HVAC design flaws, all cause those pressure differences. Without this block, we don't do any sealing back here inside the house, do we? On the right-hand side of this diagram, we insulate at the overhang, but then out over the finished conditioned space between the first and second floor, we have lights, we have all these things, and we're not doing any sealing because there's another floor above. But if we don't block here, then we're going to have that air movement. We're going to have air movement either from outside or from inside into that, and as the air moves through the insulation, we have less insulation. Again, airflow in is airflow out, whether it's controlled or not. This picture isn't as clear as the one I have further on, but this is the crawl space, and you can see the mold. You can see the dark spots, and if you can see the back there, I need to lighten this picture up. There's a lot of mold on the rim joist. This is the one. Improper airflows effect on occupants. This is a lot of mold in a house that was less than a year old.
I think it was all good, it's just that they wrote the code bad.
The code is written well, the code wasn't properly applied.
They live in the damn thing, so it didn't turn the...
We'll talk about that after, okay? Pollutants, mold growth, radon. We just had the question on smoke, CO2, VOCs, cleaning chemicals. These are all things that have a bad effect on people. I mean, just this last year, what did we have a big, or maybe 2 years ago, we had this big thing where they were talking about paint strippers and people that died because they were stripping paint inside their house and they had no ventilation. And there's some thing in the paint strippers that was killing people. How our envelope is built, how it exhausts, how it ventilates, all affects those things. Moisture and mold, poor humidity control, and condensation issues, combustion. We have backdrafting gas appliances, carbon monoxide, which is lethal, conditioned air wasted to outside, replaced with hot or cold outside air. And all these problems with our gas appliances are solved with we have some great gas appliances, work really well, extremely safe. I have one of them in my house. I have a tankless water heater. It's a really high-tech, great gas appliance. But it's sealed combustion, it's direct vent. It does not use any air out of my house. It doesn't put anything into the air in my house. There's not a risk of me discharging carbon monoxide into my house simply because of the design of the water heater. Now this is a tank type water heater, and it uses combustion air out of the house, and it has a B vent that goes up through. Has anybody read the 2018 IRC code on the range hoods? We didn't adopt the 2018 IRC. We're still on the 2015. But the 2018 IRC says on the range hood section, the 400 CFM, it says if the gas appliances in your house, the space heating and water heating gas appliances in your house are direct vent, you don't have to provide the makeup air. It's an exception to the 400 CFM requiring makeup air rule. So we didn't adopt that, so that's not part of our code here in Utah. But basically the code body is saying, you know what? Our big problem with exhausting too much air is reversing B vents. And so this water heater will backdraft. Exactly, the water heater will backdraft. If you turn on that range hood, you suck more air out of the house than can leak in through the walls. It's going to find a source, and it's your gas appliances sucking down the B vent. Same thing happened with my first house, my very first house I bought back in the earlier in the 70s, and it had a wood-burning fireplace. That was one of the big selling features. How romantic and how wonderful to have this wood-burning fireplace in your new little home. And you start a fire in that and get a rip-roaring fire, and it sucks so much heat out of your house and so much air out of the house that my B vent would reverse. And I was in a subdivision where there was 300 or 400 houses that were exactly the same. And they'd always call me, my furnace smells funny and there's hot air coming and moist air coming out of the front of my furnace and out of my water heater when I burned my fireplace. It was running out of air. And that's dangerous because it's carbon monoxide coming into your house. We had to crack a window close to the fireplace when we burned the wood in the fireplace to provide combustion air. All these problems can go away with direct vent appliances. I'm going to say something that people don't like me to say, but if you have a home that you're spraying foam and you're doing all these things and making it nice and airtight as the code requires, you can't have an open hearth fireplace and expect it to work. In fact, the code really doesn't allow you to build the open hearth fireplace. If you go to chapter 9 and read that last section about it and the combustion air and everything, you're not supposed to take a house negative as part of your combustion air process for a fireplace.
If it's gas log, you have to prop the damper over.
But that violates the other sections of the code. So they really don't belong in a tight house today. But all of these things, prop and dampers, open and everything, because we have a risk. We have a risk, a pollutant that can kill you that we have inside our homes. And if we can control our airflow, we don't have the risk, or we minimize the risk. And I remember I said it's solved by direct vent appliances. And we're going to circle back to that in just a second. We finish up a slide or two. So we have improper airflow, effects on occupants still. We've talked about some of the other things that are more dangerous right back here. And let's talk about these other things. Comfort. Cold drafts in the winter, hot air in the summer. Had a conversation. Your basement gets cold, right? His basement gets cold in the summer all the time. When his air conditioner runs, his basement's always cold. Improper airflow. That's improper airflow in the HVAC system. That's duct leakage. It's some of those issues that we're getting that down there. And so he has some comfort issues. Convective flows, warm air rising. Cool air falling creates temperature imbalances in the building and between levels and the floors. When I bought my house I'm in right now, 3 levels with 1 furnace. When we bought it, it had a ceiling fan in every single room just about in the whole house. And I says, what's that for? And he says, well, it's to make the temperature more even. Well, yeah, the make the more even was an understatement because, and it didn't solve it because it was, in the summertime, it was 8 degrees warmer upstairs than it was on the main floor. The furnace was a little too big, but the big deal was there wasn't any return upstairs. And so all the hot air rose, and all we were trying to do is to cool it off with cool air coming in from the ceiling, and the cool air would fall. And so I needed to add return to the ceiling upstairs.
Isn't that the best place to put your heat recovery ventilator up in the?
There's a lot of factors on where you put your heat recovery ventilator, but high is typically where they're mounted. My point I'm trying to make is warm air rising and cool air falling can really impact comfort. And then we make it worse by putting a grossly oversized furnace or air conditioner in there, and it runs a short cycle, and so the air just stays stratified and never gets mixed. Where if we have properly sized equipment that runs longer cycles, it works better. Whenever someone insisted on doing multiple levels with a single furnace, I always put in a 2-stage furnace that would run on low heat until it wouldn't keep up and then jump up to high heat. So it'd run long cycles. When it was really cold, it might run almost all night long at a low heat level, but it mixed the air and it kept it even. Convective flows, that's what we've been talking about. Occurs in both summer and winter. Cold basements, both seasons, right? Warm upper levels, and the load calculations properly done, properly sized, minimizes those issues. Mechanical design flaws, which the biggest one is oversizing of equipment. So wind can blow through our house, stack effect can affect our house, and our combustion and ventilation can affect the pressures in our house. I thought this was a great series of slides. How we think the code works, or we thought the code works. If we have a crawl space and we ventilate and we locate them so that it cross-ventilates, what happens? We think that we have air coming in and just flowing through the crawl space. Do we see a lot of effort being made to seal the floor between the crawl space and the house? What do we have? We have tubs with holes for traps. We have plumbing penetrations. We have all this stuff going through the floor. And we really don't make a conscientious effort to seal that floor. So what really happens with that crawl space, and we might put a vapor barrier down, but generally not. So what really happens, we have these holes down here, we have a leaking floor, and we have the stack action, we have the heat rising in the main floor, and it's going to look for a source to replace that air that leaks out through the can lights and the ceiling lights and everything into the attic. And so what it actually does, a lot of it, is we draw in air from the crawl space, which is humid, and we take it up through our house and out through our ceiling. So I think we do more this than this. Now the building science solution, and I'm going to tell you that this has to be done correctly for it to work, is to condition the crawl space. Now what are the requirements when we condition the crawl space? It's a 6 mil vapor barrier, taped and sealed, runs up the walls, caulked and sealed against the walls so that we have a super tight vapor barrier across the dirt. Moisture comes out of the ground. I don't care how dry a climate you're in, we have moisture coming up out of the ground. We do that, then we provide some ventilation either through the household ventilation, heating and cooling system, or through an exhaust fan that maybe just exhausts a little bit of air out of the crawl space. Please.
That be done by indirect heating and cooling in that crawl space?
Okay, so is this indirect conditioning? Is that what you're saying? Okay, now that's a great question. We do, and I don't know if I said it, we do have to insulate the walls, right? We have to spray the rim joists or insulate the rim joists. And then what the code says is we need to move, I'm trying to remember the number. It was just,
50
no, it's,
square foot.
no, it's only like 3 CFM per, it's a pretty
One
small
CFM
number.
Per 50 square feet or something.
Yeah, one or 2 CFM per 50 square feet. So I was thinking it was 2 because of 400 400. Anyway, it's a small amount of air. It's a pretty tiny amount of air that either has to be exhausted out and is based on the square footage. And the number lots of times comes in at 8 or 10 or 12 or 15 CFM. It's a pretty small number. Yes, the space is indirectly conditioned. We don't necessarily have to put a supply in there. What the code directs us to do is to put an exhaust fan that just exhausts that little small amount out of there, or we put some supply down there and provide a return path to that supply. And that return path can be a small return air grill in the floor.
You can put a transfer air in.
You know, a transfer that comes from the floor. The problem is it's a low number, and too often they say, oh, well, I'll put a little supply and I'll put a little return, and they do them right at the furnace. So they'll put a little small return air grill on one side of the furnace, and 8 feet away on the other side of the furnace they put the supply grill. And guess what that does? Nothing to provide a little bit of circulation through the whole crawl space. So what I like to see is just a little 1-inch hole or something in some boots around the perimeter of the building, you know, the HVAC boots where they're blowing up through, and just a little bit of air blowing in around the perimeter, and then towards the middle you have your transfer grill or you have your return air, you know, a small return air grill in the system if it's down there.
Yeah, why don't they address that, and then the air stagnates in the corners?
Yeah, the air's, it needs to be cleaned up a little bit. And when we say they, who's they? And you've heard me say this before. They need to address it. Who should fix the code? Us. You and you and you and you, right? If you want to fix the code, I've been whining and complaining about cutting holes in the wall for combustion air, and Wendy Johnson and I, who used to be at Midway, we complained about it together, and so what did we do? We fixed it. We fixed it in the code.
I thought you were going to fix that, make it like the IMC so it ran continuous.
You're supposed to fix that. If we see this, we got to be real careful. I'm going to have some more slides on that. I talked just a few minutes ago about combustion appliances. right here is a 80% efficient furnace. You'll notice it has a little inducer motor right here, and the inducer motor's in the middle of the upper half of the furnace, and the burners are just below it, above the blower compartment. It has the discharge where the B vent connects, right on top there of the furnace, and you'll notice that's a 4-inch collar, and then it has a little 1.5 by 1.5 square hole. Why is the hole from the fan so small? Because the fan in the furnace is what we call an inducer fan. It is pulling the products of combustion through the heat exchanger, and it has to go back and forth a couple of times. So it's pulling those products through. We're having the heat transfer, and then it discharges into this bigger vent. So is that fan pushing it all the way through the roof? No, it's not. It's discharging it into that vent, and then it's relying on the heat, that 20% of the heat that's wasted, and taking it up through the roof. So that's what carries the products of combustion, is the wasted heat. By what? By stack action that we've already talked about. This sealed direct vent furnace has the burners sealed in a compartment. Fresh air comes in the top. The burners are in the top section there. The air is pulled down through the heat exchangers. And as you look over on the right-hand picture, air comes in high and then it discharges out and goes outside. That is a direct vent furnace. It is sealed from inside the house. So the code requirement that changed in 2018 that says we don't care about makeup air for the kitchen range hood, because if you put in direct vent, you've eliminated the hazard. We don't have a carbon monoxide hazard anymore. We can't reverse the furnace because the furnace is sealed from the rest of the house. So we're not concerned with that. If the installer chooses to only put the exhaust pipe on the furnace and doesn't run the air intake or the combustion air pipe, then it is not a direct vent furnace. It's not a sealed furnace. It has to have combustion air, and all the rules apply, and we do have the potential for a hazard in the house because the furnace isn't sealed. A sealed furnace or a sealed water heater, the flame does not see the internal environment of the house. It's completely sealed from inside the house. Okay, let's talk about ventilation for a few minutes. We've mentioned it several times. We've talked about putting in a fan to exhaust a little bit of air. And this is all about providing some fresh air. We build the house tight enough that we need some fresh air to maintain air quality. You ever noticed how if you have a big room with a lot of people, and if it doesn't have good ventilation, it gets stuffy and you can't, you're lethargic, you get sleepy? That's because we've got too much carbon dioxide. We're breathing out all this carbon dioxide, and it's not healthy for us. So we want to ventilate it. So here we have our supply-only ventilation system. Now this might be your furnace, or it might be a fan all by itself that brings in some air and it discharges a little bit of fresh air in a couple of places in your house. Now we're not going to do this in our cold environment because we don't want to blow cold air straight into our master bedroom. So we'll do it with our furnace, pull it into the return, mix it with the other air, and then discharge it through our regular registers and grills. This is a supply-only positive pressure ventilation system. So we're taking the pressure inside the house positive, and what's it going to do? It's going to leak air out that we push out through the walls and the ceilings and wherever we have a hole in the envelope. With everything we've talked about before, would we consider this a good ventilation system or maybe a bad, ugly ventilation system? I'm going to say it's probably the bad, ugly ventilation system. Why? Because we are pushing air into our outside walls. And what does our air transport? Transports moisture into our wall cavities. And that way we're increasing the likelihood that we have condensation occurring in our wall cavities. Now you could say, well, I'm going to have a vapor barrier there and it's going to stop it. And we'll talk about that a little bit more, but I don't think it's going to. So my least favorite ventilation. Now, this building has supply ventilation, but it also has exhaust. And I don't even need to go up and look at the mechanical equipment to guarantee that, because this is a VAV system, and I know it's bringing in some outside air, and it was going to have some power exhaust that's running and exhausting air out of the building. And there's controls that are trying to maintain probably a slightly negative pressure in the building. And it's what we do on large buildings like this all the time, and it works quite well. So the HVAC system can provide some, and we supply it, but if we couple it with an exhaust also, then we have a balanced system. So our negative pressure or exhaust only system, whether it's a single fan in the master bedroom, a fan in the hall, or whatever we might do, sometimes we might see a central fan that's ducted into all the bathrooms. That's okay. That's a negative pressure system that exhausts air out of the space, and what does it do? It leaks air in to replace it through the walls. Now, if we're leaking in through the walls, is the moisture we produce in the house going to impact the wall cavities? No, because we're leaking in and exhausting the moisture. So we're bringing outside air in through our wall cavities. Our air's dry. If anything, we're going to dry the wall cavities a little bit, and we're going to discharge to outside. So if this is the poor man's ventilation system, this one I like. Please.
With the exception, say for instance, if you were doing this on a rainy day, it would be bringing moisture in with the air through the wall cavities.
Okay. The question is, if we're doing this on a rainy day, we're going to be bringing moisture in with this type of ventilation system. And you're exactly right. But in our climate, how many rainy days do we have? Not very many, do we? In fact, when's the last time it really rained any amount? Months ago?
About a week ago.
Not very much. I just got enough to make my car dirty. But anyway, and guess what? When it's rainy, it's typically not so cold that we have the issues, right?
Now, how would this affect our area in the wintertime, though, with this particular system?
Okay, in the wintertime, good question. So what's going to happen? In the wintertime is when we have the biggest risk of condensation in our wall cavities. So in the wintertime, what's our air outside as far as humidity? It's dry, dry, dry. The moisture drops out of the air because it condenses out of the air. Cold air can't hold very much moisture. It really struggles to hold any moisture because it drops out. And it drops out and it settles on my windshield and it settles on my lawn and everything else. So we bring in that cold air from outside and it's already dry. And as it comes in through and it starts warming up, it becomes even drier. And so we actually get some drying effect in the wintertime as that comes through. I'm not saying that it's a really terrible thing if we get a little bit of moisture in our wall cavity if it has an opportunity to dry. You can get a little moisture, a little water on a piece of OSB, and if it's allowed to dry and it's not saturated, it'll be okay. But if it's wet all the time, then it's gonna go bad. So we want to prevent as much condensation, and then we also want to give it the opportunity to dry, which kind of gives me pause on the vapor barrier. So this type of system is a pretty good system. It's the poor man's system, if you want to use that term. But every house in Utah should at least have this on it. The really good fans, maybe a couple of $100. You can add controls to them. They make them really nice fans, and they work. So the physics of it suggests that this is a better plan, correct? because we're going to dry the cavities rather than wet the cavities in the wintertime. And then our ideal ventilation system is that ventilation system that exhausts and supplies at the same time. For whatever we remove, we replace, and we have a balanced ventilation system. Now, when I installed these, I like to put them in so the house was slightly negative. Now, the only risk with that ties back to the radon systems. If your house is slightly negative and you have a radon issue, you need to address it because it'll actually draw a little bit more radon into your house than if your house is positive. So that's one of the positive features of a positive ventilation, is that it helps counter the radon issue. But let's not lose track of something here. What are we doing when we have a ventilation system that's running all the time? We're reducing the moisture in the house. You know, that we haven't talked about that, and that's kind of my part 3 on this, but when we have a ventilation system running, and the code defines our ventilation systems as whole house ventilation systems that run continuously, or they run for 1 hour every 4 hours at 4 times the rate. Or you can run it at 2 hours or an hour every 2 hours at 1/2 the rate. At 2 times the rate. So what it's basically saying, we come up with a number. Let me describe it this way. If we have a requirement for 50 CFM continuous ventilation, then we put in a fan that runs at 50 CFM. And it runs at 50 CFM all the time, 24 hours a day. If we want to, the code will allow us to say, well, I only want it to run 1 hour every 4 hours. And so every 4 hours it's going to run, but it has to run at 200 CFM so that it averages 50 CFM per hour. Or you can run it for an hour every 2 hours at 100 CFM so that you still average 50 CFM every hour. If we're ventilating as it says, it's going to work. If we ventilate by saying, well, I'm only going to turn it on when I'm there at the house, or I'm only going to turn it on when we're awake, or I'm only going to turn it on at night, we're not addressing the issue. We're not controlling the moisture because we're only ventilating at certain times. Whole house ventilation systems are based on ventilating all the time at a very small rate. Okay, who knows what this picture in the upper right-hand corner is? Give you a hint, it usually has a hose hooked onto it and goes over to a big propane bottle. Salamander heaters, you guys too young to have seen those out there sitting in houses all the time? Drywallers used them all the time. It's just a big burner in this barrel with a top on it, and the drywallers used to use them all the time. They'd bring them in, set them in the house, turn them on, and heat up the house so they could tape in the wintertime.
We used to burn fuel oil.
Yeah, and then they have the torpedo type that burn fuel oil.
World War II.
Yep. I have one of those sitting in my storage unit. They put a lot of humidity out, don't they? This building's over on 5th East and 45th South. And I actually went on Google Earth and got a picture of it because I spent several months in 1976 working on that building. And I remember the year because it was the year my first son was born. And we had the new model energy code come out in the mid-70s. And that's when we first saw what we called MECCheck. And that was the predecessor to ResCheck. And that's when I first learned about energy code. And I actually, as an HVAC person, did some MECChecks for some of the builders that we did work for. Well, the people that were writing these model energy codes didn't have the experience with building science that we have today. And they concluded that one of our big risks in our buildings is the air leakage and the diffusion of moisture through our walls. And the diffusion is the moisture that would just move through a piece of sheetrock, slowly through that sheetrock.
You want to find out how these older buildings were ventilated, go in that old Arbax building up there in downtown Salt Lake.
It's probably gone, isn't it?
It's still there.
Yeah. Well, let me go on. So this building, the new code came in and they said, you know what, we want more than a vapor barrier on the walls. We want a vapor barrier on the ceiling. So this was the fourth building of 6 or 7 that we did there. And so the drywaller, well, the insulator came in and insulated and put a vapor barrier around the whole thing, put it on the ceiling too. The drywaller comes in, we're all working in this building, and I thought, well, this is kind of silly, this vapor barrier on the ceiling, is that going to work? And, but it was going to make the building tighter, it's going to make it more energy efficient, right? So the drywall guy comes in, and I still remember his name was Mike, and he was one of those piece rate drywall hangers, so he was running all the time, man. He was hanging drywall so fast. And he hung all the lids, did all the walls, had his salamander heater running to keep it warm while he worked, put on the first coat of mud, left the heater on and went home. We all get there the next morning to go to work. I was working down underneath, and guess what we found when we walked in the door? Sorry?
Wet.
It was wet. Guess how wet it was? It dropped the ceilings. It dropped the ceilings right down on the floor.
That was in this building here.
It was this building right here. And it was just it was like a quarter of the building. They were doing TIs, you know, the building was just being built, and they were finishing this first space for a customer, and that dropped the whole ceiling right on the floor. What happened? Stack action, heat flow, airflow, and another piece of building science that we haven't talked about yet today, and Rob alluded to it a little bit. What's in propane and natural gas and wood and everything else that we burn? What do we call them? We call them hydrocarbons, right? A hydrocarbon includes hydrogen and carbon. And then what do we do when we burn them? We combine them with what? Oxygen. So we have carbon, hydrogen, and oxygen. Now, if you burn a hydrocarbon and you don't burn it complete 100% with lots and lots of oxygen, one of our byproducts is CO. We bond carbon with oxygen and we get CO, which is carbon monoxide, which will kill you, right? And then if we have a little more oxygen, we'll get not only CO, but we'll get CO2, which is carbon dioxide, and it won't kill you, but we can't live breathing just carbon dioxide. That's what we exhale, you know, after we take oxygen out of the air. And then we have the whole issue with carbon dioxide in the atmosphere, which we really aren't worried about on this discussion. So we have carbon monoxide and carbon dioxide, so we're using carbon and we're bonding it with some oxygen, and then we have all these hydrogen atoms left over. And so what does the hydrogen bond with for the last major byproduct of the combustion process? It bonds with oxygen. And when we have hydrogen and oxygen, and we take one hydrogen atom and we take 2 oxygen atoms, I'm making you think about high school, Patricia. One hydrogen, 2 oxygens, we have 2 hydrogens, 1 oxygen, H2O. Brittany just said it, water. That's the chemical reaction of combustion. Carbon monoxide, carbon dioxide, and water. we get those 3 byproducts and then some other crap depending on what we're burning. But we are guaranteed to get those 3 every time we burn a hydrocarbon. And so when they had that heater running inside, we not only had the water from the sheetrock mud, and the first coat is the heavy coat, isn't it? The corners, they put a big heavy amount. The seams, they put a big heavy amount. Then after that, the finishing coats is a lot less. So there's 10 or 15 gallons of water in drywall mud stuck on there, and then we add a whole bunch more gallons of water from all the propane that we just burned with oxygen, and we have air and heat transport carrying moisture straight up, saturate the ceiling, and in a matter of hours, the ceiling falls down. It's building science. This is at a grand scale of the things that we're talking about. We're talking about a smaller scale, but it's the exact same principles. We are doing things in our buildings that are creating moisture, and then we're not controlling how we get it out of our buildings. Things like that, you know, I can't remember lots of stuff about my HVAC career, but that's one of those things that you don't forget walking in that building and seeing. And it was probably twice as big as this room, all the ceilings sitting on the floor. So we learned some hard lessons from those tighter buildings in the 1970s. What we learned is we can decrease our energy costs and our air leakage with some of the things we do, but if we're not careful, we're going to increase the moisture problems, the indoor pollutant levels, the health risks, the mold, the rot, and the occupant complaints. And back in the 70s and 80s and 90s, and it still even occurs nowadays, but there was a lot of discussion about sick building syndromes. We have unhealthy buildings. We're containing everything inside. And it's kind of been brought back to the forefront right now. Is our ventilation systems set up and maintained so that we're maintaining a healthy building? Maybe in some cases, but maybe not. Maybe the next code cycle we're going to see some new requirements, or we're going to see some improvements on our code to ensure that our building ventilation systems work right. Now, my thought is we don't have to do a lot to the requirements. We have to do a lot to make sure we're following the requirements and we're ventilating our buildings correctly. Because the things that are in the code, the things that are in the standards, the things that are in ASHRAE are really pretty good. But we have to apply them, and then we can address those things.
You had your parents hold up in, Bill.
My parents used to live in a place that brought in a little bit of ventilation air from outside and introduced it into the hallways, and then it came into the units. But they didn't have operable windows, and they didn't have exhaust, and so the ventilation was kind of poor in that building.
When was that, Bill?
70s.
Was it?
Patricia.
I wasn't born yet.
Patricia let us know that she wasn't born yet, and I know Brittany wasn't born yet either. So there are some youngsters around here. Rob, too, right? Well, I was born.
With the HVAC in Brigham Young's place.
Yeah.
Well,
And aren't I doing well for being that old?
Looks pretty good.
Balanced energy efficiency and indoor air quality. So we need to find a balance. And some people might say we're doing too much on the energy code. We need to find a balance. Well, that's why the code isn't more advanced than it is, because there's those groups that are holding it back a little bit and saying, let's not quite go so fast. And I'll be honest with you, I'm one of those people that for the code, for the energy code, we had some big increases in the 2009 and 2012 code, and when the 15 codes came around, I'm one of those that says, whoa, 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 let's slow down a little bit and let's make sure we understand what we have in the code and make sure we're applying the principles that are in the code before we make it even more restrictive, or more aggressive, I think is probably a better word. There's some that want to see the energy code improve 15% every year, every 3 years, or 5% every year. And I think it's just a little bit too aggressive because we're having a hard time catching up to where we are right now. So, if we get that right balance, we have acceptable indoor air quality, decreased health risks, reduced complaints, reduced moisture levels in our structure, and we have a healthier building than a leaky building, and we're able to control the moisture. So here's a better picture of the crawl space that has mold. Less than 6 months. And the issue was the crawl space vapor barrier was not installed correctly. That was the big factor. It looked,
Was the mechanical system never run?
the big factor was the vapor barrier on the crawl space only went to the edges of the footings and did not run up the wall and wasn't sealed to the wall. And so we had constant moisture coming up around the edges of the 6 mil vapor barrier. And it wasn't taped at the seams. And if you rolled the VisQueen back, it was soaking wet underneath, and it was actually muddy underneath because of the moisture that was collecting on the bottom of the VisQueen. And yes, the ventilation system wasn't left running. It should have been set so that it was continuously operating.
That thing was right by the river too.
And it wasn't far from a river. And so the water level, the groundwater, was higher than you might expect. But you know, we really need to take out of our head that we're in a dry climate and we don't have water in our ground. I live on the other side of the river. We're in Sandy City Hall, right? And we're just up out of the east side of the Jordan River, river bottom area. So we're up out of we're 50, 60 feet higher than the river right here. I live on the other side in South Jordan, just about 13th west. I'm up out of the river bottom, and I have groundwater underneath my house at 4 feet below, 4 to 5 feet below my backyard. My house is raised up so that it's not in the water. But I go 400 yards east of my house, and it drops down into the river bottom. There's a layer of clay there water comes clear from the Oakers all the way across, and it doesn't surface until you get out there to where it slopes down. You would think I'm way above the river bottom. All the moisture in the ground's going straight down. I'm not going to have any water, but I have water really close to the surface. We have the moisture in the ground. It doesn't have to be close to the river for us to have that moisture coming up into our houses. And remember me talking about the three methods for doing a crawl space? This one they tried to do the building science method, but they left out a couple of pieces. And because they didn't get it exactly right, the result is potentially pretty catastrophic. That's pretty serious if you leave that going for a long time. Did they fix it? Yeah, they fixed it. They brought in, they dry ice blasted the mold off, and then they put a mold treatment on it, and then I believe he sprayed foam on the rim joist, and you can see that the rim joist is much worse than here. Why is that? Because that's that weak link, and all it had was a little piece of rim joist insulation there. If they had had the rim joist spray foamed, they would have still had a little bit here, but they wouldn't have had any of it back there behind that rim joist insulation. Airflow can transport moisture into ceilings, walls, and other frame cavities. And we don't even know we have the airflow, and that's why I've spent a whole day talking about that airflow, heat flow, and moisture flow. Moist air contacting a cold surface may create condensate, and it doesn't have to be that cold. This area wasn't that cold. Yeah, it was a little cool because they had the heat turned down. But do we have to have really cold temperatures to get condensation? No, we don't. We just have to have the right combination of humidity in the air and temperature. Back in the old days, when I was younger, when I was 8 years old, my parents used to let me and my buddies, we'd sleep outside all the time. Grab a sleeping bag and sleep outside. It was great. Lay there, look at the stars. I still remember it from 60 years ago. And guess what? Some mornings we'd wake up and everything's nice and dry, and some mornings we'd wake up and what? We had a heavy dew, and my bag was wet and the grass was wet. And it wasn't cold, and it wasn't hot. It just, the conditions were right for the moisture to condense. We hit dew point. And so we hit dew point in our houses all the time, even when we think we might not hit it. We're hitting dew point, and these conditions occur. Wood rots when it absorbs 30% of its weight by water. OSB delaminates even earlier than that. But when you get wood wet to 30% of its weight in water, it starts to rot. What are our solutions? It depends on where we are. We need to do proper air sealing and stop the airflow. Remember I said stop the airflow, not the vapor flow? We need to mechanically ventilate, and that removes the excess moisture, and insulate to minimize cold surfaces. And continuous insulation is one of those things. So in this house, we had a vapor barrier problem on the ground of the crawl space. We had a ventilation problem because they didn't have any circulation in the crawl space, and they weren't exhausting out of the house. This was built when the code said we need to have continuous mechanical ventilation. If they had a fan up in the house always running, at the size of that, it probably would have been about 70 CFM. The level of humidity in the house would have been much less, and the problem would have been much less.
Did they do a blower door on that thing?
I have no idea if they blower door tested it. But we had enough things wrong that we had the condensation occur. So there is the spray foam in the rim joist. If you do that, if you don't blower door test, they should be doing that. That's their choice by not blower door testing. We didn't take our break, did we? We got so excited about talking about crawl spaces and mold and how old I am. Let's take a 10-minute break. All right, welcome back. We have a bunch of slides to get through and not very much time. So we're going to kind of move along a little bit quicker here. We'll kind of rein in some of the audience, the live audience here, and move forward. Brittany wants me to let everybody know that's out there on the web, if you want credit for this class, you need to send her an email. And you got her email from, she sent you the link on how to join on here, so just reply to that email and she will make sure you get your CEUs as appropriate. All right, duct leakage. Okay, we've gone back and forth and we've talked about all the ways that we can create pressure differentials in our house, and we understand that when we create pressure differentials and we have holes in our house, our building, we're going to have air moving, we're going to have heat moving, and we're going to transport moisture into areas that we might not want it. So one of those ways that we can create those pressure differentials, and it ties in with your cold basement, is leaky ductwork. We have an attempt to seal some of these ducts, but it's a really poor attempt. And in fact, the problem is the upper picture there. They've dovetailed that elbow into the top of the duct for its takeoff, and they haven't closed the gaps. Anybody that's ran a piece of duct knows that you can close those dovetails a lot tighter than that. You can show a little craftsmanship and make a tighter joint to start with, then it doesn't take much to seal it. The bottom picture here, we have a piece of rectangular duct, and they couldn't get that corner to go together quite right, so they didn't push the drive cleat up far enough. They only sealed, if you look closely, they only sealed the duct where the inspector might see it below, and they didn't even make an effort to seal on top.
They do a bad job on those furnace replacements too.
Yep. This is just a horrible job. I can't imagine anybody not having enough pride to at least make a complete tight joint on their duct system. That's terrible. But so
Furnace replacements, when they replace the AC coil, they put some tape on.
yeah, they just tape it. So what does this do? This creates pressure differentials. So we have air moving in areas we don't want. We might be positive pressure in a room. Your basement, you probably have a bunch of this stuff down there. And so he wants to air condition his house and he wants it to go up where it's warm. And it's leaking just like a hose leaking right at the hose bib, right at the source. We're leaking out all this cool air and it's not getting to where we want it to be. So it's warmer up there and it's leaking down into the lower part where it just lays in your basement, and your basement's always cold. It's not very hard to figure out, but that's exactly the condition that you have. So even though the duct's inside the thermal envelope, we can create problems, we can create pressure imbalances, and we're reducing the airflow to other areas of the house. So here's some ductwork in a garage. And you remember we had a picture early on of the ductwork that had the bad insulation around it. If someone puts bad insulation in here, they are just going to put bad insulation on the bottom side. No one is going to go in and work insulation down the sides of the duct. And so what we end up with is a furred down cavity or chase for that ductwork, that we have insulation on the bottom and we don't have any insulation on the side, that 1 foot drop or whatever it is. So it's, maybe we should tell them, wrap all that duct with R8 insulation first, because if they just put bats in there, it's going to be poorly insulated, and we're going to have all these cavities where they're open air, aren't we? I mean, we know we are when we remember that picture earlier. So there's one way we can do it that I think is a great way to do it.
What about ductboard on the interior?
Putting ductboard instead of metal duct?
No, if you have the insulation on the inside of the turn.
Inside, oh, on the turns? I'm not sure I understand your question.
Installations like this, where they take and do the insulation on the inside of the run
Oh,
rather than the outside.
Okay, duct liner. Yeah, duct liner. You can put duct liner on it, but standard duct liner is like 3/4 of an inch, and it's maybe, well, it's R2 something. If you get full inch, it's R4.2. For you to get full R8, then you have to put like 2 inches, and then you have to make your duct 4 inches bigger to account for the duct the thickness inside, and it's really expensive to produce. So, I mean, I built a lot of line duct, and I lined a lot of duct for acoustic reasons, but in this application, I think this is probably a really good choice, is to net and blow that whole thing full. So we are filling up all the joist spaces above, and we're just completely encapsulating it in insulation. And that's a nice system. And you can just look at that and say, well, yeah, that one's going to work, can't you? That's a good system. Cantilevers, proper installation, the gaps, the air movement, we already talked about that one. Here's some more pictures on those cantilevers. Look at all the holes that we have. It's extremely critical that we address the air sealing on these if we want to have our building work properly and we minimize those airflow issues. Overcutting the boxes, if they're fitting a little tighter, they're sure a lot easier to seal. The Tyvek probably isn't going to seal that overcut hole. Remember that branch duct that went out over the insulation? Just not a good situation. Not insulated, the duct is not insulated properly. The previous slide we were looking at the cantilever itself, now we're looking at the duct. There's not a minimum R8 there. Again, that would be better net and blow. How about this penetration? If they come in and stucco that, the first thing the HVAC guy is going to have to do when he comes back to put the termination cap on it is he's going to have to break the stucco out, destroy the air barrier, because those two pipes need to be exactly a 1/2 inch apart for the termination to fit on. Now, you wouldn't know that, but he should know it, and he should have put something on there that spaced them right. I mean, I would have fired a guy if he would have done that, because I'd make a mess trying to do the finish on the house when the coverings are on. Effects of airflow on energy efficiency. This is a good job. What have they done? They've got this spot that opens into the attic, and so they've put drywall on the back side so that we have our air barrier, so they insulate it, and it's taken care of. Airflow, if we have infiltration, it increases the air leakage. We have to replace that. Mechanical ventilation, we already know how that solves the problems. Then we have some airflow that doesn't increase air changes, and that would be airflow in that wall. It might not increase the air changes, but it decreases the effectiveness. That wall on the drawing there where we had the knee wall. And so we have airflow that impacts our ventilation or our infiltration, and we have airflow that impacts our insulation. Does both. So the big thing we got to do, summing this part of the section up, is we need to control our leakage. And it's going to take some caulking and sealing and foam, but we got to control it. So we talked a little bit about the blower door already. Here are our options. Spend some time on this. We either have to do the blower door test and meet that 3.5 air changes per hour, or we have to go through every item on this checklist. We don't have an option to not meet all these unless we blower door test. And one of the items on here is rim joist shall include an air barrier. We have to have an air barrier with our rim joists. Blower door testing versus the table, and we've already talked about this a little bit. and so I'm not going to spend too much more time on it. If the builder does not want to do the blower door test, he has to comply completely with that table. These are the things we mentioned. And here's that summary of that table. And everything on here is stuff that we've talked about. All those are the items that we've been discussing on how we need to seal the envelope. Speaking of they fixing the code, this is one of the things we fixed. If you have a mechanical room with the open combustion furnace, the open combustion water heater, combustion air coming in from outside, that is supposed to be enclosed in a room. Isolated from the rest of the house, a door with a weather strip, a door, with a threshold and all that. Isolate it from the rest of the house. I do not require a exterior door with foam in it. An interior door with the big airspace and everything in it really meets the fenestration requirement. It is around a 0.3 U factor on that door. And the exception is direct vent. If we have those direct vent appliances, we don't have to create that sealed room. We discussed briefly before what direct vent is. This is a direct vent furnace with a sealed upper burner. The one on the right is a direct vent furnace with an open burner. That one does not qualify as a direct vent if you don't seal the holes in the side of the furnace. And I think, well, maybe I don't have a picture in there. Furnaces that are built like this, they have a rubber grommet that has to go on all the penetrations. And if they don't put the rubber grommets in, it's not direct vent. It's opening the house to inside the furnace. And you need to verify that that's truly a direct vent furnace, and this one is because it has that sealed burner compartment. So summarizing our mechanical ventilation real quick, because we've already talked about it, and I got some pictures I want to go through before we call it a day here in the next hour. Here are our 3 ventilation choices. We positive pressure it like we talked about before on the bottom left. We can suck in a little bit of outside air, introduce it into our house, and we're bringing some fresh air, and then we leak out the excess air. And that's how we get our air changes. But that's also pushing air through our building envelope, which we probably don't want to do. The next one, the middle, is that fan, that ultra quiet fan. And those fans are amazingly quiet. You might have done inspections where you went in the bathroom and there's the fan in there and there's no switch for it. That's because the fan is running all the time and you can't even hear it. And it's constantly doing a little bit of that exhaust. And that's the one we spent some time talking about. And then the HRV, ERV that we've brought up, but we really haven't described how they work in detail. It's an exhaust fan and a supply fan in one box, and it has a heat exchanger in there. So if I'm exhausting 72-degree air out of my house in the wintertime, that 72-degree air goes through a heat exchanger headed to outside. At the same time, the fresh air coming from outside comes in through the heat exchanger and goes through the other passes on that heat exchanger and grabs the heat from the exhausted air. And so we have an energy or heat exchange. As the warm air is being exhausted, we use that heat to warm the cold air that's coming in from outside. If you want more information, Google ERV and HRV, and it will tell you about the differences between them. Air handlers and ducts in the attic. If you have an air handler in the attic, you have to pressure test your duct, period. If you have, as of right now, if you have 25% or more of your duct in the attic, you have to pressure test your duct. So if you have even a small portion of your duct in the attic, it has to be pressure tested. And this is not an option. This is not tied to the blower door test. This is a requirement that if you have ducts in attics, that we pressure test it to make sure it's not leaking, because what happens if it leaks? We're throwing away air that we just spent money to condition. Duct insulation on all sheet metal, we talked about that. A platform per the code. Now this is not a very old installation where I took this picture. I'm not going to say what jurisdiction it's in, but there's no platform. A mechanical contractor that crawled in many attics wading through the insulation, that's ridiculous that you can't service the piece of equipment. If the air handler alone's there, we got to test it, or 25% of the duct. And how do you test it? You just have a little blower that you pressurize the duct system, and that number has also been amended so it's weak. So we are allowed to leak too much. Again, if we have the ducts in the attic, we have to pressure test them. And let's think about it. The way the code's amended, and actually it changed a little bit. Now, I made this slide when it was 8 CFM per 100 square feet. A 2,000 square foot home would be allowed to leak 160 CFM. That's a lot of air to be thrown away. That's a bunch of air, isn't it? Well, it's tightened up to 7 CFM, so that number is still 140 CFM. Do you want your system to throw 140 CFM of heated or cooled air away every minute of operation? No, that's a lot of heated air. I don't think it's unreasonable to expect a tight duct system. There are companies that test ducts that will give you a report. There's companies that actually seal the ducts from inside. They spray a mist in there that work real well. Sealing attic air barriers. This picture is a little bit hard to see, but we have scissor trusses, and then we have all these drop ceilings all the way around it. So they have the high ceiling through all the living space, and then they drop the ceilings over halls and bedrooms and all these areas. And what the code says and the table requires is we really don't have to do all of this if we do this. All of those fur downs, every place we have some type of fur down, if we put a lid on top of it, seal it, what does that provide for us? Our attic insulation is continuous all the way across the top of all that. If we go back to this one, how are they going to insulate these? They're going to blow insulation here, then they're going to put insulation in here, then they're going to have insulation going across here, and they're doing the same thing over on the right side and over on the left side. And so we have all these ups and downs, and how do you seal those well? Every time we have those transitions from horizontal to vertical, we have another spot that's going to leak air and another spot that the insulation might be weak. So it's much better if they just took this plywood and put a lid above up against the bottom of the truss and then insulated completely over the top, so we had a nice, straight, clean air barrier, thermal barrier right across the trusses. If they don't blower door test, they have to do this on top of all of them. Again, a leaky box. Here is terminations for a 95% efficient furnace that they put the little collar on it so they at least have the spacing. So when the weather barrier is applied and those are sealed up, it will provide a better seal with having to tear the stuck wall apart. Also nice to note is they put a little wall flashing on there for the refrigerant lines so that the weather barrier can be shingled in with the flashing there. I made a note here, and maybe you can't see them real good. On your handout, maybe a little bit better. One of the major sources of leakage on your duct systems is around your furnace and your air cleaner and your return air connection, and I have arrows pointing at all these places. I might have shared this with you before. If I were to go home, and let's keep it simple, and tear the motor apart on my lawnmower and do some work on it, replace some parts, put it back together. Would it work well if I did not worry about gaskets and I just put it together and then I smeared sealer around the outside of the engine? No. It's stupid, isn't it? It's ridiculous. It's not going to work. So why would we take an air conditioning coil that has a flat mating surface that's like 5/8 inches wide and a furnace top that has that? Why would we not put a bead of silicone type sealer down, set our coil cabinet on it so it squashes and forms a gasket, do the same thing when we hook on top with our plenum, do the same thing when we hook on with our air cleaner, the same thing when we hook our return drop to the air cleaner. The major sources of leaks right at the air handler are taken care of because we took 10 seconds or 20 seconds to apply some type of gasketing sealer before we put it together. I have no patience for whining that it's really hard to seal ductwork. No, it's not really hard to seal ductwork if you are conscientious of thinking about it as you put the ductwork together. Those takeoffs that we looked at before, those are hooked into the duct when it's on the ground. They're not put in when it's up. You cut them in and then you put up a section of duct. You measure and cut in the next one, you put up a section of duct. It's real easy to seal them while it's on the ground. Just a couple of pictures. You might not be able to see them real well, but we got water lines and all kinds of stuff running through this return panning that it's just almost impossible to seal. We have the leakage at the cantilevers. I'll jump on. They started sealing, but they didn't complete it. They didn't complete the elbows. This one they did, this one they did not. This is a bigger view of that previous picture. Now there's no pride in that work, is there? Selective duct sealing. They seal some spots and then they don't seal others. That's really interesting. The code, the 2015 code actually says we're supposed to seal this seam right here. The seam, left-hand picture, the bottom of that pipe. The 2018 code, they decided maybe that was a little bit of overreach. That seam doesn't leak. We didn't adopt the 18 code. We're still in the 15 code. That's up to you if you're going to let them get away with the 18 code, and I don't have a problem with that. Almost none of this duct is sealed, but then you go over and then some spots are sealed. It's important that we seal the duct. Filter cabinets. You notice the big filter cabinet. I'm just going to put in a plug real quick. If you ever change your system out, ask about thicker, high-efficiency filters. Those little cheap, well, they're not cheap, those little expensive 1-inch pleat filters that you pay $15 or $20 at Home Depot are so restrictive that they don't work well with your air conditioning. You don't get enough airflow through them. So if you want a good filter that's going to remove viruses and all that stuff, you're going to need to go with a wider, thicker filter that's not so restrictive. Ensure the furnace has a sealed burner and seal all the penetrations. This is the side of a furnace. We need to make sure these holes are sealed. Here's some duct sealing. Some of it's poor, some of it's better. Here's one that's just horrible, that upper left and the bottom right. Those are terrible. If you're inspecting and you don't want to carry around a ladder, you can go to Harbor Freight and buy that mirror for almost nothing. Or if your arm's long enough, you can take your cell phone up and shoot a couple of pictures of the connections on top, but there's no excuse not to seal those. We already talked about that one, so we'll jump on. Here I have a backdraft damper, and it's hard to see because of the shadow. Excuse me, I have a termination without a backdraft damper. Can we have a penetration with a pipe and exhaust fan and no backdraft damper? Yes, we can if it's a whole house ventilation system that's operating 24/7. If it's operating 24/7, we don't need a backdraft damper. Can lights and boxes in ceilings are supposed to be gasketed and sealed. Here's a cantilever. Do we know if it's sealed or underneath that soffit or not? And I threw this one in just because it was wonderful to see. They have an actual return in every bedroom of this house. We have a return path.
If you don't, how big should the gap be at the bottom?
Okay, great question. If you don't have a return or if you don't have transfer grills, this is why a load calculation is important in a duct design. I have a table, I didn't put it in here, but Manual D has a table that we put in it when we rewrote it a couple of cycles ago that tells you how much you have to cut your door depending on the CFM. So if you only have one 6-inch supply around 100 CFM, you need to have about 1 inch. If you have, and send me an email and I'll send you the table, it's great. If you have like 400 CFM or 500 CFM and you're trying to draw it under a 3-foot or a 2.6 door, you have to cut your door off like 5 inches, which no one's going to do. But we put it in the book because everybody says, oh, we're just going to draw it under the door. Well, you can't draw but more than one supply under a door. That's it. And I can send you that. And Manual D is while we're on it, is Manual D code. The code in chapter, I want to say chapter 15 in the IRC says duct systems shall be designed in accordance with ACC ANSI Manual D. It's a reference standard in the code, and so it's code. And actually, if you go to the return air section in the IRC and in the mechanical code, it even now says the same thing. You have to have return for all the supply that you put into a room. So both Manual D and the code address it. Manual D has the table, which kind of makes it obvious that an undercut doesn't work. Someone mentioned earlier that Garbett Homes sprayed a little gasket material around all these places that we see in this right-hand diagram. Because we have a lot of leakage, you put sheetrock on both sides of a stud wall, an interior wall, it doesn't seal tight to the top plates, and so we have a lot of leakage through there, and blower door tests show us that. And so in this case, they're taking this little strip of white foam, it's kind of like seal, and they're just staple it along the top plates there, in this like this location here, and when you put your drywall to it, it creates a gasket, and it seals the leakage through those top plates. Real quickly, if we have a unconditioned storage space under a porch, we need to put a wrong button. We need to make sure we have a threshold and a weather strip on the door. I don't mandate an outside door, again, because an interior door with the air spaces and stuff in it are okay. The unvetted crawl space, we need to make sure we have the vapor barrier, it's sealed, we have the spray foam, we have the insulation on the wall. Otherwise, it's not going to work, and we beat that up. Moisture flow. Let's see what we can get through on this one real quick. Remember we talked about the 4 methods or 4 paths that we see moisture moved. The bulk water, that's the leakage from outside. The capillary action, that's coming up from the concrete into our material. Our air transport, that's the stuff that we push into our walls because we have pressure problems in our house. And we've talked about that one a lot, so we can move forward. And then we have vapor diffusion, and we have not talked too much about vapor diffusion yet. And that is the water that passes through the building material. And what I'm saying by that is, if we had a piece of 4x8 sheet of drywall and we had an opening between like a swimming pool area with high humidity and a dry area, would we have moisture migrate through the drywall? Eventually we would, because drywall, unless it's Den Shield or something like that. But normal drywall, the paper and the gypsum will allow moisture to diffuse and slowly move through the drywall. That's diffusion, and that's what we're trying to protect with a vapor barrier. Now, I'm going to just touch real quick on some bulk water. Here's a large house that they did not work well on the design and installation of the bulk water, and they ended up tearing all kinds of stone. And this is just one section of the house. A huge amount of material came off this house, probably 60%, and you know where this house is too. And it's because the bulk water was getting through the stone. They weren't flashing it properly, and they didn't flash above the windows properly, and they had some issues with it. So let's talk about vapor retarders. Visqueen plastic is considered a class 1 vapor barrier, and it's going to leak 0.1 perm or less of water. A class 2 is between 0.1 and 1, and a class 3 is between 1 and 10. What's a class 3 vapor barrier? Latex paint on drywall. That's a class 3. Now I've kind of alluded to that I don't like vapor barriers on our walls, but I love vapor barriers on crawl space floors. I think they have to be there on your crawl space floor if you're going to condition your crawl space, because we really need to stop that water. And they need to go, if you use wood foundations, you're required to have it. If you have a crawl space, did you know if you read the code closely, if you do that real good, well-sealed vapor barrier on the crawl space and you vent the crawl space, you only have to have 1 foot per 1,500 square feet of crawl space. So you have actually a third option. You can do the normal ventilation, 1 square foot per 150 feet, or you can put down the vapor barrier really well and do the 1 per 1,500, or you can completely seal it, do the vapor barrier and all those things we talked about. Under slabs, we are supposed to be putting vapor barriers under our slabs, and we really should have them taped and sealed just like it talks about there. That's in.
Probably end up with more than 1 per 1,500 because you got to put 1 in each corner.
Yeah, if you put 2 in there, and you're probably going to end up with more than that anyway. But we know that we don't put vapor retarders behind showers and tubs, and we don't do them in basements. But interior wood frame, the code tells us we should be putting vapor barriers in some climate zones in interior wood frame, including the one we're in. And we need to do something in our unvented attics and rafters, and we talked about that. Our vapor barrier is our closed cell foam. And in any case, we need to comply with 702.7, and that's what the energy code tells us. So here is a basement floor that's sealed up real well. And this also minimizes the amount of moisture you get in your house. With that groundwater constantly putting moisture up through the ground, it's coming into our house. And so this is code, and it is supposed to be there. And that's a proper job.
Why is a vapor retarder not required behind tubs and showers?
Why is a vapor retarder not required behind tubs and showers and behind basements? And I'll be honest with you, I'm not 100% sure. Anybody else have any ideas? I know I've been told it for a long time.
The wall covering that Diamondback or...
It creates a vapor barrier.
It's a vapor barrier, so if you put another one on there, then there are 2 of them.
We have double vapor barriers, and
But 9 times out of 10, behind a tub, they'll insulate it, but not put anything to cover that insulation on that wall. So you're only covered on 5 sides.
now let me back up. We don't put a vapor barrier on it, but we should have an air barrier.
Okay, air barrier, not a vapor retarder.
Yep.
Okay.
We should have the air barrier.
Okay.
Yeah, and that's what it was. You're right, Gil. Thank you. We don't want to have double vapor barriers there with materials in between. And in fact, someone would mention to me when we have the double vapor barriers, if we have any moisture between them, they'll never dry. And so that's going to create a problem. But yeah, we do want the air barrier, but we don't want the vapor barrier behind those.
Sometimes if they put it on there, I just have them
Cut
slit
it.
with a knife.
Yep. So here's the code. I took this right out of the code. We're in climate zone 5 or 6 or 3 for St. George, but they don't have the requirement we do. But in 5 and 6, we're supposed to have a class 1 or class 2, which are plastics basically. The exception are those basement walls, below grade portion of any wall, areas that we're not going to have damage if we have moisture and freezing, and class 3, where any one of these conditions in this table occur. And what this table really says is you don't need a vapor barrier down here in the bottom of number 5 and in the bottom of number 6 if you have a certain amount of closed cell foam on the outside. Then they don't care about the vapor barrier. And then it says if you have banded cladding over wood panels, fiber panels, or over gypsum board. So if you have the airspace behind your cladding, whether your cladding is stucco or whatever, and lots of manufacturers are making products now that allow some breathing space, and even Tyvek makes some material that has some, it's thicker and it allows airflow to flow behind there, and that gives an airspace for drying. So the vapor retarders section of the code kind of is understanding the problem, but they're not understanding it 100%. And let me go a little bit further and I'll give you some more details on that. Cladding with an airspace. So here's cladding. We have foam on the outside and we have the battens for an airspace. Basement walls, have you ever noticed the older the basement is, the older the home, the smellier the basement is? Doesn't every old basement smell musty? Every single one of them. Why? Because we don't see it, but the cold concrete has condensation occurring on it. It gets wet from condensation, but we don't see it. Why? Because it's porous and it sucks into the concrete. If we did not have the concrete get cold, or if we had it really sealed off somehow and insulated, then we wouldn't have that issue. And so building science tells us that on the left-hand diagram we can do a couple of things that are really going to help those basement walls. And the first one is put foam on the outside of the foundation. Where you come up to grade, you're going to have to put something like a cement board or a hardy backer type board that you can plaster over to protect the foam. Spray foam your rim joists, and that's going to keep your concrete warmer so it's not going to get moisture condensing on it. And
Spray on water.
huh?
Spray on foundation spray.
Foundation sealer is not going to keep the concrete inside warmer. That's the issue. The issue is we're trying to keep the concrete inside warmer so that moisture doesn't condense on it. The other thing,
So how can you put that board over the top of that foundation water barrier?
you glue it, you pin it. There's all kinds of procedures for it. The manufacturers,
Over the top of that?
yeah, put it over your sealer. Your other option is put something closed cell foam, whether you spray it or you put rigid board and seal it on the right-hand diagram on the inside of the foundation, and then you do your spray foam in your rim. The whole thing we're talking about here, the code doesn't say this, but we do get the condensation occurring on our concrete walls. And it's because the concrete walls are cold. Just something to think about. The effects of the moisture flow, when we have moisture get behind our stucco, then you end up having to tear it off because the OSB is delaminating. We have the mold, we have the allergies, we have the sick building syndrome. Some of them, with the formaldehydes and everything that are in some of the materials in the past, have caused birth defects and everything else. And we have comfort issues. If we have a lot of water wetting our building products, then it's uncomfortable. Here's the effect of moisture. and this is a condensation issue. This building had slab on grade. If you look on the right-hand side there, the exposed part of the foundation in a very cold climate, we have it condensing so much that it's saturated the concrete, and it's even freezing the condensate on the corner there. It's so cold in that climate that you're actually able to see it. We've had this discussion, so let's just move on. We still got a lot of slides. So vapor diffusion, the code typically tells us this. We have a wall, inside, outside. We have moisture inside. You see all my little arrows? We have moisture, vapor pressure from the vapor inside the house, and it strikes the drywall. It tries and will eventually move through the drywall. And that's why we put a vapor barrier, to try to stop that moisture that migrates through the drywall. That's the vapor diffusion. And it is a slow process, vapor diffusion. Eventually, if the moisture gets through, where I have the blue line on the inside surface of the OSB, is where we're going to get the condensation. And we've talked about that today, haven't we? We're going to have condensation occurring there because it's cold surface and the moisture gets to it. And if we're high moisture inside, we're going to have more problems. Okay, Dr. Joseph Stiebrick, you've heard him before. This guy is a brilliant guy on building envelopes and vapor and all this stuff. He's written a couple of guides and books for different climates and different areas of the country. And he shares a little bit of information. A sheet of plywood, a sheet of gypsum board with 70 degrees inside temperature and 40% relative humidity, which is a little bit high for our climate in the wintertime. Over the entire heating season, a typical heating season, will diffuse about 1/3 of a quart of water through that drywall. So for every 4x8 sheet of sheetrock, you have 1/3 of a quart of water go through. But if we have a hole in that piece of sheetrock, a 1 square inch hole. Now, if we have an electrical box in a piece of sheetrock, and if we take that 1/8 to 1/4 inch width of the overcut on the sheetrock between the electrical box, we probably have at least a 1 square inch total opening, wouldn't you say, around that box through the sheetrock. So we have a 1 square inch hole, for discussion's sake, at every penetration of an electrical box in our drywall. A 1 square inch hole in a 4x8 sheet of drywall will move, if we have air leakage and pressure to push the moisture into the wall. Again, the same conditions, 40% relative humidity, 70 degrees outside, 30 quarts of water. Now, what should be our big concern? Should it be the vapor barrier, which will do nothing for this? The vapor barrier, if it's good and tight, will do something for this. It does absolutely nothing for this because it's not sealed. And this is 90 times as much water through the same 4x8 sheet, 32 square foot of drywall. Which is our biggest concern? If we understand this building science, it's the moisture transported in the air that we're pushing into our walls. Now, how do we address it? Number one, we maybe want to keep it a little bit less than 40%. I run my humidifier around 30%. We remove or exhaust the excess moisture out of our house. And how do we do that? We have our whole house ventilation system that's always running and removing the excess moisture. So all those things that we've talked about before are things that we want to do so that we don't have this condition. Make sure the house is slightly negative. Make sure we're ventilating it. Make sure that we are air sealing it so that we don't have all that movement of air. I'm going to give you an example of what happens when this occurs. My good friend Dean Webb, that I work with on some of this investigative stuff in consulting, shared these pictures, and he actually came to one of our classes, and you might remember Carl when he came and talked to us about this. And here's a townhouse project with a bunch of lick and stick stone, as I like to call the cultured stone. And it looks fine, doesn't it? Townhouse project, a whole bunch of units, the chimneys look okay, there's a fireplace in there, past inspection. The problem?
How they supporting that thing
Huh? It's cantilever.
at the bottom?
It's a cantilever, I'm assuming. I don't know.
You got weight on that.
This is that cultured stuff. They've just stuck it.
You still got weight on it.
They've stuck it to the metal lath.
That stuff weighs up.
Yeah. Well, we're not going to worry about that today. You can worry about that.
Bad deal there.
Let's go to the next slide. It's kind of bright, but they took a corner out. So they took one of the pieces out and everything looks okay, right? We see a couple layers of building paper behind it. The metal lath that they pulled out appears okay. We cut the building paper, pull the building paper away, and what do we see underneath the building paper? You have an idea of what that W
Water valve.
that W is on a membrane that they've put across the whole fireplace, and it is Grace Ice and Water Shield. What's Grace Ice and Water Shield? It's a rubberized membrane material that's really sticky, bituthane that you stick on the lower edge of the roof so you stop the ice dams. Is it a vapor barrier? Yeah, it is. It's moisture tight. Moisture doesn't go through Grace Ice and Water. So someone has violated one of the key components of a vapor barrier and put the vapor barrier on the wrong side. They put it on the cold side, not the warm side, in a cold climate. So if you have the vapor barrier on the cold side, it's even worse than just the OSB, because a little moisture might move through OSB, but the moisture from inside gets into that fireplace chase up against the OSB, it saturates the OSB, and it can't dry through. And if you cut the grace off, it's got a powdery mold all over the whole entire fireplace assembly. So they had to tear all the stone off, tear all the grace off, tear all the lath off, tear everything off, re-OSB the thing, and do it properly.
Just that one or the whole townhouse?
The whole project. He had pictures of pallet after pallet after pallet of new stone that was sitting there all over in the project. Everybody's living in it. Hundreds of thousands of dollars to repair that.
It'll all fall off anyway.
Incorrect method used throughout, misguided. Grace Ice and Water is a great product, but it's not made for that. Let's wrap up with a couple of slides. I'm going to try to burn through these in about 15 minutes or so. Here's a shower area that they've used closed cell foam product, extruded polystyrene. They've taken care of the air barrier and the thermal barrier. It's insulated real well. We don't care what they do from there. Here's the vapor barrier installed well in 2 crawl spaces. It's run up, it's taped, it's sealed. It's done a really good job. I threw this one in just simply because one of my friends from down Spanish Fork, Brody, has been sharing with me pictures of stuff he's been running into, and they maybe don't apply directly to everything we've been saying, but is this compliant on this flex duct? It's run down, it's kinked around there, kinked again where it hooks to the boot. If you've listened to me ever talk about flex duct, that is the grossest violation. Here are some TJI floor joists on the left, bottom left, and that they are panning and trying to enclose all three sides of a floor joist system and made no effort to seal it.
Why don't they just put an elbow or something on that metal one?
Well, they should have come through over here someplace. They used the wrong boot. They could, if they had to circle around, use an end boot. Don't use a, use a boot that you can hook in from the end. I mean, they're going to have to fur down for this, and they've crushed the flex. I'm going to jump on to the next one. Here's another view of that house we talked about before. All these fur downs all over in this area. They really should have a lid on top of them, and then you don't have to do any of that stuff because it's all inside the thermal envelope. It's just dead spaces inside the envelope. Here's an area that they at least have prepped the air barrier where they're going to have to do some insulating. The code, without amendment, says that we have to run all of our return in duct. We can't pan any. We can't pan anything. You can't use the framing structure. We've amended that out. However, here's someone that has done a good job of not using panning, putting a return in both sides of a bedroom, and ducting them with pipe and boots and takeoffs, and done a good job. So it's a nice job. It controls the noise. It gives a good return path everywhere. So that's a nice job that meets ACCA standards. A header that allows foam to be put in where this one doesn't. Not as well, but with this ladder blocking on a non-bearing header, you're able to net and blow and insulate it that way. And then there is some ladder blocking here so you can insulate behind that stud. Here's a good thing that put the insulation dam up so that this goes out to a porch so that when they blow the insulation, it isn't all falling out on the porch soffit. You can keep, and it's full depth, high heel truss, so you can keep full depth of the insulation. The insulation rulers at Rough, this goes out into a garage, and the only thing I can assume is they're going to insulate the garage too because they did not put an insulation dam there. But these are things that we should be looking at. Here's the insulation dam coming along here, but they did not extend it here where it goes out over the front porch. But they do have foam in the header. Here it's done the right way. Here is a drop down cavity on the left-hand side, and they have put a lid up first so they can insulate over the top, and the insulation's continuous. Here's a knee wall that they've added the blocks at the top and bottom so that insulation in the knee wall is enclosed on all 6 sides. Anything wrong with the step flashing and the flashing on this roof? Like everything's wrong? Can they fix it? Sure, they're going to have to cut the Tyvek, put a piece up underneath, and lap back over the top so they shingle it. Not very cool where they did their air barrier, but they didn't run it down behind the tub. We didn't talk much about it, but we got to think a little bit about it. We were concerned about the rim joist going outside. What about the rim joist that separates inside a house here on the left and the garage where we get a lot of leakage? Those blocks that you put in on TJIs aren't air sealed. And so in this case, they have spray foamed all those so that we have a good air seal between garage and inside the house. Here they have put foam on the outside of this slab on grade, which is required if you're in a cold climate. And here is the liquid applied weather barrier that I think someone asked about a little bit earlier. You need to make sure it is an approved liquid applied weather barrier and air barrier, and it is not a vapor barrier because we don't want a vapor barrier on the outside.
They make an OSB product that's already got it on.
They make an OSB product called Z
Yeah, that's it.
Z something, and it has tape and everything.
Tape the seams.
You tape the seams, and I might have a picture in here, and that's a good product. Here we have front door on the left and a porch that goes out, a covered front porch, and they haven't blocked above the front door. What's going to happen? Is it going to get insulated and sealed? Maybe not. I would think it's not. Here we put blocks in, but we haven't finished sealing them. We got the gaps on the side. Here we have those wall cavities that are getting insulated on the left, and they haven't put blocking across the top. Here we have a cantilever, again with blocks going out, and they're not sealed. Fur downs, drop ceilings, and no lid has been put in either one of them. Now this doesn't seem like a big deal, but they come in and blow insulation on them, and then the insulation fills it up, and then we have a little spot here that has no insulation. And then we have all the air leakage that occurs all the way around it. Here it's done right. We're going to have some ductwork running through this chase, and they have drywalled it first and sealed it. And then here's one that's really interesting. Us talking about that stack action and all that pressure coming up against our ceiling and trying to push moisture up into our attics and everything, and all the air leakage that we get at our interior walls. And this one, we have our baffles on the right-hand side there. They put rigid foam and sealed those, and then they have sprayed foam all the way across the top side of the ceiling drywall. So they're sealed everywhere. I don't think you need to go to quite that extent. You could just spray foam over the top of your walls and your boxes, but it's going to be sealed. So in review, and this is our last one. We've talked about a lot of stuff today. We've talked about heat flow, the conduction, the convection, the radiation, and all the flow of heat we have in and out of our building. We've talked about our airflow, the leakage of air, the wind, the stack effect, the mechanical fans, and we've talked about our moisture, our bulk, our capillary, our diffusion, and finally our air transport. And I just want to summarize by saying we need to be worrying more about our air transport moisture, the moisture that we're pushing all over our buildings by the way our buildings are built or the way they're ventilated, and maybe put some of the others a little bit further down on our list. You know, there's lots of things, the rim joists, there's many things that we've talked about. I hope this is beneficial to you, and maybe we'll see you on another one. Here's my contact information. If you want to talk to me, I seriously would prefer, if you can, send me a text. If you can describe your question, that would be great. If not, just text me and say, hey, I got a question, I need to talk to you. I'll call you. If you can put it in the email, that's even better, because sometimes I'm busy during the day or I'm playing during the day, and I can answer them. With my state contract, I want to make myself available to you, but I'd appreciate it if we could make it so that it works well for both of us. Thanks so much, and we'll see you next time.